Good morning. Thanks very much all for coming out early. I want to start this morning with a question. And I think perhaps many of you will know the answer to this question, in which case you will think it's a silly question. But it's still fun to think about. So what I want to know is, which was the first cataclysmic variable to be discovered? It was UGEM, of course, in 1855. It's a lovely little paper that's actually encourage you to go and read it, because it describes so many of what we think of today as dwarf novae: the flickering, the blue color during outburst, the recurrence time. It's really great. So here we have the number of CVs known versus time, starting off with UGEM over here. The second CV to be discovered was SA Cygni, the one that Stella showed us a really long light curve from yesterday. But it took more than 40 years before it was discovered. And after that, another 80 years or so before we had this picture of what a CV is, and a white dwarf accreting from a donor star and a thermally unstable disk around it. So the point is that it took more examples than just UGEM before we really understood what was going on. Having many examples of the same thing shows us which are the common properties to a class of systems, and which are the stranger, the odd properties. SDSS led the charge on big surveys from around 2000, and right now transient surveys are all around, a variety of them for different science reasons. To a certain extent, a lot to look for supernovae, but there are various other science motivations for these surveys. But you can see how they have really ramped up the number of CVs we know coming from these transient surveys. I'll get back to the numbers a little bit later on, but for now I just want to say why we look at transient surveys, what the value of transient surveys are for CV research. I'll focus on Gaia alerts as a transient survey, and then also talk about some of the problems we have with CVs that are discovered in this way, and what we might do about them in the future. The two surveys that have really led the charge for CV research in this field are the Catalina Real-Time Transient Survey and Assassin. Now these two surveys took slightly different approaches. Catalina going really deep to 19 to 21st magnitude, depending on which of the three telescopes they used. They cover around 80% of the full sky, avoiding the galactic plane for crowding reasons. But in the 12 years that they were running, they discovered 1,387 CVs, of which 80% of them were new, were not known before the start of CRTS. And just as an illustration, the reason for that is because of the depth that they use. This is just the magnitude distribution of the CRTS CVs in blue, and the ones highlighted in green are SDSS CVs that were known before the start of CRTS. And you can see that Catalina goes about 2 to 3 magnitudes deeper, and that's the reason for discovering so many more new CVs. Assassin is not as deep. It only goes to about 17th magnitude, but they cover a particular area of sky more frequently. They use 4 different sites, and they've just added another site in China as well. And so they do cover the full sky. A couple of years ago, so they started covering the galactic plane as well. And in the 6 years that they've been running, they've already published 1,963 CV candidates. What the light curves from these surveys have shown us is that there is a great variety in the variability of these CVs. Some of them show very frequent outbursts, some less frequent, some only have a single outburst in 10 years of the survey. And then also that some of them are detected in quiescence and in outburst, but there are some which are only detected when they are in outburst. But we can go to other surveys that are deeper, things like SDSS or pan-stars, and then look for the quiescent object in that survey. So here we can see CRTS detected this at just above 20th magnitude, and in SDSS there is a 19.8 magnitude object there. In the same way here, we don't see this in CRTS in quiescence at all, but there is a 22nd magnitude object there in SDSS. And so that's one of the advantages of using transient surveys, is that you can discover CVs that are not below the nominal limit of your survey because of these very large outbursts that they have. What was interesting here is that in the 500 CVs from CRTS in the SDSS footprint, there was only a single one which did not have a counterpart in SDSS, which means that there isn't a significant population of CVs that are fainter than 24th magnitude. And with outbursts of 5 or 6 magnitudes, and Catalina being sensitive to about 21st magnitude, it does mean that it should be sensitive in principle to CVs that are in 25th magnitude or fainter, but there doesn't seem to be that many. One thing to watch out for is that SDSS is looking out of the galaxy rather than into the plane of the galaxy. So if this holds for other surveys that really do look into the galaxy, it would be interesting to see, and I'm not sure I can really give a reliable answer to that yet. Another thing that we can use transient surveys for is to use the number of outbursts detected as a proxy for the accretion rate. So what I did here was to take the light curves from CRTS and count the number of outbursts in each of those light curves, with the idea that systems with higher accretion rates should have more outbursts in their light curve. And of course, that a system with more frequent outbursts have a higher probability of being discovered, but it also means that they will be discovered earlier in the survey, and that's why you get this slope downward. The colors in this don't really mean anything. This is the number of outbursts detected in the light curve as a function of discovery date. The colors are just to guide the eye of the different years of the survey. So you can see that things with many outbursts are detected in the first year of survey, and that goes down later on. But the interesting thing to notice here is that the survey is dominated by CVs with only a single outburst in the 6 years that this was running. So it seems to be dominated by lower accretion rate objects in there. And this is just showing the same thing represented in a slightly different way as a cumulative distribution. This is the discovery date, and each of these lines are a different number of outbursts. So the top one is 9 outbursts over 6 years. This one at the bottom is just 1 outburst in the 6 years. So you can see ones with more frequent outbursts are discovered early in the survey, but it also flattens off really quickly. There wasn't a single one discovered in the last 3 years or so of this was done, whereas the ones with just a single outburst, their number just keeps rising and rising towards the end of it. So it suggests that that will continue rising. The new CVs to be discovered from this will increasingly be low accretion rate objects with few outbursts. And that's the high accretion rate objects where we see many outbursts in the light curve have all already been found within this footprint. Just to test this idea again of linking the accretion rate to the number of outbursts, we also had a look at some of the spectra. One of the main results that came out of the SDSS survey was that the short period low accretion CVs, things that are close to the period minimum, have spectra that are dominated by the white dwarf. So you see the wings of the white dwarf in their spectra like this. And from the spectra that we took from the CRTS objects, we found a very similar thing. The things that the CVs with white dwarf dominated spectra tend to have fewer outbursts, and ones that are dominated by the accretion disk or the donor star, they tend to have more outbursts. So 60% of the white dwarf dominated CVs had only a single outburst in the light curves of CRTS. Here you can see this was the number of outbursts over here. The ones with fewer outbursts are the white dwarf dominated, the green line at the top there, and that's significantly different from the spectra that are dominated by the disk or the donor star. So from 2 angles, we have this idea that this is low accretion rate, both from the spectra, so you can see the white dwarf, the disk is really faint because the accretion rate is so low, and then in terms of the number of outbursts that we see to see a low accretion rate object. A year and a half after the second Gaia data release, I think Gaia probably doesn't need an introduction, but Gaia Alerts as a transient survey is perhaps less well known. But there are great advantages of using Gaia as a transient survey as well. One, that it is a uniform all-sky survey, just using a single telescope rather than the multiple telescopes of the ground-based surveys. And it also has very high spatial resolution. So even in the plane, it's possible to get really good results, good photometry, and also very high dynamic range. So you detect CVs or objects at both the faint and the bright ends equally. Gaia also doesn't have any weather constraints, or at least not as variable as they are on Earth, which makes a real difference to the survey. And then if we combine this data with the main Gaia data release, we can convert this to space densities, as Anna told us yesterday. And so using Gaia for this kind of work is a really valuable thing to do. Another thing that really sort of sets it apart, I think, from other surveys is that for every observation you have, you also get a color or low resolution spectrum for every observation. And I'll show you that later on. It feels like only yesterday when I was watching the launch on the stream, live stream for Gaia. So it's a bit shocking to realize that we've already ended the nominal mission. We are now in the extended mission already. It's been approved to 2020, and there's an indicative approval to 2022. And over this time, Gaia will observe every star an average of 100 times. So that's the light curves that we use to look for transient variability in the data. Vastly simplified, this is the process for detecting Gaia alerts. The star is observed by Gaia, then the data is downlinked to ESA, where it gets processed here in Madrid. Basic calibrations applied in the initial data treatment pipeline here. Then the data is sent to Cambridge, where we associate each source with previous observations of the same source and look for variability. And then every alert candidate is inspected and published to a public website from where anyone can find their favorite object and go observe it, please. Every page, every alert has a page like this, where all the Gaia data appears with a finding chart, the Gaia light curve, the BPRP spectra, and all of the information that Gaia has on that object. And the great thing about this is that this is completely independent of the main Gaia data releases. Once we decide that something is an alert, all the data for that object becomes public immediately. Everything from before the alert and also after the alert. So you can go back, check back on specific alerts that you're interested in, and continue to get the Gaia data for that alert. So that's all public. But Gaia was not designed to be a transient survey, though, and so it has a few little quirks that you have to be aware of. One is that it takes 1 to 2 days for the data to come down from the spacecraft and to be processed in Madrid. And then the processing in Cambridge adds on another day. So there's a delay of about 3 days between Gaia observing a target and we publishing. And so that's something you really have to keep in mind if you're looking for fast transients, or if you want to follow up fast transients. In general, you really have to have the telescope available and go immediately, because at this point the transient is already 3 days or so old. And this does mean that, with all of these other transient surveys that are running, many of these surveys are finding outbursts or finding supernovae in particular before Gaia does. But it's still a very valuable thing to do, because our astrometry is by a factor of 5 or so better than any of these others. So we have very, very precise astrometry and also very, very good photometry, and then the light curve that is available for that object before and after. Also, things like that have been developed for transient surveys on sky, things like difference imaging, processes like that, cannot be used with Gaia data. It doesn't produce any images. All of that data processing is done on board. So each of the alerts has to be inspected by eye. We call it our wet neural network, where every alert is inspected by humans and vetted before it is published. And that's just one of the things you have to do if you only have a catalog to work with. But so far, we've published 9,642 alerts today so far, and we're publishing them at a rate of around 9 per day. Each of these changes in the slope is a point where we made some significant change to the way that the alerts were identified, and that's the rate at the moment, 9 alerts per day. 23% of the alerts are spectroscopically classified. That's driven largely by supernova surveys, things like PESTO, that follow up the supernovae that we find. But if you want to know in terms of CVs specifically, the CV discovery rate is around 8 per week, so just more than 1 CV per day found from this one survey. Alert identification remains one of the most difficult parts of this for all transient surveys, and in particular for deep transient surveys such as this. And there definitely are days where I feel like this, where they all just look the same to me. But fortunately, that's not the end of the story. Here I show you some of the BPRP spectra at the bottom with their corresponding light curves for various classes of objects. And you can see that there is definitely a clear difference between the various classes of objects. This first one here is an outbursting CV, and it's actually eclipsing as well. You can see the points drop out there. It's a very blue spectrum of an outbursting CV. This is a type 1a supernova. They're actually quite characteristic from the spectra. This is a YSO. And this is a star that was alerted on because of a microlensing event. And we find that this, along with some contextual information, things like detections in other catalogs and proximity to a galaxy, things like that, those are the most characteristic events that help us to classify some of these alerts. Internally, we use a random forest classifier to do it, but if you've ever done work with these things, you'll know that biased input can really mess things up, and that's unfortunately the situation that we're in. It's very small samples of data to do something like this, and that's why we only sort of use it internally as a guide. But it is still very useful in terms of the spectra that we see. Our main confusion really still is between very young type 1a supernovae and then CVs and outbursts. They actually do look very similar in terms of color, and especially if it's something in a hostless transient where you don't see an underlying galaxy, it's difficult to determine what they are. And then we still have a lot of, I'll show you in the next slide, a lot of transients that are just completely unknown. From this, you can see that we're very much dominated by supernovae. These are candidate supernovae. Those have been confirmed. In general, this quarter of a year, those are the ones that have been spectroscopically classified. And then we have some candidate CVs, candidate supernovae, and then things that are just completely unknown. CVs plus candidate CVs make up 12% of our transients, and that was about what CRTS found as well. I don't know if that's any why that is, but it just happens to be similar to what CRTS found. Right. So the Gaia CV so far, there are a total of 985 so far, of which 27% are confirmed CVs. About half of them, 53%, are Gaia discoveries, things that were discovered for the first time by Gaia, in spite of this delay between observing Gaia's observation and publishing the alert. But only half of them are detected in Gaia Data Release 2. So about half of them are fainter than this limit, than 20.7, so are not in Gaia. And whether, as I said before, I have not done the cross-matching with deeper surveys to see if this holds, that we don't see CVs much fainter than 24th magnitude. My feeling is that it doesn't, that there are a substantial number of CVs that do not have quiescent detections in pan stars, for example. Our own follow-up has focused on the blue objects mostly. with the main aim of finding CVs and AM CVn stars. What I'm showing here is the BPRP color of all alerts, all other alerts in red, and in blue and green are the CVs and CV candidates. And you can see that the CVs are significantly bluer than most of the other alerts are. And so those are the ones that we are following up on. And it's worked well so far. We found 2 new AM CVn stars. This one over here, Gaia 16 ALL and 18 CJW. CJW was actually suggested to be an AM CVn before, but not confirmed, and then we detected this outburst, and again it was the amateurs who went out and measured the period for these systems. The period of 16 ALL is not known yet. And then this is an AM CVn from Assassin that we were able to confirm through this program as well. Gaia was, of course, the discoverer of the first AM CVn with a fully eclipsing white dwarf. Is a favorite object of Matthew's, and so I'll leave that to him to talk about. And then also we found the first, this is a known AM CVn, SDSS 0807. We discovered the first outburst of the system in Gaia as well. And the amateurs measured a period of 53.3 minutes, which is the longest period of any outbursting AM CVn that we know so far. Actually, at the time that Gaia was 14AE was discovered, its period of 49.7 minutes was the longest period for an outbursting AM CVn, and now we've increased on that again. And I think Matthew will say more about that in terms of the evolution of CVs and of AM CVn stars and what that means. Then also some of the helium-rich CVs. We discovered a system at the end of 2018, Gaia 18 CVI. It has a 21.7 magnitude, G-band magnitude object in SDSS, and we detected an 8 magnitude outburst of this object. It was found by Master just a day or so after us, half a day or so after us. And they reported it as a candidate nova because of the large amplitude of the outburst. But it was clear from the BPRP spectra that this was not a nova. Unfortunately, it was not ideal for follow-up observations. It was really very deep into morning twilight already. But some of the amateurs looked into this and realized that it had an outburst, a long-lasting outburst in 1949 as well, that's recorded on the Harvard plates. So like 70 years between separate outbursts. And then one of the amateurs who work with quite a lot, Josh Humsch, incredibly dedicated, even in extremely difficult conditions. You target never rising above, air mass 2.5 or something, air mass 3. He pointed his telescope and followed it into daylight almost. And he measured a superhump period, the superhump period of around 65 minutes. And this is interesting because this is right at the long end of the known AM CVn periods, but it also falls exactly where we know some of these sub-period minimum CVs that are helium enriched, where they fall. And it's really interesting to see, the very large amplitude outburst, the period. It makes it a curious object. Thank you. Now I'd like to get a spectrum and know what it is, but it's really difficult. At these sorts of magnitudes, to get a spectrum of signal to noise of 10, you need an hour on the VLT. And it's difficult to justify that, to take an hour spectrum to see just what it is for an object you think has a period of an hour, integrates across the whole orbit. And that's the problem with some of these transient detected CVs, that a lot of the very interesting objects we find are just so faint that there really isn't a lot you can do with them in terms of science, except statistics, perhaps. So what to do about that next is a difficult question. We're not even reaching LSST yet, and already we're at the point where it becomes difficult to do that. What I would like to do in future is Anna and I will extend on the work that she's done in terms of space densities, and for that to use Gaia Data Release 3, and specifically the spectra that will become available as part of Data Release 3. DR3 will be split into two sections. The first sort of early or third quarter of next year will have similar content to GDR2, but with the extra data that's included, the accuracy, the precision of the data should be much improved, and things like quasars happening to fall into our 150 parsec sample should hopefully be removed with the addition of this data. But the second phase of the full data release in 2021 will include the BPRP spectra, and from that we hope to identify a sample of CVs based on the ones that we already have. So in order to do that, I started updating the catalog that Anna mentioned yesterday. And so far, have about 9,820 CVs in this catalog. For now, VSX is by far the best catalog that we have at the moment. But at the rate that CVs are discovered, as I showed in those first plots, it's really hard to see whether, or to decide whether something is real, whether really is a CV, and to keep track of all of these changes. And this is done by volunteers from the AVSO, from working on VSX. So definitely do support them in their work over here. But it is also a problem of completeness. Just from buried in papers, I found an extra around 300 CVs that are not included in VSX yet. So I'll be in contact with them and get them to add that as well. So that's where the catalog stands now, is around close to 10,000 CVs. Around 70% of them are included in Gaia Data Release 2, but that's still very preliminary work. And around 60% of them are bright enough to have parallax measurements as well. And so this is where I'd really like to have your input, because looking at 10,000 objects individually is not so much fun that you want to do it more than once. So if there's anything in such a catalog that you think would be useful, do let me know. At the moment, the things that I'm working on are improved positions from Gaia or from pan-stars. And this is particularly important for Assassin, where the astrometry really is quite poor, and also CVs that were discovered with small telescopes. Some of the objects in the original Downs catalogue, have never been looked at since they were discovered, and have some poor astrometry. So we'll update those positions. Then I'd like to include a flag to say whether something is a confirmed CV, something that we are definitely sure is a CV or a candidate. Then some information about the brightness, maybe a quiescent brightness and an outburst, but not as much as was included in the Ritter-Kolb catalog, for example. CV type, like that is included in VSX, or maybe something simplified. So if you have some ideas of what you think would be useful in terms of a classification of CVs, do let me know. I'll include some Gaia identifier that would make it easy for cross-matching, whether that's the GDR2 ID or the GDR3 ID, we'll see. And then, of course, the orbital period, if that's known. So, yeah, I'd like to have your input on that, if that would be useful, and I'll leave up the conclusions there. Thank you very much.
The numbers of Assassin versus CRTS, I was a bit surprised that, given the difference of depth.
Yeah, it's as I say, this is exactly the problem with some of these CVs. They're all CV candidates, and how many of them really are confirmed, I don't know. Thing about Assassin is the sky coverage, also the coverage of the galactic plane. A lot of those candidates are in the galactic plane. CRTS avoids 30 degrees around the galactic plane, and a lot of the CVs in there, a lot of the new discoveries from Assassin are actually in the plane.
So I have two questions. One, if you can, maybe it's because I was a few minutes late, if you can clarify I didn't quite understand why there wouldn't be CVs with less than 24th magnitude in quiescence. And the second question is, you mentioned the difficulty in getting time with the VLT or whatever large telescope. What people from the Cherenkov collaborations or even Fermi integral do when they need time, let's say they go to the next wavelength, which is the X-rays, and they need to time for their transients. They just write a proposal saying, we have lots of interesting stuff in our data. Please give us some target opportunity time because we have such scientific cases and we'll choose a couple of them and use them well. Can you do something like that?
So I'll answer the second question first. Yes, we are doing something like that. We are doing Gaia follow-up in exactly that way. But the problem is not necessarily just getting the time. The problem is that, you know, in order to get a spectrum that's scientifically useful, something that has signal to noise of 10 or 15, so you can actually, you know, see something in the continuum of the spectrum, you need an hour of integration time. You know, the orbital period of this thing, we think, is about an hour. So, you know, there's no chance of doing any phased resolved information or measuring masses or doing anything with the data, and that's the problem. And your first question is about the faint CVs. The reason there is that we said that CRTS is sensitive to 21st magnitude objects. CVs have outbursts of, you know, 4, 5, 6 magnitudes. And so it means that in principle it should be sensitive to systems that are 25th magnitude. But within the 500 that are in the SDSS footprint, there was only a single one which did not have a quiescent detection in SDSS. So they were all, you know, 23 magnitude or brighter. And from that we concluded that there cannot be a large population that is much fainter than 23 magnitudes.
I was curious about the 500 new CVs from Gaia.
Yes.
And do you have a feeling for how many of those 500 you would think or bet on are real CVs?
I would say the majority. It's difficult now for me to put a number on that, but I'd say the majority. Because of the spectra, the BPRP spectra, and then also because of cross-matching in other surveys. So we check all of the light curves against ZTF, against a CRTS, and sometimes you see outbursts in other light curves as well. So multiple outbursts is one of the things that we do use to call something a candidate CV. I'd say the majority of them.
Okay, let's thank Elme so we can keep on schedule. Sorry, no. Okay, our next speaker is Matthew, and he will be talking about the evolution of AM CVn binary stars.
Thanks. Okay. Hi, everyone. My name is Matthew. I'm a postdoc at the University of Warwick, where I work on AM CVn binary stars. And so today I'm going to be talking a little bit about these binaries. I'll start off with an introduction, because I'm aware it's sort of a fairly niche field within AM CVn, within CVs. And then I'm going to talk about the particular, like one of the big open questions in the field of AM CVNs, which is where they come from, so how they evolve. Okay, so to start off with, what are these things? So the figure here is one I'm sure a lot of you are familiar with. It's period distribution of CVs. And there's a fairly well-defined period minimum at about 75, 80 minutes, below which not very many CVs are known. But there are a handful which have shorter periods than this, and almost all of those binaries are AM CVn systems. So all of the AM CVNs that we know have these two things in common. Firstly, they have very short orbital periods, so between sort of 5 and 65 minutes. And secondly, the accreted material that we see in the binaries is dominated by helium. So there's often quite a few metals present as well, particularly nitrogen, but in almost all the systems there's no detected hydrogen present. So the number of systems that we know has increased a lot over the past couple of decades. it's not uncommon to find papers even from sort of the early 2000s talking about there being 10 or 12 known AM CVn candidates. Since surveys like SDSS and PTF and Assassin started finding more systems, we now know of around 60. There's 56 that are published and a couple more which are sort of still on the way. And as I say, all of them have these two factors in common, short orbital periods and helium accretion, and from those two things together, you can say something about the nature of the system, particularly the donor star. So you know that the donor star has to be something quite evolved, and it has to be quite dense, just so that it can fit in a binary with a period this short. So one of the things which sort of drives interest in these binaries, as well as being interesting in their own right, they're quite powerful emitters of gravitational waves, not at frequencies that we can detect from the ground, but from a space-based antenna like LISA, which is expected to launch in the 2030s. So the figure here is all of the known galactic binaries which we think LISA should be able to detect, and it shows the strength of their emission against the frequency compared to the LISA detection limit. And I don't know if the colors have come out too well from the projector, but the black points, which is most of them, are AM CVn binaries, and the red and blue points are non-accreting binaries. So the majority of the known binaries that we think will be detected by LISA are these AM CVn binaries. So it's been suggested if we can sort of characterize some of these binaries that we know, we can use them to test how well LISA is calibrated once it launches. Okay, so the question about these binaries that I'm particularly interested in is where they come from. So there's a fairly sort of there's a traditional description which you might have heard of AM CVNs, which is that they're accreting double white dwarfs. It's one of several proposed models for where these binaries can come from. It's generally, I'd say, the one that's got the most press over the past couple of decades, and historically sort of been favored by some of the evidence and some of the modeling. But as Ashley mentioned in her talk yesterday, there's some more recent evidence which suggests this might not be the best description of where these binaries come from. Okay, so overall there are three models for where AM CVNs can form by. The first is the white dwarf donor channel, it's where the AM CVn descends from a double white dwarf. The second is somewhat similar, but instead the donor is a helium burning star. And the third is the evolved CV channel, where the binary just descends from a CV with an evolved donor. And I'm going to take you through a kind of sort of cartoony representation of what these evolutionary channels look like. I'll start off with the sort of typical model of CV evolution, which, again, I'm sure many people are familiar with. So you start off with two main sequence stars. One of them starts to evolve off the main sequence. As it grows, it engulfs its companion, and you have this sort of common envelope around the two binaries. Once that clears, you're left with a white dwarf and a main sequence star. And when accretion starts between the two, because the main sequence star is hydrogen dominated, you accrete hydrogen and you form a CV. For an AM CVn, our channels start off quite similar. So I'm showing here two channels, the double white dwarf track and the helium star donor track. In both cases, you again start off with one common envelope phase. As one of your stars evolves, you're left with a white dwarf and a main sequence star. What you then need to happen before mass transfer starts is for the second star to again evolve off the main sequence. You go through a second phase of common envelope evolution, and you're left with one of two things, either a double white dwarf binary, in which the second star which evolves is a much lower mass, sort of helium core white dwarf, or you can be left with a white dwarf and a helium burning star. So this would be something like an SDB star, or sort of like the core of an asymptotic giant. So it's burning helium and it has a shell of helium around it, but then the hydrogen, which would have been the atmosphere of the giant star, has been stripped away during this common envelope evolution. In both cases, you start accreting, and you accrete from the helium-dominated donor, and so it looks like an AM CVn. And this accretion starts at orbital periods of order 2 or 3 minutes, and then over time, the system evolves outwards towards longer orbital periods. So our third channel is the evolved CV channel, where you need to start off with a CV which has an evolved donor. So before the mass transfer starts, the donor's already built up sort of a helium core. Then over the course of sort of long time scales, billions of years, by the mass transfer, you can strip away the hydrogen from the atmosphere of the donor. You reveal that helium core, and your accreted material becomes helium-dominated. And so you sort of pass smoothly from being a CV to being an AM CVn. Okay, so all three of those models have sort of some open questions about them. In particular, the last channel that I showed, the evolved CV track, has difficulty explaining, when people have modeled it, they've had difficulty getting rid of all of the hydrogen from the donor within a reasonable timescale. So the region of sort of initial parameter space where you can form an AM CVn is fairly small, and so population synthesis suggests that that it's difficult to contribute much to the AM CVn population by this channel, but that it perhaps only contributes a few % of the known systems. Population synthesis has generally favored our other two channels, in which we have 2 phases of common envelope evolution. And to choose between the two, when people have looked at the composition of the accreted material, they've generally seen more nitrogen than carbon, which is more consistent with the donor being a white dwarf, which has recently undergone CNO processing, than with the donor being a helium star, which has undergone some triple alpha burning, which would have produced more carbon. Okay, so what we'd like to do, now that we have our 3 models for how AM CVNs can form, we'd like to look at the systems that we know and look at each system and say which of these channels could it have formed by. One of the ways we can do this is to look at the donor properties, particularly its mass and its radius, because those will be different for each of the 3 channels. So the figure here is donor radius against donor mass. Each of our sets of lines are evolutionary tracks for the 3 channels. So these solid lines are models where the white dwarf is a donor. Each track is a slightly different core temperature of the white dwarf donor. The dashed lines above are models where the donor is a helium star. So because the donor has still been undergoing some burning, it's got a bit more thermal support than a white dwarf would have, and so it's a larger radius for the same mass. And these dotted lines coming down from the top are where we're descending from a CV with an evolved donor. So on that figure, our donor would be evolving from right to left as it's losing mass. And on the same plot, you can draw these lines of constant orbital period. That just comes from the fact that we know the donor is Roche lobe filling, and so we can calculate its mean density from the orbital period. And so these are lines of 10, 20, 30, up to 60 minutes orbital period. So if we can find systems where we can measure the mass and radius of the donor, we can plot them on this figure. A difficulty comes from the fact that for almost all AM CVNs, the donor is much fainter than the rest of the system, and so we can rarely see the donor directly. The systems where we can study the donor most easily are eclipsing systems. I'm going to be talking about 2 of these. These are the 2 which have been published. Later on today, you'll hear about a third system which was discovered more recently. Excuse me. These 2 are YZLMI, which was discovered in 2005. The measurements that I'll be using come from this paper by Chris Copperwheat in 2011. And the system that I've been working on is Gaia 1488E, which, as Elme mentioned, was discovered from a Gaia Science Alert in 2014. The original discovery paper was published by Heather Campbell, and my follow-up paper was published last year. And so if you look at an eclipsing system, as the donor passes between us and the rest of the system, we see a light curve, something like this. You have a deep feature in the middle where the central white dwarf is eclipsed, and you have a fainter feature following that where the bright spot is eclipsed, the bright spot being the point where our accretion stream hits the edge of the accretion disk and causes something of a shock. And so you can fit a fairly simple geometric model to a light curve like this, and you can use that to measure a range of properties for the two stars, in particular the donor mass and radius, which is what we were interested in to compare to our models. And so for our two eclipses, we can plot the mass and radius that we measure. YZ LMI comes out here, so it lies in this region of space which could be explained by either having a white dwarf donor or a helium star donor, those two being the more favored channels. That's more or less consistent with what we expect. For Gaia 14EE, though, we found a more surprising result. So the mass and radius that we measure seems to fit best with the system having descended from a CV with an evolved donor. If you remember, our sort of expectation going in is that this channel maybe produces a few % of the AM CVn population. So for the second system you look at, to fit with this channel is not impossible, but it is somewhat surprising. And I should note that although we fit with this channel in terms of mass and radius, the particular tracks that I've plotted here predict some amount of visible hydrogen in the accreted material of around 1% up to 5%, whereas we have a measured upper limit of about 1 part in 10 to the minus 4 hydrogen in the accreted material. So there is that inconsistency even with that channel. We'd like to add more systems to that plot. And for that, we need to look at a couple of other ways of studying the donors in these systems. One way is to use spectroscopy, phase-resolved spectroscopy of the system. If you can find a spectroscopic signature of one of our two stars, then you can track the dynamics of the system. There's a couple of reasons this becomes difficult for AM CVNs. As Elme mentioned, part of the problem is that the orbital periods are particularly short, and a lot of the systems are quite faint. So getting sort of phase-resolved spectroscopy with usable signal-to-noise becomes quite difficult. Unlike many CVs, AM CVNs, you don't see the donor at all, and so you need instead to have a spectroscopic signature from the accretor. Some AM CVNs have this, but a lot of them don't, and so that makes things more difficult. A second method, which Stu mentioned in his talk yesterday, concerns this photometric signal that a lot of AM CVNs show, called the super hump. It's related to the precession of the disk, and there's an empirical relationship between the period of that signal and the mass ratio of the two stars. This has been quite widely used for AM CVNs, but there are a couple of sort of health warnings that should be given. It's an empirical relationship only, and it was derived based on hydrogen accreting systems. So AM CVNs, the composition of the accreted material is different, and the mass ratios are all sort of clustered at one end of the sort of more extreme end of the CV mass ratio range. And so it's not necessarily guaranteed that this method is calibrated well. We only have two AM CVNs where we've been able to test the calibration, and one of them it agrees, the other it doesn't agree so well. But it's not clear whether that other system, perhaps one of the measurements is somewhat uncertain. So using these two methods, we can plot all of the AM CVNs which have measured mass ratios on this plot. The green points are spectroscopic measurements, the gray points are the super hump measurements, and we have our two eclipses from before. For the systems where we only know the mass ratio, I've assumed an accretor mass of 0.7 solar masses. And across all of these systems, it seems as though the donor is somewhat inflated compared to what you'd expect for a white dwarf donor. So most of these systems lie in this region of space that fits with being a helium star donor. There's a couple of systems which could perhaps fit with both channels. There's no system which can only be explained by being a white dwarf donor. And we have a couple of systems up at the top which perhaps fit best with being evolved CV descended. So from these measurements, it leans towards perhaps saying that not very many of these systems have white dwarf donors. Another possibility is that if there's something in the white dwarf, in the double white dwarf evolution, which could perhaps inflate the donor more, sort of heat up the white dwarf donor and cause it to be more, push it up into this region of mass radius space. But I wouldn't be able to suggest what a mechanism like that could be. So I'm going to look at an independent sort of an independent measurement you can do, which also moves towards looking at how these systems have evolved. And that's to look at the mass transfer rate, which we can measure using the system's Gaia parallaxes. So the most direct way, the simplest way you can do this is just look at how bright the system is. So this figure is the absolute magnitude of all the AM CVns which have Gaia parallaxes available as a function of orbital period. And the two dashed lines here are how bright you would expect the central white dwarf to be, give an assumed mass transfer rate. And the mass transfer rates are consistent with being a cold white dwarf donor or a hot white dwarf donor. So the hotter donor has a higher mass transfer rate. At the short period end, all of our AM CVNs are much brighter, and that's because they're dominated by the accretion disk. At the long period end, say from 40 minutes to 70 minutes, most of these systems should be dominated by the central white dwarf. And for Gaia 14EE, which is the eclipser, which is at a period of 50 minutes, that is indeed what we see, that the light is almost all from the central white dwarf. And yet all of these systems are brighter than you would expect the central white dwarf to be, which perhaps suggests a higher accretion rate than these white dwarf donor models predict. We can also try to measure the mass transfer rate more directly. This was some work that my supervisor Tom Marsh did. It was published in a paper by Gavin Ramsey. For 15 AM CVNs which have sort of fairly reliable Gaia parallaxes and also a good range of flux measurements in various wave bands, we performed some SED fitting using just a fairly simple model of a white dwarf and an accretion disk, and use that to try to measure the mass transfer rate of these systems. There's a couple of points which seem to be somewhat outliers, but the rest follow a general trend which more or less runs parallel to our predicted models, but somewhat higher. So a higher mass transfer rate, which again suggests more inflated donors. And this perhaps explains another surprising thing that's been seen in some AM CVNs, which Elme mentioned. So in the original models of these systems, it was generally predicted that you would have outbursting systems up to periods of about 40 minutes, and after that the accretion rate would be too low and you wouldn't see any outbursts. But as Elme mentioned, we've seen quite a few outbursting systems from periods up to, say, 55 minutes, which fits with this if the mass transfer rates are higher than has been predicted. Okay, so to go on to some consequences of this, it seems that from what we've seen, it seems like not very few, if any, of our AM CVNs seem to have white dwarf donors. Those double white dwarf systems have to go somewhere else. If they're not able to accrete stably, then instead they must start to accrete unstably. And so perhaps a higher percentage of the white dwarf, of the double white dwarf systems merge than has been thought. It perhaps goes some way towards explaining the another open question in AM CVNs, which concerns their space density. So it's been seen in AM CVNs for a while that the space density that we measure from our known systems is less than has been predicted from population synthesis by a factor of about 10 or so. And if one of our favored channels that can produce AM CVNs doesn't contribute very much to the population, then that perhaps goes some way towards explaining that discrepancy. Okay. And I also wanted to talk about another consequence of this, which concerns the gravitational wave emission. And so I'm going to go back to my favorite system, the Eclipser, Gaia 14AE. So this big red blob here is the mass and radius that we measure for the donor in Gaia 14AE. The red blob lower down here is what you would have predicted if you assumed that the donor was sort of a cold and degenerate white dwarf. And so the mass difference between these two measurements is about a factor of 3, which means the gravitational wave signal is stronger by about a factor of 3, which then means that the volume over which you would be able to detect a system like this is increased by about a factor of 30. And so if it seems to be true that the donors in AM CVNs are bigger and hence more massive than you would predict given cold white dwarf donors, then you would expect LISA to detect more of these systems than you would predict if you assumed cold white dwarf donors. And so if you want to kind of understand the gravitational waves from these systems, you have to understand what the donors look like. Okay, so I will leave you with my conclusions, and thank you for listening.
Okay, questions?
Yes, I'm a bit confused about these inflated donors. I don't know very much about AM CVn systems. At so short periods, how can you have an inflated? You mean bloated?
Yeah, so I just mean that the radius being larger than a degenerate white dwarf would have. So suggesting some sort of thermal support. Yeah.
Okay, and a second question is, what is the visual magnitude of Gaia 14AE?
The apparent magnitude is about 18.5. Yeah. To go back to your first question, were you asking for the sort of very short period systems, how you can fit an inflated donor in? That is true, and I think for we know two systems which have periods below 10 minutes, and I think for those systems it's thought that the donor has to be something sort of completely degenerate just to fit inside a binary that short. Both of those systems, the P dot is still, the system is still inspiraling rather than spiraling outwards. And some modeling work of these binaries by Ken Shen sort of suggested a mechanism which could destabilize the very short period systems through friction with Novae ejector, which would then cause the two stars to effectively, so you would form an AM CVn for a short period of time at a very short period, and then it would merge rather than being able to expand out to longer orbital periods. So it might be that the short periods can have degenerate donors, but then the longer period systems perhaps have more inflated donors because they're formed by a different channel. Perhaps.
All right, so for the helium star channel, so you would expect that the helium burning star would contain some appreciable amount of carbon in the core. At least at some point after some sufficient mass transfer, when the core is now transferring, so you would expect the carbon to be present in the disk. So my question is, are there any AM CVNs with observed significant amounts of carbon lines?
Yeah, that is the sort of the fly in the ointment of this conclusion. For the systems where we've been able to look at the carbon to nitrogen ratio, we see a lot more nitrogen than carbon, which fits a lot better with the donor being a white dwarf than with it being a helium star. So that seems to go against what we're seeing from the mass radiuses and the mass transfer rates. So I'm not really sure how to reconcile those two.
So I know that the evolved donor channel is kind of disfavored, at least in the past, but we know currently probably something like 20, 25 of these sub-minimum period CVs, they must evolve into something. Maybe not AM CVNs, but there's a lot of them.
Yeah. Are there that many? I thought it was more of order 10 that are sub-period minimum, but okay. Yeah.
You mentioned super hump relation. Do you monitor somehow outbursting systems to establish whether this relation is true and useful for the AM CVns?
Yes. So yes, there's a couple of groups that do that. In particular, a large Japanese group with Taicho Kato. They monitor quite a lot of these outbursting systems to measure the super hump.
Can you remind me again what the theoretical reasons were behind disfavoring the CV channel for making these? Was it from some binary population synthesis? Was that what you were saying, or
for the evolved CV channel?
Yeah.
I think it's more from sort of modeling of individual systems. So I was talking to Lorne Nelson about this. There was a paper, Gaia and Nelson, a couple of years ago. I was trying to ask him if it was possible to recreate our Gaia 14 AAE from the evolved CV channel, and he generally said that it was, but it's, like I say, it's quite hard to replicate the lack of hydrogen that we see.
These were using MESA simulations, was that right? Or
I don't think it is using MESA,
okay.
But I'm not too sure.
I'll check. Yeah.
But the problem he was saying is sort of, you can create a system with no hydrogen, but the region of like initial parameter space, so your like 0-age CV has to be, it's a very small region of space you can start off from. And so you can perhaps explain some systems like this, but the more AM CVNs you form, the more of these like superior minimum CVs with helium, with hydrogen present as well, so you have to form as well.
Yeah. Okay, thanks.
Any other question? No? If not, let's thank Matthew again.
Thanks very much.
Okay, our next speaker is Ingrid. She will be talking about Gaia DR2 catalog of extremely low mass white dwarf candidates.
What about now? Good, okay. Morning everyone, my name is Ingrid Pelisoli. I'm a postdoc at the University of Potsdam. And today I'm going to talk about extremely low mass white dwarfs, or ELMs for short. And in particular about my methods and motivation to build a catalog of ELM candidates from the Gaia DR2 data. So since I'm the first one talking about ELMs in this conference, I'm going to spend some time explaining what they are and why we should care about them. So ELMs are white dwarfs whose mass is below the single-star evolution limit given the age of the universe. What do I mean by that? A low-mass main sequence star that would evolve as a single star normally would take longer than the age of the universe to become a white dwarf of this mass, because the main sequence lifetime is longer than a Hubble time. So in order to explain ELMs, we need some kind of mass loss enhancement. And of course, the easiest way to achieve that is to add another star to the picture, as illustrated here. There are two possible channels, the stable Roche-Lobe overfold channel and the common envelope channel, which is similar to Matthew already described, because ELMs are possible progenitors for AM CVn systems. So this figure is illustrating the case where we have an ELM with a canonical mass white dwarf companion. What happens here is that following the formation of this most massive white dwarf, we are going to have mass transfer from the low mass main sequence star onto the white dwarf. This can happen in a stable manner, so we have the Roche-Lobe overflow channel, or it can happen in an unstable manner, forming a common envelope. And in both cases, what happens is that the outer layers of this low mass main sequence star are stripped away, leaving a helium degenerate core, so this has to happen before the onset of core helium burning. And we have this helium degenerate core with a thin hydrogen layer, which is the ELM. The masses of ELMs, well, for the stable Roche-Lobe overflow channel, seem to be up to 0.3 solar masses, down to 0.14. For the common envelope channel, we have masses up to 0.4, But here I'm going to use 0.3 as an upper limit for ELMs because there seems to be an observational difference for systems with mass above 0.3, as I'm going to go back in a minute. Of course, because they seem to come from an binary evolution channel, ELMs are good constraints to binary evolution, in particular to closed binaries, so everyone in this conference should care about them. This binary evolution channel is supported by the non-sample that seems to be composed by 100% of binaries, or consistent with a binarity of 100%. However, before Gaia, we had an issue determining the radius of the stars, because the radius of a low-mass white dwarf is hard to constrain based on spectroscopy alone, which is the way we usually do for canonical mass white dwarfs. That has two main reasons. One of them is that ELMs, especially in the pre-ELM phase where they still can have some residual burning, they can have parameters overlapping the main sequence. So they can become bloated and they can have a radius as large as a main sequence star, even though with a lower mass. And another reason is that in the range of temperatures that we observe the ELMs, where they spend most of their time, the Balmer lines are not so sensitive to log G. So what happens is that we have a large uncertainty, and what happens is that we cannot really tell between a distant main sequence star and a nearby ELM. This, before Gaia, was known as the SDA problem, and I'm illustrating here with 3 spectra. The top one is the A-type white dwarf with a log G of around 7. It's somewhat hot, so we can look at it and we can say this is a white dwarf. This middle one is a main sequence A-type star, and the third spectrum, we fitted this spectrum and we obtained a log G of 5 with an uncertainty of basically 1 dex. So as I said, this can either be a distant main sequence star or a nearby ELM. So we cannot really constrain the radius based on that alone. So what people did is, if this is in a closed binary where I cannot fit a main sequence star, it's an ELM. Otherwise, I don't know. So binarity was assumed as a requirement to classify an object as an ELM, essentially. But if we go a little bit above 0.3 in mass, as I was saying, there's an observational difference. For objects with mass between 0.3 and 0.45, which are usually referred to as low mass white dwarfs instead of extremely low, astronomers are not very creative with names, right? What happens is that the binarity is only 70%. So it can be that there are other formations mechanisms involved, apart from binarity. This has been suggested in the literature. For example, we could have strong wings due to high metallicity. We could have a substellar companion that caused the outer layer to be removed, and this substellar companion then evaporates, so we only observe a single star. Or it can be that the star was originally in a binary, but we don't observe it in a binary anymore. One case would be, for example, supernova stripping. So if the companion explodes as a supernova, and then the outer layers of the ELM progenitor are removed, this could leave, for example, a signature in the in the galactic orbit of the ELM. And another possibility is that these low mass objects that are observed as single are as a result of a merger. And one question that I've been asking myself since I read about these different channels is, could they form the ELMs that we observe below 0.3 as well? And as it stands now, we cannot really answer this because, as I said, we've been using binarity as one of the requirements to call something an ELM. So in order to test this, we need a sample that is classified as ELM regardless of binarity. ELMs are cannot only give constraints to binary evolution, but ELMs also present challenges to binary evolution. One very nice example is this K2 object published recently by Masuda and collaborators. It is an ELM in a binary with a solar type star, and it was detected only through self-lensing. So we see here this increase in brightness caused by self-lensing. And the ELM in the system has a mass of 0.2 solar masses, so it would require enhanced mass loss to be formed. However, the orbit in the system is too wide, it's over 1 astronomical unit, so it's too wide for the system to have formed, to stable Roche-Lobe overflow, or even to have interact at all. So in the paper they referred to this as an impossible ELM, because it's putting it's placing a challenge to our current models of ELM formation. Another reason why we should care about ELMs, and I always mention this whenever I write a proposal because it's where the money is nowadays, is that they are gravitational wave sources. So this is an updated version of the same plot that Matthew has already showed. And there are two ELMs here in particular. One of them was discovered in STSS data by Brown and collaborators. It is up there, and it has an orbit which is around 2.8 minutes. So it's well above the LISA 4-year detection limit. And the most recent one that was discovered by Birch and collaborators has an orbit with an orbital period of less than 7 minutes, which is the one up there in red. This object would be detected by LISA within 2 weeks of operation. So ELMs can be really strong gravitational wave sources. I'm mentioning these two, but there are other objects further down here, and there are objects also contributing to the background. So in order to understand the signal that LISA will be detecting, we need to understand the nature and the characteristics of the ELM population. So hopefully I have shown that ELMs are important, and you should all be caring about it. And now I'm coming to the current status of this field of research. So on the observational side, we have about 150 objects known. A few of those have pulsar companions, and the ones that were discovered in the optical are mostly from SDSS, so they were selected as candidates from SDSS scholars and then followed up. So as a consequence, they are basically all in the northern hemisphere, and also because of the scholar selection, they have temperatures hotter than around 9,000 Kelvin, whereas the models predict that ELMs can cool down to about 5,000 Kelvin within a Hubble time. So I have this selection for hot objects in the known sample. From this known sample, the space density was estimated to be about 160 ELMs per kiloparsec cubic. As I said, binarity has been used as a criterion, and the periods of this observed sample are up to 36 hours because they were all basically closed binaries. On the theory side, we have a predicted density of 1,500 ELMs per kiloparsec cubic, so it's basically a factor of 10 difference. We also have theories saying that single ELMs are possible, and we also have theories saying that periods can be up to 100 days. So there is a very big difference between what we are observing and what theory is predicting. And there's only one thing that we are actually testing, which is the space density, and there's a factor of 10 difference there. These are the two things here. If single stars are possible and long periods, we are not really testing right now. So we might need better models because we have this big difference in the predicted density, so maybe we need to do some better population synthesis there. But as I am an observer, what I say in big red letters is that we definitely need more observations because we are not testing everything that theory is predicting. And whenever I talk to theorists about this, for example, about single ELMs, they tell me, you first find one, and then I'm going to try to do the model. So we have to first observe to convince the theorists to work, apparently. As I already mentioned, we had problems with this before Gaia because we could not really constrain radius based on the spectra alone. We could have a distant main sequence star or a nearby ELM. But now with Gaia, we have parallaxes. So we can constrain distance, and we can say this is a distant main sequence star or this is a nearby ELM. So here, for example, I'm showing a Gaia HR diagram. So this is absolute magnitude versus BP minus RP. In red is the Gaia 100 parsec sample, the one with very good parallax measurements and etc. In green, these green triangles are non-ELMs that were in Gaia. And in gray is a sample of SDA stars with good parallax. And what we see here is that given Gaia, we can say that most of these SDAs are up there in the main sequence. So they turned out to be mostly halo metal poor main sequence stars. These colored lines are 10 giga-year isochrones, so we can see that these SDAs seem to be consistent with the halo age, and they are more or less in the halo turnoff. And using a similar approach, drawing an HR diagram and looking at where the objects are, we can actually try to find new ELMs. And especially we can find new ELMs without any consideration about whether they are single or in binaries. So that's what I set off to do. The first thing I did was to see where the known sample is, so I can try to find objects in the same region. So this is the Gaia HR diagram again. Now the 100 parsec sample is in black. In gray is a sample with a similar selection to this 100 parsec sample, but is tending to 1 kiloparsec, so we have more objects. The known ELMs are shown here as colored symbols. The ones in red have bad parallaxes, so parallax is worse than 5 sigma. The ones in blue have good parallaxes. The symbol is a square when the mass is is lower than 0.3. And a triangle, like this one's down here, when the determined mass in the literature is higher than 0.3. So it would actually be a low mass star. And as you can see, they concentrate mostly in this area. So of course, higher than the canonical mass white dwarfs and below the main sequence. This line in gray here is an evolutionary model finishing on an ELM of a mass around 0.3, so the upper limiting mass I'm going to be using. So what I did was to do this color selection indicated by the dashed blue line. It excludes the canonical white dwarfs below it, the hot subdwarfs above it, and scattered main sequence stars to the red. I also applied the typical requirements on good astrometry, so including color assess and etc. I can discuss this more afterwards. And at first, I only requested the parallax to be better than 3 sigma. And that gave me about 100,000 objects. So what I did was to cross-match these objects with SDSS to see what kind of things I was recovering in this region. Here is that diagram again, and now the objects with SDSS spectra are shown as a color code. One, which is the dark blue down here, is an object that looks like a white dwarf, so it has very broad lines. 2 is a white dwarf with a main sequence companion, so a composite spectrum. 3 are spectra that show A-type, so hydrogen lines, not necessarily very broad. 4 are CVs. 5 are B-type stars, which are mostly up here. 6 are clearly F-type main sequence stars, or even K, so they have lots of metals, so I know they are definitely not white dwarfs. And 7 are quasars. So with a 3 sigma cut in parallax, this region here is very much contaminated by main sequence stars and even quasars. So what I did was to increase my selection to 5 sigma, and then this is mostly gone. I still have 4 quasars and a few F-type stars, but most of the contamination is gone. To eliminate the remaining F-type stars and quasars, I moved the red line to this solid blue line here instead of the dashed line. And I increased the selection now to 5 sigma, and in this region now there are about 11,000 objects. So with these filters, I eliminating contamination of objects with bad astrometry, but there are also objects that are in this region of the HR diagram. So for example, you might remember from Anna's talk yesterday that the CVs are also in that region. And also canonical mass white dwarfs with main sequence type companions are going to be in that region. So to separate these possible contaminants, I cross-match those objects with other photometric catalogs. Notice that now I'm saying separate and not exclude, because of course we spent yesterday the whole day talking about CVs, so I'm not just going to throw the CVs away. I'm just going to put them in another drawer. So here I'm showing a color diagram resulting from a cross-match with 2 mass and Ys. This is J minus W1 and W1 minus W2. In gray are all the objects in my sample that have these colors. In blue are the CVs identified from SDSS spectra. And in red, the composite white dwarf, so white dwarf and a main sequence star. And we can see that they concentrate redwards of this dashed line. So what I did was simply say, well, these ones go on the CV or composite white dwarf drawer, and these ones are the ELM candidates. I did a similar thing for other surveys. So here are, on the left side is J minus R versus R minus I, and the right-hand side is R minus I versus I minus Z for SDSS, PAN-STARRS, and SkyMapper. The color code is the same as before, so the red objects are the composite white dwarfs, in blue are the CVs. The CVs are more or less everywhere, but we can still separate the composite white dwarfs that are up here in a different region of this diagram. So again, the ones redwards of the dashed line, the ones blue of the dashed line are the ELM candidates, and the ones to the red are the CV or composite white dwarf candidates. So doing that separation, the result is a catalog of ELM candidates with a little less than 6,000 objects. This catalog is all sky. So here in blue are the known ELMs, and color-coded by parallax over error are the ELM candidates. So we can see that now we have a good coverage of the sky. This catalog should be very complete down to 16.5. Around this magnitude, the parallax is not better than 5 sigma anymore for most objects. And of course, the catalog is not very complete for dense regions because Gaia is not very good for dense regions. So I excluded any object that had another Gaia identification within 5 arcsec, because these ones can have bad parallax. And importantly, with this candidate list, I'm covering the whole range of temperature and masses predicted by the models. So I go down to temperatures of around 6,000 to 5,000 Kelvin, so much cooler than the ELMs that we know now. One of the first things I did was then to calculate, again, the local space density based on the fairly complete sample here. And the number I get is a bit higher than the one in the literature, which is now 300 ELM per kiloparsec cubic, but it's still 5 times lower than the theoretical estimate. So it seems that we really need to do something better with the models here. We still have this big discrepancy. I can still not say anything about if there are any single objects there, but this is one thing I want to do shortly. I have already 13 nights at INT and 4 nights at SOAR, so I will observe both the northern and the southern sample. Not only I want to confirm that these objects are indeed ELMs and not something else that ended up in this region, but I also want to probe the binarity and see if ELMs are really 100% binaries. And hopefully I want to compare this to better population synthesis models and see if we can solve this discrepancy in the space density. If anyone is interested in contributing to this observational effort or using the sample in your simulations, the full catalog is available here. This work is already published in multiple notices. And for the ones interested in CVs or composite objects, I also made available the catalog of the rest of the sample, let's say. And well, I'll just leave you here with the HR diagram of these candidates and take any questions. Thanks.
Okay, questions for Ingrid?
Would they all be helium white dwarfs, and how would you form them through a single star evolution?
So yes, they would be helium core white dwarfs, and the proposed mechanisms to form it are, it was right there at the beginning, sorry. So either high metallicity, causing a stronger wind and making mass loss more effective, or a substellar companion, removing the outer layers. A substellar companion, and then this would evaporate. But again, because they are observed as single doesn't mean that they were formed as single. So the other propositions is supernova stripping or a merger, yeah.
Or the wind could be that strong?
For larger masses, it seems that yes. So this was, in this region of masses, they observed single objects in a cluster with high metallicity, so that's what led to this proposition.
For the periods, I mean, the observations are that they're all sub 36 hours, and the theory predicts up to 100 days. Like, it's a great discrepancy. Could it be that we are biased towards larger periods in observations?
Towards shorter periods, yes, definitely. As I mentioned, it was basically a request to say this is an ELM that it was in a closed binary. Otherwise, it was hard to constrain the radius. Nobody has even tested for long periods. The only long period one known is that one in a self-lensing system that I showed at the beginning. Yeah.
Could you quickly go back to the last slide with the HR diagram?
Yes. Yeah.
So there's kind of clearly a gap between the things sitting above the white dwarf sequence, but then at the top left corner, is this then sub-dwarfs creeping in?
Yes, so there's a big overlap between my catalog and the sub-dwarf catalog, and also between the white dwarf catalog. So yeah, there can be hot sub-dwarfs here still, and I would also guess that they can even be canonical mass white dwarfs. So that's why I'm only calling them candidates for now.
We have time for more questions. Yeah.
When you say the theoretical models, do you mean population synthesis studies that reproduce the evolution to get these ELMs through the two channels that you showed before?
For the space density, it was a population synthesis model, but for example, that green model I show here is a mesa-evolutionary model by Alina Strate. Yeah.
One last question. No more questions? Then let's thank Ingrid again. Yes. Okay, then our last speaker in this session is Alejandra. She will be talking about magnetic braking and the formation of ELM white dwarfs.
Okay, thank you. I think this works. Good morning, everyone. Thank you for the opportunity of giving this talk. This is actually my first binary conference, so I'm new at the binary community. Not the white dwarf, but the binary community. So my name is Alejandra. I work at the University in Rio Grande do Sul, Brazil. And I'm going to talk a little about some results of the influence of different prescriptions of magnetic braking and the formation of ELM white dwarfs. This is a work that I'm doing in collaboration with Alina Strate from Radboud University in the Netherlands. So Ingrid already gave incredible introduction of what ELMs and low mass white dwarfs are, so I'm just going to go quickly here. So I'm a theorist, so this is my HI diagram. Here we have the logarithm of the surface gravity as a function of the effective temperature. So the larger the gravity, the larger the mass, and for white dwarfs, that means the smaller the radius. So luminosity basically is increasing this way. So this is an HI diagram. So here I'm comparing two samples in black circles. This is Ingrid's Catalogue that she published this year. I have here at the low mass range and low effective temperatures. And for comparison, we have here the orange cloud. This is a sample of around 13,000 canonical white dwarfs. That means that they have usually carbon-oxygen cores. This is a sample from SDSS, and I'm only considering hydrogen envelope objects. So as Ingrid said, we have an overlap between the ELM candidates, the confirmed ELMs in this case, and the what we call the canonical white dwarfs, especially here at log G7. So, as Ingrid pointed out also, one of the requirements to be classified as an ELM is that it has to be in a binary system with a short period, because that way we know that we cannot fit a main sequence star in the orbit and we need a smaller object. So I'm going to focus on those systems, the helium core white dwarfs that have a binary companion. And in that way, I can look at the period. This is the orbital period of the system as a function of the helium core white dwarfs. So here I'm going to mix a little low mass and extremely low mass objects. So in orange, again, is Ingrid's Catalogue. I included two more samples. The blue triangles are millisecond pulsar companions of the galactic field. I restricted the systems with period lower than 10 days. This is from Manchester et al. 2005. And I also included 10 objects in red squares that were analyzed in Lina's paper in 2014. I'm going to explain why those objects are there in a minute. So if I want to compute models, I will say, okay, most of the points seems to fall in that region, with a stellar mass between, I say, 0.15 to 0.25. Ingrid put a maximum ELM mass in 0.3. The uncertainties are usually pretty high, so I can restrict between 0.15 and 0.25. So if I want to study these objects in a mass-wise way, I want to compute models that give me these final masses. Just to start it, I can look at the other systems later. So because, again, Ingrid said, because these systems have lower masses, they cannot be formed by single stellar evolution in the age of the universe. So we need these binary companions and we need binary evolution. So just to clarify here, I included two evolutionary models in my HI diagram. Here we have a very simple 0.6 solar mass evolutionary model that goes basically through the middle of the canonical white dwarf distribution. You can trust me on that. And in red, we have a model from Istrate et al. 2016. This model ended up in a helium core white dwarf with basically 0.21 solar masses. So as you can see, the behavior of the models is quite different when you have binary evolution and when you have low mass and extremely low mass white dwarfs. We have all this looping in the HI diagram due to residual burning of hydrogen at the bottom of the hydrogen envelope. That leads the star to a giant configuration and then go back and forth. But apparently these loopings are quite necessary to cover the region where we observe the helium core white dwarf. So this is going to be important. So in 2014, Alina, in her PhD thesis, she computed a grid of ELMs. Actually, the focus was not study ELMs, but millisecond pulsar systems with extremely low mass companions. They have helium core white dwarf companions below 0.2 solar masses. And these systems are the red systems that I showed in the plot before. These systems in particular have periods of below 15 hours, but she was interested in a subgroup of those with periods between 2 and 9 hours. So the objective of the work was actually reproduce these systems here. So she used for the loss of angular momentum, the typical components, mass loss, gravitational wave radiation, and in particular magnetic braking. So as I learned in the last few months, this is the canonical magnetic braking formula from Rappaport et al. 1983. And the result that she had is that in order to reproduce these systems with a very low mass and a short period, the initial period has to be fine-tuned. So the initial period they got was were between 3.39 and 3.43 days. If you compute the difference between those, that gives 57 minutes. So in order to give these systems to actually produce helium core white dwarfs with masses below 0.2 solar masses, you need to fine-tune the period in a matter of minutes, which is a problem, and that's why it's called the fine-tuning problem. So this is a plot from Alina's paper. This is final period as a function of initial period. This is the bifurcation period, so everything that way is a divergent system, and everything this way from the bifurcation period here are convergent systems. So in particular, she separated the convergent systems into convergent, that are basically non-detached systems. So this region here is not forming helium core white dwarfs. Probably the donor star will be completely accreted, or maybe they will merge. So those are not the systems we are interested to. And the intermediate systems are detached systems with, in particular, periods above 9 hours. So the region of interest for them was basically this line here. So, of course, this fine-tuning was not real. It actually gave, it was compared to observations, and in this region, the number of objects that should be observed was a factor of, was the ones predicted by the theory was like an order of magnitude below the ones that were observed. So obviously, this is not physically accurate. So we use this to see if we can solve this problem. And last year, Van and collaborators, they proposed a new prescription of magnetic braking. They actually don't care about helium core white dwarfs, at least in this paper, but they want to study the low mass, the intermediate and low mass X-ray binary population, okay, because the population system synthesis wasn't working. They found that the canonical magnetic braking gave mass transfer rates that were an order of magnitude too weak to explain the population of these systems, so it's basically the same problem. And they say that this was not adequate for population system and evolutionary computations. So they used this new prescription, and they actually kind of solved the problems, not all, as always, but they could reproduce the persistent low mass X-ray binaries, and they actually found some improvement in reproducing transient systems. So this was their motivation and their results. So we think, okay, if this prescription solved their problem, maybe it can solve ours. So we tried this to form helium core white dwarfs. So basically, they consider 4 prescriptions in one. The default one is Schumann's law, so the canonical magnetic braking with magnetic index 4. The second one, they introduce a correction that's called convective boosted that is related to the convective turnover time, sorry. This is related to a correction of the magnetic field due to convection. The third case they call intermediate, so they also scale the magnetic braking linearly with the wind mass loss. And the last one is called wind boosted, that basically considers all the corrections. And this is basically wind mass loss boosted by rotation. So what they found is that this last one was too strong. Apparently, every part of the correction was working well, was within the default values. But when you put everything together, it gives a mass transfer of one solar mass per year, which is too high. So they say this is not working. Something is happening. They said that maybe with high rotation rates, you should include some structure in the magnetic field, and this structure, this additional structure, will dampen the mass transfer, and then you get something that is physically accurate. So following their recommendation, we study, as a first step, these three cases. Okay? So first step, we computed a grid of models using MESA evolutionary code. We start with a donor mass of 1.1 solar mass in the main sequence, and the accretor is a bond-like source, neutron star-like 1.4 solar mass. And we explore a range of periods between very short, 1.52 days, to 120 days. So we also extended the sample for the long periods that will give us low mass white dwarfs. So this is some physics. There's a lot of physics involved when you compute an evolutionary track, a lot of free parameters. But for rotation, we assume that the rotation period of the donor is synchronized with the orbital period since the beginning of the computations. We use a wind prescription that is basically Raymer's law with an eta parameter equal to 1. In this case, we didn't include diffusion in our computations because it's very computationally expensive, like 5 times more expensive in time. And what we wanted to see was the orbital evolution, basically the relation between the initial period and the final period. So we didn't think that it was necessary to include diffusion at this first step. Of course, we are going to include diffusion later. So the first result is, this is again final period as a function of the initial period. These circles are the default case, the stars are convective boosted, and the triangles are the intermediate case. So in this range here, this is the period that was of interest in ISTRATE 2014. So this will say between 2 and 9 hours. And it says, so for the intermediate case, I can take off the almost. We no longer need fine-tuning. We can produce these systems with these final periods, with initial periods between 5 and 6 days. So now the difference, the period range, is of an order of a day. So we went from a fine-tuning of minutes to a non-fine-tuning of a day. But this is not what we were interested in. We're interested in forming helium core white dwarfs, but this was a good thing. For the convection boosted, we still need some fine-tuning at the lower periods, so that's why it says almost. So as I said, we are interested in forming helium core extremely low mass white dwarfs. So here we have the initial period as a function of the final mass of the helium core white dwarfs. So again, this is intermediate, convection boosted, and default. For the default case, I have to make a comment here. For the default case, we do get some points for lower masses, but you need to fine-tune that. And that's exactly what we didn't want to do. We didn't want to do fine-tuning. So first, for the high mass range, this is 0.4, so this is a high mass range. we see that all the prescriptions kind of converge to the same behavior. That's something that is expected because these are long periods, long initial periods, 100 days. So we expect that with large separations, the effect of magnetic braking is not that strong, and in particular, the corrections to the magnetic braking are not going to be important. So this is a good thing. And if we say, okay, but I still want you to compute a model of with an ELM resulting in 0.15 to 0.20 solar masses, what you got? Okay, we got these two models here. We can produce those systems for the case of convective boosted with initial periods between 2 and 6 days, and in the case of intermediate magnetic braking, we get a range between 5 and 10 days. So it's a range of days. Of course, we can change the mass of the accretor and the initial mass and change a little this, but we don't longer need a fine-tuning of minutes to produce extremely low mass white dwarfs systems. We get those from a wider range of initial periods, which is what is important. I'm just going to skip this one. And another thing that I would like to show you is the orbital evolution. In each case, so this is the orbital period of the system. And the age, we computed models until to the Hubble time, of course, because we want to see these systems. And this is for the default case. And the color-coded is the final stellar mass of the white dwarfs. So blue is basically 0.4, and red is 0.15. Okay? So this is the default case, the one that's supposed that is not working. The black circles is when the mass transfer starts, and the red stars is the moment when mass transfer ends. So here what we got is, I don't know if you can see the colors here, but these are the systems that are closer to a lower mass, 0.15, which are actually our range of interest. You see that we don't have too much models in that mass range because we didn't fine-tune in the order of minutes. Also, for one thing that when we got from the computations is that for the lowest period, these gray lines, we get non-detached systems. So these systems are not going to detach and are not going to form helium white dwarfs. If we go to the convection boosted, we have a better coverage of the low mass range. We still have some non-detached systems in the low period range, not as many, but still there. And finally, the intermediate case. Again, we get some lower masses, lower final masses in the same period range. But in this case, for the lower periods, like this one and this one, theoretically, these are detached systems. This is actually a neutron star and a helium core white dwarf, but they look a little weird. So we are not really trusting these results. We believe that the intermediate case for these particular systems is not physically accurate, so we need to look into this a little more. And finally, I would like to show you some HI diagrams because I think they look pretty. And this is the default case. Again, the black circles is where the mass transfer starts when the star is in a giant configuration, and the red stars is when the mass transfer ends. This is the default case. We do have a lot of above 0.3 solar mass results. We do not get a good coverage of this region, and this is important because that's where the observed ELMs are. So with this prescription, we don't get a good coverage. We do get some looping solutions there. So loops are funny because they appear like in a middle range of masses. So for, I will say, 0.2 to 0.3, 0.35, maybe you get a loop. This will change with metallicity, and of course it will change if you add diffusion. So this is like an intermediate mass effect. If we go to convection boosted, we get a better coverage of this region here, where we find the observed helium core white dwarfs, the extremely low mass white dwarfs, sorry. And finally, for the intermediate, again, we get these weird tracks here for the lower periods, but we still get a nice coverage of mass in the low temperature range. Okay, so these are some conclusions that we got. No fine-tuning required in mass. Basically, we can produce these helium core white dwarfs in a range of, I will say, 0.15 to 0.25 solar masses. We don't need to fine-tune the initial period in an order of minutes. We actually have a range of days, and that means that these helium white dwarfs will be kind of easier to produce, so you get these systems with a wider range in initial periods. And we actually think that this could be important for population synthesis, but because that will increase the number of helium core white dwarfs in this mass range that you get, at least you get from the models. So we hope that this will help, and you trust us. So as I mentioned at the beginning of the talk, this is an ongoing work that we're doing with Alina. So the next steps are maybe considering the wind boosted case, because with these prescriptions of magnetic braking, we are not able to produce helium core white dwarfs with masses below 0.15. There are some objects that have lower masses, so we don't know if this Roche-Lowe channel is adequate, if we need another one, if we can do this with a different prescription of magnetic braking. And the next step forward is to change the equator mass to include the carbon-oxygen white dwarf systems that Ingrid mentioned. So this will take us out from the main sequence, the millisecond pulsar companions to a carbon-oxygen or maybe an oxygen-neon companion. So thank you.
Questions for Alejandra?
From what Ingrid was saying, there are already too many ELMs in the population synthesis models compared to observations. So is it good to potentially increase the number?
To increase the number, I don't know. So we are, yeah.
I think what Alejandra maybe means is that increase the number of low mass objects. So the models are currently only making objects down to 0.14 solar masses, and we have a few that seem to be even lower mass than that. So to produce then we need something else that might be what they're doing now.
Hi. Am I correct in thinking that your stars are actually spinning down more rapidly than Schumann-Hitch laws predict?
Yes.
Because that's not something that we see any examples of in isolated stars. I wondered if you could think of any kind of physical mechanism why stars in binary should spin down faster than single stars would do.
I think that the additional effects that Van and collaborators are considering, like considering the interaction between a first correction to the interaction between the magnetic field and the convection, could do the trick. I think we are adding some physics, like first order correction of physics from a simple, I believe it's a simple law. So we are expecting some changes. In particular, we are expecting that they spin down rapidly. We actually forming more tighter systems, so the periods are being reduced, again because the angular momentum is being lost more efficiently. This is a preliminary work. We have a lot of work to do from here forward with the population synthesis, and also to see if we can reproduce the mass and the period of the systems at the same time, because at this point we are only worrying about producing low mass, extremely low mass helium white dwarfs, but we have to look for the periods of these systems also.
Okay, I think it's time to go to the coffee break. And let's thank Alejandra again.
So now my time starts now, right? All right. Thank you for giving me this opportunity, Graphic and other organizer. I am, okay, I have the pointer. Okay, I am Banibrata Mukhopadhyay, working in Indian Institute of Science, which is located at Bangalore, one of the biggest institute in the country, India, and oldest too. Okay. So, title is Gravitational Waves from White Dwarf Sources. Primarily, I will concentrate in this talk plausible continuous gravitational wave, though I'll touch upon also binary systems too. So talk will be mostly based on some of the papers I have been writing with my students and collaborators since last few years, though the list is not exhaustive. So let me begin with the plan of the talk. So I'm talking about gravitational wave and continuous gravitational wave. That means required ingredients must have been established to be there in the white dwarf. That means I have to show field is strong enough, it should have rotation, and they must have, axis must have been misaligned. So first I'll plan to establish them in white dwarf premise. So question may arise immediately, whether adequate magnetic field, strong field is possible in those white dwarfs, and as well as rotation. Many ways it can be explained, at least plausibility can be explored. One of the ways is accretion. I'll give a very simple sketch by which one can argue by accretion, high field and high rotation is possible. Then once we are satisfied with this idea that highly magnetized rotating white dwarfs are possible, we'll go for rigorous model of white dwarf by GRMSD numerical simulation. And then we are all set for gravitational wave emission exploration. I'll also compare the energies from gravitational wave as well as electromagnetic or spin down emissions. I'll compare. Luminosity is UV luminosity is very important aspect that I'll touch upon. And finally, I'll summarize with conclusion. All right, the main idea. So for this community, first point is not at all new. Since last 10-15 years, at least a dozen evidences are for peculiar type 1a supernovae. Peculiarities lie with, first of all, their light curves. They don't really follow Phillips' law. And then there are oval luminosities, and finally, low ejecta velocity. And many people argue they to be super Chandrasekhar progenitor white dwarfs. Even in the Nature paper of Andy Howell, he went even up to arguing 2.8 solar mass. Either that Nature paper or follow-up paper. And since last half a decade or so, we have been enlightening this issue by exploring high magnetic field, plausible highly magnetized white dwarfs, we call B white dwarf. And we showed that eventually leads to the super Chandrasekhar white dwarf and altogether new mass limit. Of course, there are other consequences of, apart from this explaining oval luminous type 1a supernovae, white dwarf pulsars, gravitational radiation, which is the present talk. And that immediately brings super Chandrasekhar white dwarf in the limelight. You might have noticed, many groups have been working in this field in different aspects, not necessarily magnetic field. That was our idea. People later on were motivated, looked for modified gravity effect. Though in white dwarf, GR effect is not important, but some of the groups showed that at the high density central region, GR effect and modified GR effect is important. Then argument was matter encounters non-commutative physics. That is more of quantum mechanical argument. Then ungravity effect. Also partly quantum, partly classical idea. And then people argued that white dwarf may have net charge, not really neutral in charge. That also could produce super Chandrasekhar white dwarf and many variant magnetic fields. So all of them leading to modified mass radius relation. Okay, not all of them are looking into mass radius relation. They more looked into the just massive white dwarf, super Chandrasekhar white dwarf. Some of them went ahead and exploring mass radius relation too. And most of the cases it was found that they are deviating from Chandrasekhar's mass radius relation. But question remains, there is no direct evidence. Where are they? If they are there, theory predicts where are they. So quickly recapitulate, highly oval luminous peculiar type 1 supernovae, nickel mass if I plot as a function of bolometric luminosity, I'm just borrowing Howell's plot. Black curves, black points are perfectly in accordance with conventional theory, but 3 points here are clearly overshooting Khokolov's pure detonation limit, and they are the peculiar candidates. Argument is that high luminosity for them is proportional to two terms. One is rest mass energy, and that is the kinetic energy of the ejecta. And for all of them, this is to be low. So any high luminosity has to come from here. And also, as I said, they don't really follow this typical Phillips law peak versus stretch relation. They are having high peak and first declining rate. So that basically started igniting idea of proposing alternate ways, plausible violation of Chandrasekhar limit, maybe. All right. With this, in this talk, as I said, I'll look at the highly magnetized white dwarf counterparts and how that can help. And final aim is to understand gravitational wave, whether gravitational wave astronomy can help detecting them, as because they don't have direct evidence yet. Well, as I said, first I have to establish at all strong field which is required for gravitational wave emission, possible to be there in those sources. So one of the very simplistic sketch I'll touch upon here. Idea is that, okay, again, it is not very uncommon these days that surface field could be 10 to the power 9 Gauss. And if they are following kind of dipole-like structure field, a central field could be 3 order of magnitude higher maybe. So let's consider white dwarf having surface field 10 to the power 9 Gauss. Idea is that, which is sitting here, component is supplying mass continuously. By forming a disk-like structure, it reaches here, so white dwarf gains mass. As it gains mass, it becomes more gravitating, gravitational power increases. It tries to shrink the size, and from magnetic flux freezing, if it is to be assumed perfectly conserved, decreasing radius will give increasing magnetic field. And that way it will create extra outward magnetic pressure. As a result, in the mass radius curve, where it will reach here, for example, and which is about to get bursted, exploded, what will happen, extra magnetic field will halt the exploration. It might also change certain threshold nuclear burning energy density, and it will deviate from this curve to that curve. That is a proposition. And so up to this, we cannot distinguish magnetic and non-magnetic white dwarfs. And here it will be deviated, and altogether it will take different path. And white dwarf, due to strong magnetic field, will turn out to be non-spherical. And and this continuous mass streaming with the flux freezing will keep pumping field and shrinking the size. And that way, this curve will be deviated. And that philosophy can be implemented by simple set of equations. Again, I am neglecting for this purpose all the important and complicated CV physics. So in the accretion phase, what I just explained, 3 conservation laws are considered: linear momentum, angular momentum, and magnetic flux. And as a result, mass is increased, and also in a plot in a few minutes. And it is assumed that at some point field becomes very strong. So white dwarf is here. Maybe it has multipolar magnetic moments, and field lines will be extended all the way in the outward direction. What will happen? Strong field will stop any further accretion. It will go to the spin power phase, pulsar phase, and suppose it is following this kind of law, rate of change of angular velocity is a function of angular velocity to the power n. N is equal to 3 is dipole. We consider general kind of relation, and at that stage, so this is a dipole approximation. We know omega dot is equal to omega to the power 3 if I substitute. But if I deviate, just for generality, I just consider n not equal to 3. As a result, what we find, so angular velocity and magnetic field at the surface, first, following the set of 3 conservation laws, accretion phase, changing, field increases. At that stage, I argue magnetic field has become very strong, accretion momentarily stops, it becomes spin power pulsar like white dwarf, and this is the angular velocity, and it starts emitting out of its magnetic field and angular velocity. So angular velocity decreases, field decreases. Again, when field significantly has been decreased, again it has gone to the accretion phase, and again angular velocity and field increases, and this being repeated as I tried to schematically told at the beginning. And in the end, it turns out to be very highly magnetized surface white dwarf, about 10 to the power 11 Gauss. Surface field is 10 to the power 11 Gauss. Angular velocity also turned out to be non-insignificant, quite high value. And entire process is done by the lifetime of our universe, mass as a function of time in ER. So I am just trying to put the point that in simplistic physics, it is possible that starting with conventional Chandrasekhar's mass radius relation by magnetic field, which was initially dormant, at some point due to flux freezing that will become stronger, and you can have magnetized rotating white dwarf. All right, now I think in some extent with simplistic physics, I am able to convince that highly magnetized, by high magnetic field I mean surface field 10 to the power 10 to 11 Gauss, starting from 10 to the power 9 Gauss white dwarf at the surface, one can obtain white dwarf of high magnetic field and high rotation. Actually also eventually I don't require 10 to the power 11 Gauss surface field either, 10 to the power 9 Gauss will be enough. With this plausibility of white dwarf, we'll go for numerical simulation. So as field is very strong, white dwarf no longer will remain spherical symmetric. So it could be prolate or oblate spheroid depending on the field geometry. If it is toroidally dominated, it will be prolate spheroid. If it is poloidally dominated, then it will be oblate spheroid. With that, we'll go for simulation. We'll primarily consider publicly available code, which is mostly considered for neutron star, XNS code and Lorentz code. We appropriately modified the codes for white dwarf, and then we explore the GRMSD simulation with this modified code. So first set of result, here I consider toroidally dominated magnetic field in the white dwarf. Just before I proceed with this slide, let me remind you again that purely polyidal, purely toroidal, none of them, long known since 1973, is not stable configuration. You should have suitable mixed field configuration. So I'm not looking at the stability criteria at all. I'm just trying to understand magnitude-wise if field can shape the change and gravitational radiation could be possible to be produced. So this is first of all toroidally dominated case. Rotation is also there, and here rotation rate is very small. Mostly it is magnetic field effect, and central region you see it is prolate. Overall it is a kind of spherical shape. Now rotation rate increases about 50 times, and you see it is now overall oblate shape because central region is having strong field, but away from the central region field decreases, but angular velocity is uniform rotation remains intact, so it is trying to disperse the matter. So as a result it is becoming oblate spheroid, and this is the field geometry at the central region. We have simulated about 10 to the power 14 Gauss from the color code. You can easily find out. Surface could be as low as 10 to the power 9 Gauss actually. If I just explode at all, if possibility is there, differential rotating case, then you see polar hollow-like structure. So this structure comes because rotation rate here decreases from central to surface, but magnetic field decrease rate is not that strong. As a result, when rotational rate decreases, magnetic field dominates. Away from the central region, it becomes prolate. So, all right. And very importantly, magnetic to gravitational energy ratio as well as kinetic gravitational energy ratios are all the cases in accordance with Breedt limit, for example. Like in this range, actually quite well below 0.1 in all those cases. So they are stable actually. They are in the equilibrium and stable equilibrium. And mass could be actually 2.5 solar mass. Of course, that is for the differential rotation. Otherwise, it is if it's a uniform rotation up to 2 solar mass. This is the story for polyidally dominated case. Previous one was toroidally dominated, as I said. Here, magnetic field and rotation, both the effects are acting in the same direction, trying to make the star oblate spheroid. And you see the shape, again deviating from spherical symmetry. Here, of course, mass is less, depending on the magnetic field, 0.4 to 1.7 solar mass. Again, this is the ratio of magnetic to gravitational energy. And this is the differential rotating case. In this case, mass is ranging 1.4 to 1.7 solar mass. Again, satisfying magnetic to gravitational energy ratio following this paper. Central field in either of the cases about 10 to the power 14 Gauss. Surface field here slightly higher. Previous case 10 to the power 9 Gauss, here about 10 to the power 10 Gauss surface field. And central density is about 10 to the power 10 gram per cc. So I have not considered in 9 of the cases exotic central density. All are known, quite conventional central density and magnetic field at the surface. Only I had introduced as special ingredient surface to central, there is a field gradient, and that we are able to simulate by those XNS and Lorentz code. Independently we checked actually. So equilibrium sequence, mass as a function of magnetic field. This is toroidal dominated case, and this is polyidally dominated case. Toroidal case keeps increasing mass, but we have stable equilibrium condition to about 2.5. There's a restriction, and polar to equatorial radius ratio is also changing depending on the geometry, toroidal and polyidal. And so, as I said, it is very important to remember, in reality, results would be in between polyidally and toroidally dominated cases. And this could be a typical shape I already showed. Now, I hope we are all set in exploring gravitational wave emission from these triaxial magnetized rotating white dwarfs. Only information I still have to introduce is that rotation and magnetic axis to be misaligned. And interestingly, importantly rather, neither XNS nor Lorentz codes are able to capture this misalignment. That information is not there. To facilitate, in order to facilitating using that result, mass and radius, moment of inertia per se, for our analysis, I hypothesize this angle to be very small, such that angle does not have important effect when I have been simulating mass and radius from XNS or Lorentz codes. So the small angle approximation is to be has been considered in this case. And these are two polarization, you all know. This is the amplitude, and small chi is making actually H plus H cross 2 order of magnitude smaller than roughly compared to H naught. And so basically I have to supply ellipsoidal ellipticity, which we understand from the simulation I had already shown. Moment of inertia coming from mass and radius, distance, angular velocity, all are available in the simulation. Now, strain rate as a function of frequency. So they are plotted, and corresponding gravitational wave emission from those white dwarfs are plotted along with sensitivity curves. Lisa, Alia, 1 year Lisa, and so on. It is shown that, first of all, let's concentrate on these points, which are continuous gravitational wave sources from white dwarf. And none of them comes close to even Lisa curve. But interestingly, 1 year Lisa could be able to capture some of them. Also, there are some confusion noise, but some of them are beyond the range of confusion noise, though they should be able to be detected if mission appropriately by Lisa, or more appropriately 1 year Lisa investigation. I also plotted here binary cases. We all know that corresponding gravitational wave strain is basically written in this form if I know the period, distance, and chirp mass, and the components having mass 0.5 to 2 solar mass. If I assume inclination angle to be 0, if I substitute, turns out that in different range of frequency compared to the frequency range we have simulated for our white dwarf, this gravitational wave strain rate arises, and they are not at all mixed up, confused with the continuous gravitational wave, which are being detected by 1 year Lisa, but these are seeming to be detectable by even E-Lisa or Lisa, binary ones. This is the ellipticity rather of this. So it seems that highly magnetized rotating white dwarf, which you are able to simulate, and why high magnetic field and rotation would be there, I think I have conveyed in some extent. By simple toy model, those white dwarfs would be able to produce gravitational wave, and which could be detected by this 1 year Lisa curve, avoiding even confusion noise. Even if there is a confusion noise, the way to distinguish actually them out of confusion noise too. That's a different story I can discuss later. All right. So just for completeness, which is more talked source, neutron star, if I consider them to be about 10 kiloparsec away, we also just recapitulated the strain rate, and we found that none of them, as we know, have been detected by LIGO, but advanced LIGO may be detecting them, and if they are being detected by advanced LIGO, argument is that we can argue that those neutron stars' interior field can be interpreted. Interestingly, those white dwarf sources, as I showed, also are interesting sources for spin down luminosity, and so they have, spin down counterpart if they are being observed by gravitational wave detector with 10 to the power 46 arcs per second luminosity, they should have counterpart of electromagnetism, 10 to the power 34. So both together can be probed, and with more confidence one can argue them to be in the universe. In the very last 5 minutes, so still, before we try to detect in the gravitational wave, what about the luminosity? Where are they? It is related to the question, where are they? Are they low luminous, high luminous? If they are high luminous, why we are not able to detect directly? That actually I have been just doing my draft is with my friend collaborator Chris Stout. I am expecting to receive his input and correction, but yeah, he's busy. So he said he maybe will get back to me over the weekend. Anyhow, so here we are trying to look at the luminosity by modeling, again, hydrostatic balance, photon diffusion equation, and mass conservation equation. And this is the new addition, just to capture any temperature gradient effect is there in the white dwarf. And first, I assume temperature is varying throughout the white dwarf. And this is the curve, last one is the curve, according to Chandrasekhar, having no photon diffusion equation. If I introduce this, you would see the curve shifts in the outward direction. Seems unphysical because we know without magnetic field, just introduction of photon diffusion equation should not have super Chandrasekhar mass. That means temperature should not be varying throughout, which is giving us benchmarking. So, like conventional stuff, we go back and DTDR assumed to be 0 in the core. By core, I define here that, that basically envelope is the region when ideal gas pressure is dominating the degenerate gas pressure. I don't know why it is being so faint. This deviation comes here. So here to there, temperature gradient is 0, and here variation is there. And keeping that in mind, introducing that extra boundary condition, we found that all the curves, even if you have photon diffusion equation, are obeying Chandrasekhar limit, except the low radius, high radius, low mass region, deviation is there, and that was again known, even Jorge Rueda, Remo Ruffini, they showed even by final temperature equation of state, large radius white dwarfs are deviating from Chandrasekhar's equation of state, but they all obey Chandrasekhar's limit. But important point is that magnetized cases, even if you introduce this condition, core isothermal, which is the case, and this envelope diffusion equation is there, you see still deviation, and you get super Chandrasekhar like mass radius curve. And now if I just go for energy conservation, hypothesis suppose is that I introduce magnetic effect and corresponding magnetic energy at the expense of thermal energy. If this is the hypothesis, so the total energy is conserved, then for this curve, for example, I'll keep decreasing luminosity as if field effect is introduced by at the expense of thermal effect, and we see that keeping the super Chandrasekhar deviation or mass oscillation pattern intact, I can go the luminosity all the way up to very small value, 10 to the power minus 20 arcs per second. UV luminosity, I mean to say basically. So that tells that massive super Chandrasekhar white dwarfs presumably are exhibiting very low luminosity. If they are not having photon diffusion counterpart, their mass is about 1.38 solar mass. If you introduce photon diffusion equation in the envelope, not in the core, again I am reminding, it is about 1.9 solar mass. So take home message here is that highly magnetized white dwarfs producing perhaps gravitational wave could be lowly luminous. All right, I am done. So I'll summarize here. So plausible existence of highly magnetized rotating stable white dwarfs have a variety of implications, including enigmatic peculiar type 1a supernovae. That was my initial motivation when we started looking at the issue 6 years back, actually 7 years back. New generic mass limit of white dwarf seems to be more than 2 solar mass, could be 2.6 solar mass. Higher are good, it could be 2.8. Maybe rotation rate is important. They are triaxial and determined by their stable equilibrium conditions. In gravitational wave search, they should be considered seriously. The alone and binary systems could be good candidates for LISA, but also for Einstein telescope and futuristic DESIGO and BBO missions. Their UV luminosities are expected to be quite low, hence seems to be hidden from detection, but spin down luminosities are detectable. Hence gravitational wave astronomy should play a big role to detect them if planned to probe appropriately. Thanks.
So, are there any questions? Yeah. Is this working?
The lowest B field is 10 to the 9. So these are polars. So maybe people here can help me understand if there's a polar above that. We should have seen it by now.
So question is, first of all, I'm extremely excited by hearing Gagik's talk yesterday. He argues it is looking like polar, but it cannot be avoided. It may have accretion also. Second point is that 10 to the power 9 is just proxy. You can, in principle, easily simulate. Basically, you can easily look at our MNRS paper 5 years back. There are series of plots are given, and actually my plot here also, this case also, actually surface field is not 10 to the power 9, it could be quite low, 10 to the power 8 Gauss. And only hypothesis here, and that is working here, is that even if surface field is 10 to the power 8 Gauss, for example, if you don't like 9 Gauss, field profile is such that central field is 10 to the power 14 Gauss. If that is not realistic, then I have nothing to answer. But numerical simulation proves this is possible, and our hope is that, as you know, I am sure, Eugene Parker's famous book, 1972, he said that no one can rule out central field of sun 10 to the power 7 Gauss, and same sun-like star presumably is collapsing to give rise to white dwarf, and our 2013 observator, by that simulation, that work, I showed that that 10 to the power 7 Gauss central field and 1 Gauss surface field of sun, if it is collapsing to a white dwarf, this is possible. Central field 10 to the power 14 Gauss and surface field 10 to the power 8 Gauss.
Yes. So another question. He was first.
What would be the spin-down timescale for the gravitational wave emission from these white dwarfs?
Spin-down timescale due to gravitational wave emission?
Yes.
That I computed. So basically your question is, suppose spinning down is due to gravitational wave only. Yeah, I computed by, I don't remember. I remember the plot is with spin down due to its own magnetic and I can tell you by looking at my paper. It is 3 years back, I forgot. That's a good point. Actually, something similar computed by Manuel Manero, again Ruffini and Rueda 5 years back, I think, following Patinsky's original idea, and they are trying to explain that time SGR and AXP by highly ionized white dwarf. Ours was something similar, but I don't remember.
Yeah, I had a slightly similar question because you have gravitational wave luminosity of 10 to the 46, I think you said. So I just roughly estimated a spin down time scale around 100 seconds. Is that what are you expecting these to be longer lived than that? That's a very high luminosity.
I found actually not 100 seconds.
Well, can you just give a rough idea?
At least it should be year. I can.
Are you assuming that it's still accreting at that point? That's why.
No. Okay. So my point is that at some point when they are the candidate for gravitational wave emission, now accretion has been already stopped. Initially, accretion was bringing its low magnetized, low rotation phase to the phase I am talking about. Now accretion is not at all.
Okay. Yeah. So the 10 to the 46 really sounds very high to me. I mean, I've estimated for AR SCO that has a 5 million year time scale around 10 to the 34. So it's 10 to the 12 times higher than that. It's more massive, but it's much smaller, so it has less moment of inertia. It's higher rotation rate, but even so, I think you're going to be struggling to make that last very long at that rate.
I'm sorry, I'll look at it. Definitely, gravitational energy release rate is the one I have given correct. Spin down, I'll come back to you. For both of you, spin down rate.
Okay, we have to move on to the next speaker now.
So I'm going to talk about double degenerates in general, and the first two parts of the talk will be about formation and characteristics of these kind of systems, which is going to be more of a summary, kind of a wide overview of our current knowledge, and then we will go to the end of the double white dwarf mergers, and I will focus specifically on type 1a supernova progenitors and mergers, and related to a few of the works I have done through the last few years. I would like to also to mention that 2 months ago there was a conference on double degenerates, and a few of the things I'm going to show here are taken from slides that were shown there. So double degenerate implies that we have two white dwarfs. That is the definition of a double degenerate, and we can have two different kinds of double degenerates. Those that are white systems, like for example, this is represented here. This is a Sloan SDSS image of actually a triple system. So this is actually not a binary, but a triple system, which we found to be the first triple resolved white dwarf binary. This is a real image, and because the white dwarfs are actually quite widely separated, we know that these systems didn't go through any mass transfer interactions. These systems are very important, for example, to constrain initial to final mass relations, because the cooling times of the white dwarfs is the same as the main sequence progenitor lifetimes. But this is a closed binary conference, so we are going to focus most on this kind of systems, which obviously this is a representation because these are unresolved binaries, right? And this is the white dwarf in a planetary nebula, I think it was, yes. That is supposed to be a Taiwan progenitor. So from now on, double white dwarfs are going to be those here. Let's talk a bit about the formation. This cartoon here shows the standard scenario of how you form two white dwarfs in a closed binary orbit. So at the beginning, you start with the main sequence binary. One of the more massive, the more massive star actually evolves out of the main sequence and becomes a giant, no? And then the mass transfer is dynamically unstable and you form a common envelope phase. There's friction within this common envelope, there's energy transferred, angular momentum transferred, and in the end, the two stars, or the giant core and the main sequence companion, shrink towards each other, and then because of the shrinkage of the orbit, this energy angular momentum are actually used to expel the envelope, where you have finally a white dwarf with either a helium core or carbon-oxygen core white dwarf, and the main sequence companion. The main sequence companion is basically an altered 3D evolution because it didn't manage to accrete the informed material. And then you have a different kind of possibilities. We are going to focus on this one here, where we have the secondary star evolving, forming a second common envelope phase. It's more or less the same story here. In the end, what you have is a two double white dwarf binary, which we call double degenerate, with either carbon, oxygen, helium cores, either of them. And then from then on, we will go to the final stages of this evolution, which either can be a wide variety of systems. So let's focus on this formation. Is this scenario actually correct? So let's go to the angular, to the common envelope prescriptions that tell us how this evolutionary phase works, because it's actually not very well understood. We were talking about the shrinkage of the orbit. This is actually not real representation because the core of the giant star is actually moving also. This will be more like a black hole binary. But anyway, from several decades ago, there is this alpha common envelope formalism that is telling us basically when you shrink the orbit, you have release of orbital energy, which is used to expel this common envelope, and this is basically what you have here. The binding energy of the envelope, it has to be equal or to some fraction of the difference in gravitational energy, which is given by this alpha. This lambda factor is taking into account the structure of the red giant donor, which this is the red giant's donor, this is the mass of the donor, this is the mass of the envelope, and so on. This is the final separation, initial separation, mass of the accretor. And because we have observations of double degenerates where we can measure masses and orbital periods, then you can reconstruct the evolution and get all the possible progenitors that form the systems and get this kind of alpha parameters. No? Apparently, what happened is if you do this, then there were several works that didn't find a good prescription for the first phase of common envelope evolution, because what they found is that basically the binary was shrinking too much. So for the first phase of common envelope, what they found is that these alpha values, alpha lambda values were actually negative, which doesn't make any sense, or they were actually too high. Take into account that these values should be between 0 and 1 for the energy balance. So this made especially Higgs elements to propose a second formalism, which is called gamma common envelope phase, which is given here. And instead of the energy balance, it's actually considering the angular momentum balance. So you have an angular momentum lost from the system divided by the initial angular momentum lost, which is going to be equal to the difference in mass. No? We see that the common envelope implies that there is some kind of mass loss. So this has to be related to the angular momentum loss through a parameter which is called gamma. By adopting this formalism, they found out that they could reproduce actually quite well with values of compiled through this 175 of gamma, they could actually reproduce the evolution of these double degenerate systems. So it was quite successful prescription. However, later on, Webbing showed that this was actually not surprising to find this concentration of systems at this value, because there was actually the one that this prescription will give the physically possible. Also, if you look at post-common envelope binaries where you have a white dwarf and a mean sequence star, the gamma prescription actually doesn't work very well. And the alpha prescription does work pretty well. So actually we don't know which prescription is actually the correct one. There is another possibility, which is suggested by Woods et al. In 2012, that the first phase of mass transfer is actually not a common envelope, but is a stable but non-conservative mass transfer. So you actually don't shrink the orbit, but because you have to lose mass, because of the in the end you lose mass, after all, this stable mass transfer has to be non-conservative. And because then you measure the orbital periods of these double degenerates, they are very close, then you have a second a common envelope phase, which is actually followed by the alpha prescription. Okay? The first two prescriptions of common envelope evolution have been incorporated in population synthesis studies, and what right now is the only thing that we have. So if you want to simulate, for example, the population of double degenerates in the galaxy, you either have to use gamma or alpha formalisms. Unfortunately, there is no work that uses this kind of stable, non-conservative mass transfer plus common envelope phase in population synthesis studies. And that will be something that really encouraging to proceed. So current demographics. Now that we know that those double degenerates mass form through at least one common envelope phase, which we don't know which prescription actually works better. Let's talk about what we observe. These prescriptions are based on constraints from observations. So let's see where these observations come from. So I'm going to emphasize that what I'm going to show here is taken from Tom's Marsh presentation in Copenhagen, because he did a very good job putting these numbers together. So in the last 25 years, we had around 200 double degenerates, and everything started focusing on low mass, apparently single white dwarfs. because the truncation of the red giant phase leads to a low mass helium core white dwarf. So people thought, well, if we look for low mass white dwarfs, then they must be in binaries, and we have been seeing that 70% of them, at least, well, they seem to be in binaries, extremely low mass white dwarfs, 100%, well, and so on. So that was the first step. This was papers led by Tom Marsh, Pierre Masted, and so on. The SPICE survey doesn't have any constraint on the white dwarf mass, just simply takes radial velocities, 2 or 3 radial velocities of white dwarfs, and finds double degenerates. There was the last paper this year, 2019. The Sloan Digital Scale Survey has been also very productive at finding double degenerates because we have super-exposures of the SDS as a spectra, which allows looking for the velocity variations. And there is a survey by Naama Halokon, who is also trying to find more through these systems. The extremely low mass white dwarf survey, papers led by Mukerman, Klick, and Warren Brown. They found several, actually quite a lot, of extremely low mass white dwarfs, and we have seen Ingrid is going to proceed finding these kind of systems. And there is a Gaia DR2. Yeah, I have to touch this more often. So if we add now in Copenhagen, Tom also showed us that he's leading a survey of Gaia white dwarfs, which are double degenerate, which are the most important ones when you want to find masses. And there are also eclipsing systems, which allow also to finding masses and orbital periods, which are, but only a handful of them. So, as I said, these are taken from the Copenhagen talk of Tom Marsh. There are around 121 binaries with orbital periods from 7 minutes to 30 days. This will be the orbital period distribution of current double degenerates. And I have to emphasize that this has huge observational biases, right? Because, well, first, for obvious reasons, you only find the shorter ones, but especially when you look for masses, the primary mass is easier to find because you might assume there's more bright, and by fitting, for example, the combined spectrum, you assume that this comes from the brighter one, and then you get M1. But the M2, which is given by the blue dots here, the red triangles are upper limits, is much harder. Much harder because for that you actually need double line systems, and for that to be the case, the two wild dwarfs have to be more or less the same luminosity, because otherwise you don't find the double line system or eclipsing systems. It's precisely with these systems, the ones that have primary and secondary mass stars with orbital periods, that we can actually reconstruct the evolution and find the constraints from the population synthesis, gamma, common envelope, and alpha common envelope phase. So we are actually talking to observations which are heavily biased. So we not only do not know what is the formalism that reproduces best the evolution of double degenerates, but also we are very heavily biased towards systems that have masses measured. And this, as I just mentioned, is only possible if you have double line systems or eclipsing systems. This is just to show that if you compare the mass distribution of single white dwarfs, which also has double degenerates inside, this is the primary mass distribution of the currently known measured systems, which, as we were mentioning before, the giant phase is truncated, and therefore you have low mass white dwarfs. Also related to a paper that we published back in 2011, if you take post-common envelope binaries, not double degenerates, but white dwarfs with main sequence binaries, what we found is that you go to the white systems that didn't evolve through common envelope, what you find is the mass distribution is very similar to the field mass distribution. However, if you go to the post-common envelope systems, there is a peak at 0.4 solar masses. Okay, so this tells you that at least there must be one common envelope phase. So let's talk about the evolution. There's not much to say apart that these systems emit gravitational radiation and that in time they will eventually merge, right? These are the dominant sources for LISA, and this is fantastic because in a few years we will find many of them. This is just to show you how double degenerates can be used to to test general relativity. This is work in preparation, or maybe it is already submitted by J.J. Hermes, who also presented this work in Copenhagen. What he shows here is the observed minus calculated diagram for, at that time, the shortest double degenerate system, which has 12.75 minutes. So it was discovered in 2011. Until now, they have been observed, and they can basically fit this decay. That will be zero orbital decay through the gravitational radiation. So basically with all these points, what they can see is that the expected decay from general relativity is actually quite similar to what they observe. Okay. Now there is one system of 7 minutes. Maybe in 10 years from now, we can do, or they can do something similar to this. So let's go to the outcome of the evolution. We said that the double degenerates will eventually merge. And this is a picture which shows you a wide variety of systems that you can form when two white dwarfs merge. So that will be the mass of the accretor, that will be the mass of the donor. You will have only systems here, and above this line here, you will have those that they might produce Taiwanese supernova, or accretion-induced collapse neutron stars, and those here that will form carbon oxide, massive white dwarfs, and a wide variety of things that we are not going to get into details here, but I would like to focus on these two here, supernova 1A progenitors, and the merger of two white dwarfs. So let's begin. I'm going to talk about more subjective work here of papers that this one specifically published at the beginning of this year. So the idea was to test somehow or give insight on the long debate of whether or not double degenerates are supernova 1A progenitors. Many people say, well, they are not because we don't find them. So can you say this? Can you actually say that supernova 1A progenitors from double degenerates do not exist because we don't find them? So that was the main question. And what we thought is to calculate the probability to finding these systems. For that, we ended up running a population synthesis study. And as I said before, you have to assume common envelope phases. And we used the two prescriptions that we can actually use, the gamma formalism and the alpha formalism. Then you get a population of double degenerates in the galaxy, and you get those that are supernova 1A progenitors. And then you say, well, how am I going to observe these systems with our current telescopes? So the first thing that you do is to simulate the double degenerate spectrum, which is combined of the two white dwarfs. You have the parameters from the population synthesis studies, and you interpolate this in the white dwarf atmosphere model spectra, and you get a synthetic spectrum of the double degenerate, and you check if you can detect the double line systems, because as we mentioned before, this is where we can get the masses of the two stars. These are two different examples, and when you have ideal spectra, not affected by resolution or signal-to-noise issues, this is what you see. So these two systems, ideally, I will find them. But the problem is that these systems are actually very faint. So if you introduce observational biases, then you see this will be the ideal case. And then you say, well, what will happen if I go to different telescopes around the world? And we chose these ones, VLT with X-Shooter, WHT with ISIS, GTC with OSIRIS, and blah, blah, blah. You introduce the signal-to-noise ratio, you introduce the effects of having a finite resolution, and in this case, what you find is that in all cases except GTC, which has very low resolution, you will find the double peak, and therefore you will be able to measure the masses and the periods. But unfortunately, because of the intrinsic faintness of these systems, this is very seldom found. And what you actually end up finding is something like this. So that will be the ideal case, and in the end what you have is something like that. So there will be no way to find these systems. You will find that the double lines in a few of them, very few, and this will give you a probability of 2 plus minus 1 of 10 to the minus 5 of finding a double degenerate progenitor. The picture doesn't change dramatically if you consider eclipsing systems and the LSST, or you consider bigger size telescopes. So The probability does increase, but not dramatically. Fortunately, what we also found is that with LISA, you will be able to measure the chirp mass of the double degenerates, and therefore, because it depends on the mass of the two stars, if you take the population synthesis studies that we run and you take the orbital period and the chirp mass that the LISA will detect, what you find is this kind of graph, with 0.6 is the above 0.6 are those double degenerates with equal mass and above Chandrasekhar. 0.4 are unequal masses but above Chandrasekhar. So there are a bunch of systems that you will find. These lines here will give you the error of the chirp mass that LISA will measure. So that will be 0.1%, 1%, and 30%, and the same here. You can see it very well, but the important message here is that LISA will be able, if they are there and they exist, LISA will find them, and we will be able to answer for sure, or that's the expectation, if double degenerates are progenitors of Taiwan supernova. So now let's move to the merger of white dwarfs. And this is something that we have to go back to 2005. Why? Why am I interested in mergers? Because mergers might be related to an observational excess in the peak distribution of apparently single mass white dwarfs. This is the Palomar Green survey. This is a magnitude limited survey, and this is the distribution of stars in this specific survey. Because it is a magnitude limited, you have to apply a volume correction, which is called the Vmax method, which basically calculates the maximum volume for each white dwarf as it will have been observed through the survey. This volume correction favors or takes into account that massive white dwarfs are smaller and therefore you lose them. So when you apply the Vmax method, you go from a distribution to a space density distribution, and what you find is that there is a high mass bump here between 0.8 and 1 solar masses. That one of the possibilities for this is merger systems, merger of two white dwarfs. If you go to the volume limited sample of 20 parsecs, this is the total distribution in black, and this is for the A white dwarfs and the B white dwarfs. You can also see that there is some kind of excess here at 0.81 solar masses. Later on in 2015, I was also interested on that, and I analyzed the LAMOST spectroscopic survey of the Galactic Anticenter survey and the Sloan Digital Sky survey. These are magnitude limited samples, so in this case we had to apply the volume correction, so therefore we have space densities here, and again we see this kind of bump here. This gray distribution is for bolometric magnitudes below 12, and if you include the cooler systems for bolometric magnitudes up to 13, you see this high mass excess. Again, in Gaia, you also see an excess. The problem with Gaia is that we actually don't know the spectral type, so this high bump here that we found in the 100 parsec, which is volume limited, we don't have to apply any volume correction. Is this, first, is this because of the A white dwarfs? Most likely, many of them will not. So this will very likely decrease. By how much? We don't know. This is just too simple. This red distribution here is a simulation of the single white dwarf population in the galaxy, which clearly has this overexcess here. Now, the only way to see if this is real or not is to take spectra. And I was very happy to see that in Copenhagen, also Mukhim and Kilik showed that for a follow-up of some systems in the 100 parsec, they found this distribution. And this is for real DA white dwarfs. So they confirmed that they are DA white dwarfs. So you can see, well, the typical peak at 0.6 solar masses and a high mass bump. Can you claim that this is a merger or a bump? Well, they also did some similar study to us, and they simulated the wider population of single stars, and they found that this is well, in agreement with well, some kind of excess here. So the obvious question is if these are merger systems, no? So just to conclude, I would like to say that at least the formation of double white dwarfs or double degenerates requires one common envelope episode to see, because we have very short orbital periods, we don't actually know how they form. There are about 200 double degenerates known, and many with periods and masses of the primary. However, we are biased to the secondary mass. So there are few of them so far because of they have to be double line systems or eclipsing. Double degenerates, supernova progenitors. I hope it was clear that they are very hard to find, so you cannot claim that supernova double degenerate progenitors do not exist, because you actually cannot see them. At least I suspected to find many if they exist. And the last conclusion is that I think there is a strong evidence for this high mass excess of DA white dwarfs. Now the obvious question is if these come from mergers or not. So I will leave it here, and thank you very much.
Thank you. Questions?
I was interested in the Killich plots you showed. There is stuff above 1.2 solar masses. Is that consistent with neon oxygen white dwarf, oxygen neon white dwarfs, or would that be mergers?
Yes, they're supposed to be oxygen neon white dwarfs.
Oxygen neon.
Yes, they're supposed to be. They have spectra for that, so yes, yes. Mm-hmm. These are systems that they follow up. This is preliminary. They said that they have observed maybe, I don't know if it's 25% or 50%. Because when I talk to them, they follow, they take short exposures. So they only care about, from the spectra, they only care if they see Balmer lines or not. And then if they confirm it's CDA, they get the mass from the photometry. So they don't really care about going to very high signal to noise. So the idea is to go for short exposures, see they have Balmer lines, and then use the Gaia photometry and the fits to get these kind of masses.
Here's another question.
For the ultra-short period system where we have been able to test the GR orbital decay, so it's in principle possible to expect that we'll be able to also test the tidal synchronization or tidal interactions in closed double wide dwarf binaries. So how close are we to those measurements?
Unfortunately, I cannot answer your question because I don't really know. This was work done by J.J. Hermes, so maybe the person indicated will be to ask him. So sorry about that. I don't really know.
Hi, Alberto. The excess that Killich sees at high masses, you said that they are DA white dwarfs, right? Yeah. But yes, would we expect merger products to be DA white dwarfs?
In principle, yes. To DA white dwarfs merge, there will be a DA white dwarf.
You think it would keep the hydrogen?
Yes, yes, in principle, yes. Although, well, there are obviously, yes, it's possible. That's. If I remember correctly, some theoretical work claimed that actually the hydrogen will leave, so you will not see a DA white dwarf. It's a possibility, but maybe yes. I'm not sure. It could be, but some theoretical work claims that maybe not. But yeah, it's the issue with the merger systems is that you run numerical simulations and you include merge systems in the distribution. There is no way to find this peak neither. So that's a very controversial issue because apparently, observationally, they are there. So could they be mergers or not? That's a very important question to answer.
I don't know if you covered this. Do you know if they measured radial velocities, so they used the kinematics to understand whether the systems are possibly merger, so comparing the kinematics to the age of the system.
From this work?
For the massive white dwarfs.
I'm not sure they have done that, but it's something that is easily doable with the Gaia data, right? I guess.
Yeah, with the Gaia data and the radial velocity, yes, it's possible.
Yes. Yeah. I guess for that you will require higher signal to noise ratio from what they get, but in principle something doable, no?
Okay, if there aren't any more questions, then we move on to the next speaker. thank him again.
Well, hello everybody. My name is Alexey Bobrick, and I'm going to be talking about white dwarf neutron star progenitors for ultra-compact X-ray binaries. So these are almost double white dwarf binaries, except for that one of the white dwarfs is a neutron star. Well, but they are nevertheless quite close cousins of double white dwarf binaries. So when I reflect on what exactly do I want to say in my talk, it comes down to three key ideas about binary mass transfer. And the first idea is basically that the start precedes the end. And whilst it might sound painfully trivial, the point is that if you want to understand the state of an observed object, we have to understand how it exactly formed. Another point is that for binary mass transfer, angular momentum is the key, because angular momentum affects the evolution of the orbit a lot. I refer, for example, to several excellent talks yesterday, for example, by Diogo Belloni. So it matters for CVs, but also for white dwarf neutron star binaries. And finally, hydro simulations can give us more than assumptions, and that can help to explain the orbits. All right, so here's the big picture. So this is a white dwarf neutron star binary. The white dwarf is transferring mass to the neutron star. The material forms a disk. The disk heats up because of radiation gravitational energy and emits a lot of X-rays. Therefore, the binary is an X-ray binary. This is an example of a system called 4U 1820-30. It has a white dwarf of a mass of 0.067 solar masses. That means that the white dwarf has transferred a lot of its material. It has an age of order of 2 megayears, and its period currently is about 11 minutes. And you can estimate how many times 11 minutes fits into those 2 megayears. I mean to say that it has made really many orbits over its lifetime. And because of such short periods, such systems are called ultra-compact X-ray binaries. And this is how they form. So we'll start with white dwarf neutron star binaries, which are already there in detached state. There's about 150 white dwarf neutron star binaries observed as binary radio pulsars. Some of them are sufficiently tight, tighter than 4 solar radii, so that they will spiral in less than a Hubble time. There are actually 10 systems observed which will spiral in less than a Hubble time. And then after they spiral in, there are 2 possible outcomes. The systems come into contact, and the outcomes depend on the mass of the white dwarf. If the white dwarf had a low mass, the system would survive mass transfer and would be transferring over a long time, and we would get systems like on that picture, exactly ultra-compact X-ray binaries. And if the white dwarf had high mass, the system would undergo unstable mass transfer, and the white dwarf would be disrupted on dynamical timescales of a few orbits. And that would lead to some transient events, potentially supernova-like events. Now, the exact boundary between the low and high mass white dwarfs has been traditionally assumed to be 0.82 solar masses, and that was based on rather old models which were assuming a polytropic equation of state for the white dwarf and assuming a very neat mass loss from the system through a jet, which is which is centered on the accretor. And this has been okay until we got statistics. And if you look in detail, there are several problems with this critical mass, actually. So if you look at progenitors, there are systems like pulsar J11416545, which are made of, well, again, a white dwarf and a neutron star, and which will spiral in less than a Hubble time. And they contain a pulsar which is a non-recycled pulsar, a really young pulsar, which is about an order of 1 megayear old. And it means that such systems form quite often and spiral in quite often. So the in-spiral rate for such systems is between 50 and 500 systems per megayear per Milky Way-like galaxy. If we look at the outcomes instead, we see a discrepancy. So we can take the ultra-compact X-ray binaries in the Milky Way with, well, in a state where we can constrain their age, and we can use that to estimate their formation rates. And we find that their formation rates are like about 1,000 times lower than predicted by the model. So the observed system has, for example, has 1 solar mass white dwarf. We would expect that maybe a smaller fraction than unity of them would have masses below 0.82 solar masses, but it's really unlikely that only 1,000th of the population ends up being with masses lower than critical limit. And well, if we look what exactly might be the reason, and if you look at the formation models, we can get another clue. So here's an evolutionary track for a white dwarf neutron star binary which has just come into contact. On the x-axis is the orbital period. On the y-axis is mass transfer rate. The systems spiral in with very short orbital periods, and then the white dwarf transfers mass and expands, and the orbital period becomes larger, and because of that, the gravitational wave emission becomes weaker, and mass transfer rate decreases. So there's such thing for mass transfer, which is called Eddington mass transfer limit. Eddington mass transfer limit means that if material is transferred at a rate higher than this limit, then the material will be hard for the donor to accept, so it will be probably ejected. So for neutron stars, the Eddington mass transfer limit is about 4⁻⁸ solar masses per year. So on this plot, the neutron star's Eddington mass transfer limit is somewhere over here. In the model, the systems evolve starting from over there all the way. And in the model, again, material is lost neatly through a jet centered on the neutron star at mass transfer rates which are about 1 million times more than Eddington mass transfer limit, when the mass transfer is supposed to be horrendously messy. All right. The authors of this study actually do discuss that, yes, indeed, we do transfer mass above Eddington limit, actually above even isotropic re-emission limit, but however, we don't have really good models to constrain the angular momentum loss, so they assume that it's just simply, again, a jet. To do something about it, we set up hydro simulations. This is an example of a model. These are modified smooth particle hydrodynamic simulations. The white dwarf in this code, it's called on-water code, is represented by two types of particles, one for the stellar body and the other type of particles for the stellar atmosphere. In this example, the binary just going in a circular orbit does nothing, just to show the stability of the code. The idea of separating the stellar body and stellar atmosphere by these Lagrangian conservative forces is to be able to put significant amounts of resolution into the atmosphere and thus be able to resolve details of mass transfer. And well, we set up the actual mass transfer simulations. And here, the white dwarf is orbiting again the neutron star. The neutron star is not allowed to accept any mass to model this phase of really highly super Eddington mass transfer. What we observe is that the simulations stabilize into, so to say, quasi-steady regime after about 10 orbital periods, wherein the disk mass remains roughly constant, the mass loss from the disk remains roughly constant, the mass inflow into the disk remains also roughly constant. So we have this flow of material through the disk. And from these simulations, it's quite easy to extract the angular momentum of the material which is ejected from the system. And here is a simple physical point, actually. So the material which has been ejected is going really very quickly around the neutron star. This is opposed to the jet which is centered on the neutron star, which is not moving almost at all, because the white dwarf is much less massive than the neutron star. So the angular momentum of the material ejected is much higher than that of just the neutron star itself. And this has quite significant consequences. All right, one thing I didn't mention is that actually quite many of these binaries spiral in quite eccentric. So if we just take that system which I've mentioned, pulsar J1141, initially it has eccentricity of 0.2 or so, and if we calculate the gravitational wave in spiral with the Peters equation, for example, we find that the eccentricities at the contact are going to be about 10⁻�3, 10⁻², or something like that. And even if we account for tidal circularization, it's still going to be significant. So the white dwarf atmospheres instead are quite thin, so it means that it's quite easy to significantly alter the mass transfer rate from the white dwarf depending on where the Roche slope is. And so for white dwarfs which spiral in, typically the situation is that, for at least for some of the populations in there, is that the mass transfer turns on close to periastron passage and then turns off for the rest of the orbit. So it turns on and off, on and off. And we have also looked into that. We have actually simulated those systems. And we have extracted this angular momentum loss, and we have put it into a long-term evolutionary code wherein we use a 1D stellar model of the white dwarf and evolve it over many, many orbital periods, billions of orbital periods, you know. And we have constructed tracks which show the mass transfer rate on y-axis versus mass lost by the white dwarf, which is a proxy for time on the x-axis. So here are two examples for two systems. In the first plot, we have a system which has 0.15 solar mass white dwarf. It reaches some high mass transfer rates, gets lossy, but then stabilizes, and mass transfer rate decreases, and the white dwarf goes into ultra-compact extra binary again. And here's an example of an unstable system, wherein the mass transfer rate increases, it gets lossy, but then the angular momentum loss in the evolution starts to dominate the overall evolution, and the white dwarf, well, loses mass at increasingly higher mass transfer rates and then gets tidally disrupted. And well, the critical mass limit actually for these systems is actually 0.2 solar masses, not 0.8 at all. So again, this is because of the enhanced angular momentum loss from the binary. And if we take a look at how the observations look like with such a new critical mass, they actually seem to make more sense. So, for example, if we look at the systems which contain a helium white dwarf companion in the detached binary pulsar configuration, their in-spiral rates are about 0.72 systems per megayear. If we look at helium ultra-compact X-ray binaries, which are produced by those binaries, they actually agree with the in-spiral rate within 1 dex, so by less than a factor of 10, which is much better than a factor of 1,000. If we think about carbon-oxygen ultra-compact X-ray binaries, our prediction is that those cannot be formed from carbon-oxygen white dwarf neutron star in spiral, because carbon-oxygen white dwarf neutron star spirals must have been unstable, so therefore they must have led to transients. If we look at the rates of transients produced by unstable systems now, which are more massive than 0.2 solar masses, we find that they actually match the in-spiral rates, or match the observational rates for several classes of supernovae, such as calcium-rich transients or faint rapid transients, and a few more in fact. But still, it's encouraging that they have, well, similar order of magnitude for production rates as those transients. Now, just a few other small points which came up from the study, which I thought you might potentially find interesting. One point is that, well, we have been able to actually verify numerically the so-called Ritter's formula. Ritter's formula says basically what is the mass transfer in a binary if you vary its separation for an exponential atmosphere. And, well, here is a plot for a separation versus mass transfer rate. The black curve is the Ritter's law. And the thin lines, which you maybe can see, are lying on top of the black curve. Those are simulations, so this is done without any fitting whatsoever. Another point which you might find interesting is that we have found in the simulations that the volumetric radius of the donor actually changes due to tidal deformation. So again, I repeat it, so the tidally deformed white dwarf doesn't have the same volume as the non-deformed white dwarf. So in our simulations, and we have tested the numerical, well, we have tested it with several methods, and we've also checked the convergence with resolutions. So the white dwarfs actually increase their radius by about 5% on average when coming towards Roslob overflow. And moreover, for nearly equal mass binaries, the increase in the radius of the white dwarf can reach 15 to 20%. And potentially it could be an explanation for why the nearly equal white dwarf simulations, when they are set up in numerical studies, they lead to more violent mergers. And then finally, if one tries to set up a numerical binary with, well, in a circular orbit, then tidal interactions actually do matter. And if one doesn't account for that tidal interactions, one gets to set a binary on eccentricity order of 0.01, which can lead to about 0.5 dex variations in mass transfer rate. So potentially interesting. Just a few words about our other study, which we've done together with Joseph Senati and Hagai Peretz. So actually, if you can tune, if you can set up the simulations, which can do quite delicate simulations of stable mass transfer, it's not so hard to simulate unstable mass transfer. So here's an example of a neutron star shredding a white dwarf tidally. So this has been done with our SPH code. And here is on the right is an example of a flash code simulation. It's a grid-based code simulation also of disruption of a white dwarf by a neutron star. And these two codes are, so to say, complementary. Flash code is, again, AMR-based code, which is good at resolving subsonic turbulence. SPH code allows us to simulate over longer times and also has better shock treatments. So we have simulated the mergers of carbon-oxygen white dwarfs with neutron stars. And then we have applied the nuclear post-processing to those simulations, both to Flash and to SPH, with the MESE PPN code. And then we have applied a radiative transfer simulation to the nuclear yields from the MESE PPN code to obtain the light curves and spectra from those transients. And what we found basically is that nuclear yields from carbon-oxygen white dwarf neutron star mergers are actually pretty modest in the sense that we produce only a small amount of nickel-56 up to 0.01 solar masses or so. And therefore, we can predict actually that unstable systems lead to transients which are not really bright. So their luminosities reach a order of, well, minus 15 magnitude, 10 to the 38 ergs per second or so. And their spectra are, well, they're somewhat resembling of those of faint red transients, but however, they are much fainter again, and there are some certain differences. So therefore, we predict that perhaps the carbon-oxygen white dwarf neutron star mergers are going to lead to a different type of transients which has not yet been observed. And we predict that with LSST, those mergers are going to be observed at rates of order of a few tens per year. So conclusions. Well, in summary, we have done hydro simulations of how white dwarf neutron star mergers transfer material. We have used those simulations to measure the angular momentum loss from the binary. Angular momentum loss comes from the disk, which goes really quickly around the neutron star, not from the neutron star itself. Therefore, it's pretty high. Therefore, the critical mass is lower than previously predicted. This helps us to explain the observations better. Some more upcoming work. There's also going to be a population study of these binaries in global clusters coming up soon this year by our group. Then there's also a work on calcium-rich transients, which were thought to come from white dwarf neutron star binaries. Those done by Josef Zenati and others, and there's going to be talk about it later this week. And finally, we also are currently looking at transients produced by mergers of oxygen neon white dwarfs and neutron stars. Thank you very much.
Thank you. Questions?
Thank you. This is just one comment. We know already for a long time that super Eddington accretion is possible. And there are some diagrams where the number of sources versus luminosity, and we do not see any feature in the point of canonical Eddington luminosity. Therefore, actually, from the observational point of view, we do have to consider accretion about 1,000 times higher than Eddington limit. Is it good for your model or not?
Yes, you're completely right. We know of ultraluminous X-ray sources after all, and we know that, well, I mean, we know of sources which transfer material at 10 times Eddington mass transfer rate and even up to possibly 1,000 times Eddington mass transfer limit. So it a bit depends on the neutron star itself, whether it's magnetic or not, whether it can funnel material or not very well. But the point is that for white dwarf neutron star binaries, no matter which model you assume really, the binary initially is so tight that the mass transfer has to be about 1,000,000 times above Eddington mass transfer rate. It's really, I mean, extremely high mass transfer rates. It's an order of like 10 to the minus 2 solar masses per year. So it's really very, very high. So, so for our model, it's quite all right that there are ULXs. In fact, white dwarf neutron star binaries themselves can be, well, ULXs. Yeah, I guess the main point is that, yeah, mass transfer rates there get really very, very, very high.
Another question?
I thought when people are doing binary evolution, I thought normally in a situation like this, they would be talking about the thing going into a common envelope with such high mass transfer rates. But you seem to have a sort of a disk there surviving and managing to get rid of the angular momentum from the disk. Why isn't it being sort of buried under material? That's what I'm just wondering how it's able to cope with and get rid of all this material. Is that an absolute certain prediction, or?
So again, the point is that the limit of 0.8 solar masses was determined based on the assumption of just purely mass loss without any common envelope and just purely into the jet. In our model, actually, we do form an envelope and we calculate the energy, the binding energy of the material in that phase when the mass transfer rate exceeds the Eddington limit by a sufficiently large factor of more than 100. So
this state here, is there meant to be an envelope around that?
Yes, there is an envelope, and the energy of the the envelope must be unbound through. The envelope is replenished continuously from the inside, but this comes at the expense of the energy of the orbit. At least we assume the long-term evolution model, and we account for that angular momentum loss or energy loss into the ejection of the envelope. That's the point. Yeah.
Cool talk. So you say that LSST, you're predicting that might be able to detect on the order of a few of these neutron star CO white dwarf mergers.
Few tens per year.
Yeah, a few times, yeah, per year.
Few tens.
Few tens, okay. Oh, cool. So can you give an indication of out to what distance roughly that this prediction takes into account?
Yeah, so it's about 50 to 100 megaparsec at most. It's just based on the flux limits, so we can't get further than that. By the way, actually, even ZTF is supposed to be able to detect those systems at a rate about few per year. So, we might hope, before LSST we could get one, maybe.
Oh, one more question?
So how many particles do you use for your SPH simulations?
So we sample 4 typical masses, not so many, but we also sample a range of eccentricities. That's why that's why I limited the grid, and we do it at a few resolutions to check the convergence. So in short answer, 4 different masses, 4 different eccentricities, and several resolutions.
Yeah, but I'm asking about the number of particles that you use.
That's right. So in the highest resolution runs, we use 400,000 particles, and of those, 300,000 particles are in the atmosphere, in fact, and 100,000 is in the stellar body.
Okay, then I would say we move on to the last speaker. And let's thank the speaker again, sorry. Joannes van Roestel. He speaks about eclipsing white dwarfs discovered in the CTF.
Right, hi. I'm Jan van Roestel. I'm a postdoc at Caltech for about 1 year and 1 day now. I'm going to talk about basically a really observationally focused talk on the eclipsing white dwarf binaries we find with the Zwicky Transient Facility. I'll also be presenting some work by Kevin Birch, Thomas Kupfer, Michael Coughlin, and Tom Prince is the PI of the ZTF variable science. So the Zwicky Transient Facility, it's mainly designed to find transients. It's a large field of view imager, robotic telescope. It has a field of view of 47 square degrees. It has G, R, and I filters, although I isn't used that much. Until now, we used 30-second exposures, and with that, we reach a depth of about 20.8 plus minus 1 magnitude, depending on the weather conditions. The pixel size is 1 arcsecond, and the seeing is typically 2 arcseconds. It's not the best sight, but we have a very nice telescope there, so that's why we're using it. So 47 square degrees, that's actually quite large. If you look at this figure here on the right, we've got the ZTF field of view compared to LSST, for example, which is slightly less than 10. This is PTF, IPTF, the ZTF precursor. As you can see, we observe a lot of the sky with just a single pointing. So what is ZTF looking at? Basically the entire northern hemisphere above declination minus 30. And we're doing multiple survey, so it's not just one ZTF survey, so I just want to clarify that. So we'll start with the public survey, which is funded by the US NSF, the National Science Foundation. It's a 3-day all-sky survey with a 1-day survey of the galactic plane in both G and R during the same night. And just to advertise this, DR1 is already out. It's been out for a few months now. You can use the data. You can download it from the IPAC website, and you can have fun with that. Then there's also a ZTF partnership, which is doing its own survey, which is actually doing a GR and I-band survey of a smaller area in the sky with 3 observations per night in GNR and 1 I-band observation every 4 nights. It's mainly designed to do supernova science, supernova 1A science, but as we'll see later, it's also very useful for variable stars. So this data is not yet available. It will become available after 1.5 years of the observations taken. So within a year, you can start using the early data of this survey as well. Then this year we also started to do some higher cadence galactic plane data, specifically designed to find compact object, compact white dwarf binaries. This summer we observed this part of the galactic plane. I unfortunately haven't seen the data yet, so still need to process it, but given the results from the high declination survey, the higher cadence of the galactic plane should reveal many compact white dwarfs. And then there's also a 4th survey we're doing from the Caltech time of ZTF. So there's many different tags involved in allocating ZTF time. So this is the Caltech time, and with that we're doing basically deep drilling observations of the galactic plane. So we do at least 1.5 hours of R observations, 30 seconds exposure, so that's about a 40-second cadence if you take into account the readout time. And this survey is also designed to find very short period binaries. And this data will also become available 1.5 years after observation, so that will also be available in about a year. And then we're also doing a ZTF test survey. So whenever Tess is looking at the northern sky at the moment. So with ZTF, we're looking at the same area. So this is so this here is test sector 14, and the red areas indicate the ZTF pointings we're using to observe the test fields. And on the right, you can see the difference between ZTF and TESS. So on the top is what ZTF sees, and on the bottom, the test image for the same field. So, and whenever you see a variable in test, you can use ZTF data to check which one it actually is in that field. There's a slight mismatch in filters. We're doing GNR observations while test is more red. So there's a slight mismatch there, but on the other hand, you do get color information. So those are all the ZTF surveys in a few minutes. This is the DR1 data release. So on this figure shows the DR1 data. As you can see, we're in the galactic coordinate, so we're missing the northern galactic, northern pole over here. There's this gap there, and we're doing intense observations of the galactic plane. As you can see, the sky coverage is not very uniform, especially the lower declination fields have fewer epochs. It's just a decision made to observe in the best conditions, so low air mass fields are not observed as often as the higher fields. And the distribution here on the left shows the number of observations for each of the ZTF fields. So this was yesterday, I think, we have 100 observations per field. I think that's a median, but there's a large tail, which is due to these targeted surveys we're doing with ZTF. All right. So the ZTF data products, there's 2 different data products produced by ZTF. There are the alerts, which are produced using image differencing, where we take a new image, subtract a reference image, and check if anything shows up on the difference image. We're both doing positive and negative differences, which will be very useful, as I'll show later on. These alerts are sent out immediately, or at least as soon as possible. So typically a few hours after observing, you can already access this data. And then there's the other data product, which are the science light curves. So we're also doing basically PSF light curves of all persistent sources on ZTF data. And that will be available well, later on, which is the DR1, which I mentioned earlier. All right. So just to show an example of the alerts, these are a few cataclysmic variables found by Paula Scody, who's working on a CV paper from ZTF data. I won't mention anything more, but I think Isabel will talk about ZTF CVs on Friday a little bit. What I'm most interested in are these things, so eclipsing white dwarfs, as I mentioned in my title. So this is just an example of the ZTF data we have. So the dots here are PSF photometry from the science images. And this is an eclipsing white dwarf brown dwarf system which we discovered. And as you can see here, the crosses show alerts. Basically, the star disappears. So these are negative transients, as I like to call them. And these negative transients are very useful to identify these eclipsing white dwarf systems. As I also show you here, we have some bad data. Unfortunately, we're not such a large team as Gaia, and we're doing ground-based observations, so we do get affected by bad data. Andrew Drake actually made a very nice, did a very nice flagging of the data, so I think most of it we can get rid of now. So with that, we've started to mine the data, and just before I get into that, just how this is actually something I'm working on mostly, is how to classify stars, or specifically variable stars in the case of ZTF. And you basically want to combine all the information you have. So you want to look at time variability, for which we have ZTF. So here, you want to combine that with the color, the average color of that system, which we can use Pan-STARRS or SDSS and Gaia as well, or even higher and lower energy surveys. And there's the third thing, which is provided by Gaia, which is a parallax and a proper motion. And the idea is to combine all these measurements in an efficient way to identify basically all stars ZTFCs. We're not quite that far yet, so we're typically doing either a color selection, then looking at ZTF, or we're looking at ZTF variability, and then see where things appear in Gaia or Pan-STARRS. But the main goal is to basically do this, combine everything, and do a full classification of ZTF. So this is the stuff I work on mostly, but since this is the double white dwarf conference, I'll focus on, the compact white dwarf binary conference. I'll focus on a few specific systems, and just briefly want to remind you about all the different kind of compact white dwarfs there are. So for example, in white dwarf evolution, we find white dwarf main sequence stars, we find double CO white dwarfs, CO helium white dwarfs, and AM CVn systems as well. And we're finding all of these in ZTF in quite large numbers. So I'll just, for the rest of the talk, just give an overview of stuff that I have found, or one of my collaborators has found. So the main method we're applying here is just we period search all the ZTF data. So we have GPU implementations of multiple period finding algorithms. We're using mainly the Box-Lee square to find deep eclipsing systems, and we're also using conditional entropy, which is really fast to apply on large numbers of light curves, and we're searching the entire 2 billion ZTF light curves to find periodic variables. So what happens if you do that? Oh, sorry. eclipsing white dwarfs, sorry. Of course, someone pointed out to me that eclipsing white dwarfs, they're very useful to find, but you won't find many of them because, of course, there's a low probability of finding an eclipse, and if you see an eclipse, if it is eclipsing, it can still be very short, depending on the radii of the two stars. While if you're doing spectroscopy, you basically depend on the radial velocity amplitude, which is much easier to see. So as an introduction for the next slide, which basically shows all of this. So I'll take a few minutes to explain this. So on this axis here, we've got the eclipse duration in fraction of orbital period. And if you look at the middle slide first, I plotted the eclipse duration for different kinds of white dwarf binaries. So in green, we've got AM CVns. Here we have CO plus low mass white dwarfs, CO white dwarfs, and the thick lines are 90-degree lines, while the dotted lines show lower inclinations. So as you can see, the eclipse duration increases rapidly if you go to short orbital periods. So this is a bit difficult to see, but this is 5 minutes, 10 minutes, 20 minutes, and we're about an hour in here. So as you can see, we're really biased towards finding short period, the shortest period white dwarf eclipsing systems. For the double white dwarfs, really we really start, the double CO white dwarfs really don't expect to find any with periods longer than 1 hour. Just because, as you can see here, the detection efficiency, which is in yellow, on yellow here, so this part we do see, this part we don't see. And this is already if we have 1,000 epochs in ZTF, and as I mentioned earlier, we only have 1,000 epochs on a relatively small area of the sky so far. So but we do expect to find stuff here, and we do expect to find white dwarfs with larger companions like M dwarfs or crown dwarfs. And on the right, just for comparison, is the radial velocity amplitude for all these systems. So as you can see, the double white dwarfs are relatively easy to find with radial velocity searches, but the lower mass companions, you get into the tens of kilometers per second, which is much harder. So yes, so now we get to results. So this is work done by Thomas Kupfer, who couldn't be here because he got married a few days ago. So we found this 39 period system, which showed this really unusual light curve. We looked at this and first thought it was some kind of over contact system, but it shows a period of 39 minutes. It's a very blue star. It's actually in the hot subdwarf region in the Gaia HR diagram. And we tried to model this light curve using simple models like D-test system or a Rush-Lobe filling system, but that didn't quite work. So we called in the expert, Tom Marsh, and he actually used L-curve to model this system as an SDB star which is accreting onto a compact white dwarf, which makes this the first system of its kind. And we already have found the second one, which we're both in the process of analyzing. So quickly moving on to other stuff. So I'm very interested in data mining methods. So what I tried to do as a test case, I tried to find white dwarf M dwarf systems, and I used a machine learning classifier to find them using band stars, Galax, and Gaia data, and then I looked at the ZTF light curves for all these systems. So I just showed here that machine learning isn't quite perfect and still needs some work. We're missing quite a few systems, especially if they fall in the main stellar locus here. But combining all this data should allow us to identify most of them, especially with Galax and SDSS, which I we'll add later. So just to show you what I found so far, in ZTF I found 280 new eclipsing white dwarf M-dwarf systems, and just to indicate, actually recover about 30 to 40% of the known sample. So I guess we can still increase this by a factor of 2 if we get more ZTF data, because the reason is almost always that we don't have enough ZTF epochs yet. So just to go into the details here to show you an example, what I do, I search for periodicity for white dwarfs which show these negative alerts. Then I try to find a period using box least square, and then I fit a trapezoid model with some sinusoidal components in there and check if this fit is significantly better than just a straight line. And well, with this method I found 280 of them. So I'm just in process of analyzing this, but an initial result is the period distribution of this this sample, and I compare this to the Ritter and Kolb CV catalog, which is shown here in gray. It's difficult to see, but we've got the CV period gap here, and something which has been bugging me since I did my master project like 6 years ago. We should be able to find these CVs which detached as these CVs which detach as eclipsing white dwarf M-dwarf systems. So there should be some kind of period spike there. And there was a prediction by Davis, 2008, that we should find 4 to 13, a fraction of 4 to 13 of these systems. Actually, I don't see anything there, so I'm not quite sure what's going on here. We're doing a spectroscopic follow-up of these systems to get temperatures and spectral types to see if it has something to do with that. So this is some work in progress. You'll hear more about later, I hope. Then other stuff we're finding with ZTF. How much time is left? This one has been mentioned a few times, so I'll quickly go through this. So this is the 7-minute binary found by Kevin Birch, which is a double white dwarf binary. If he actually found this with only 90 epochs of ZTF, so after 3 months, so we were really enthusiastic. We're going to find like a dozen of these. Unfortunately, this first one appears to be very unique. It's the only really short period we found so far. But this is basically a very hot, compact CO white dwarf with a low mass white dwarf around it. And I'll quickly go to the highlights since I only have 1 minute left. It's one of the strongest gravitational wave sources there is, and as you can see in the LISA gravitational wave strain figure, it's one of the strongest sources. And I think the prediction was we could measure P double dot within 10 years, so that would help in distinguishing between gravitational wave and tidal effects in this system. So just to give you an overview of the stuff we found so far, so these are all the 8 or maybe 7, I'm not quite sure about the last one, but all the 8 new double white dwarfs we found in ZTF data so far. So this is a 7-minute one. We have a 14, 24, 40, 61, 91 and 94 period system, and there's one at longer period which I'm not quite sure about. And where do they well, skip this as well. We've got very nice light years for all of them. So they fall here in the Gaia HR diagram, mainly focused on where the other ones are. So the stars are the ZTF discovery, dots are the known systems, which are listed on the right. Most of them fall here, but we also do find some stuff on the white dwarf track, and I'll really need to hurry up now. This last one I want to discuss in more detail. I actually thought this was a double white dwarf as well, but apparently if you look at the light curve, it only shows one eclipse. So we got a hypercam light curve for this one, and it showed, well, it still looks like just a single, like a white dwarf with a single eclipse. The depth is all 50% in U, GRI, C, and Y. And if we took spectra of this one, which showed that it's actually an AM CVn system. So just to indicate where this one would fall on Matthew's plot, it's a 61-minute system, so it kind of falls around here. And my initial fit shows that it's somewhere in this region. I'll quickly go through the spectra here. This AM CVn is really odd, as it shows, well, maybe I should show this one. So it shows helium, which is not uncommon, but also carbon, nitrogen, sodium, magnesium, potassium, and possibly zinc as well. So it's has a quite unusual spectrum. And I think I'm over time already, so I'll just stop here and ask you for questions. Thank you.
Yep, we have time for a few quick questions.
So I don't know if you could comment about the eclipsing white dwarfs by brown dwarfs. So that would be a population that we would be looking as a end, like the end stage of CVs. So have you found any?
Yeah, so I'll show. So this one is actually a white dwarf brown dwarf system. It's unfortunately the only one we found. I mean, they show eclipses of 100%, and I
exactly.
looked very carefully, but this is the only one we found so far.
What is the orbital period?
It's about 70 minutes.
70 minutes.
Slightly longer.
And only that's very constraining then. About
yes, yes. So we do have spectra. I haven't had time to analyze them yet, but yeah, it's one of the things we're finding.
Thank you.
So just a quick comment on the period gap spike that you don't see. Like your population there will be contaminated by white dwarfs with very low mass M dwarfs that would start mass transfer below the period gap. And so you do need some information on at least the spectral type of the companion, tidy up, and then it may show up.
Yes, so we are in the process of getting spectra for all of these systems using DBSP and LIG mostly at the moment.
One more very quick question. No, then Boris has to make some announcements.
Yes, so just a few minutes between now and lunch. So one thing that we tried with this conference is to bring together a few more people, not just cataclysmic variables or double degenerates or AM CVn people, but all the white dwarf binary community. And in 2 years, or spring 21, we will have a 2-month workshop at the KITP in Santa Barbara, where we broaden that even a bit further. So anything. Oh, yeah, 21. That's 21. Sorry. I was quite tired when I wrote that. So it's 21. A year and a half from now, and it's anything to do with white dwarfs, including the people who do atomic physics, equations of states, atmospheres, all binary people, everything to do with planets that accrete onto white dwarfs, type 1As, progenitors, and so on. Those of you who are not familiar with that program, it's a proper workshop. You have to come for at least 3 weeks. You're welcome to stay 2 months. KITP provides accommodation, usually. I come back, there's a caveat to that. There's a very loose program, couple of talks throughout the week, but most of the time you will actually work. You have an office, you sit there and you just hook up with people you meet and you do work, write papers. Deadline for applications is November this year. That's not a strict deadline, but if you know you want to go, then make sure you apply by November this year. The address there is hard to read, is www.kitpucsb.edu. So the one caveat is that you can only apply as a kind of full participant if you have a staff, faculty, long-term fellowship, research scientist position or something like that. And if you have a postdoc or PhD student, you can bring them along as an affiliate participant, but they have to be there during the same time as you are there. So that's the rules. Don't know why, but okay. So if you're interested, would be very much looking forward to see as many of you there. 3 weeks, spring 21, deadline is November this year. Thank you.
So let's start the next session. I am Arek Mikhailian, the director of Burakan Observatory. I will chair this session. So the first talk is an invited one by Elias Aydi, The title is changed now, Novae eruptions powered by shocks.
Thank you.
Please, 35 minutes. I think let's keep 30 minutes or less to have time for questions.
Thank you very much. So the title was Studying Flaring Novae. Now I'm going to talk about shocks in novae, but also I'm going to talk about flaring novae. This work is a collaborative work with a lot of collaborators and friends. Many of them are in this room. Since it is the first talk about novae in this conference, I'm going to introduce novae a little bit. So what are novae? Novae are stellar eruptions that occur on the surface of accreting white dwarfs and interacting binary systems. So we have, or cataclysmic variables, so we have the white dwarfs accreting material via an accretion disk, and then the matter build up on the surface of the white dwarf. The pressure and the density increase, and once a critical pressure is reached, we have a thermonuclear runaway triggered on the surface of the white dwarf, ejecting parts of the envelope at velocities ranging between 500 and 5,000 kilometers per second in extreme cases. The remnant hydrogen burning on the surface of the white dwarf, the emission from the remnant burning diffuses through the ejecta and peaks initially in the optical and then in the ultraviolet. And while the ejecta expands, it becomes optically thin for the hydrogen burning on the surface of the white dwarf, which peaks in the supersoft X-rays. Now, after the party is over, the accretion resumes on the surface of the white dwarf, building up for the following eruption. So in a nutshell, novae accrete, erupt, repeat. The recurrence time of novae range between 1 year in some extreme cases, like the crazy nova and M31, up to thousands and thousands of years. Now, why we study novae? Of course, if you are interested in the physics of accretion and nuclear processes, these are the objects to study. Novae contribute to the dust formation, to the dust abundances in the galaxies, and they can be used as laboratories to study dust and explosive transients. Also, they form lithium, and they contribute to the lithium abundances in the galaxies, and they are candidate progenitors for type 1a supernovae. And more recently, another interest has been added for studying novae, and I will talk about it a little bit later. But from the standard model of novae being powered by emission from the white dwarf, we'd expect that a typical light curve of a nova show a quick rise to a maximum and then a smooth decline. But not all novae behave. And the optical light curves of novae show a diversity of features from long-lasting maxima to cusp shapes, to flares and jitters, to oscillations, dust dips, and only 40% or maybe less of novae show a smooth decline. And usually when I look at this plot from Srop et al., this is my reaction, because what's happening here? I know a lot of people have tried theoretically to explain these features, but I still believe that the optical light curves of novae are still poorly understood. Now, to summarize, novae, as we know them, are stellar explosions powered by thermal emission from the hot white dwarfs, which diffuses through the ejecta. And this has been the standard paradigm of novae eruptions that has been accepted for several decades. Until a surprise came with Fermilab detecting GeV gamma ray emission from novae. And it was a shock. No, literally a shock, because you need shocks in order to accelerate particles to relativistic speeds, more particularly the diffusive shock acceleration mechanism, which requires dense shocks and fast shocks and dense medium. Sorry, the video is corrupted. But we know that nova ejecta are not that fast, not compared to supernovae. But they are really dense. And here's a plot showing comparison between the density and velocity of nova ejecta compared to other transients that you might be familiar with. And we can see that nova ejecta are really dense. So there are two scenarios for accelerating particles, the leptonic scenarios, where electrons are accelerated via the relativistic Bremsstrahlung, so they emit high energy photons, and we have the hadronic scenarios where hadrons collide to form pions, which then decay and emit gamma rays. And therefore, we can add another interest for studying novae, which is the study of shocks and the study of particle accelerations. But the big question is, where are the shocks happening? Well, the first novae that has been detected by Fermilab in 2010 was Nova V407 Cygnus. But this one, it was a bit different because it has a giant evolved secondary. And the shocks were suggested to occur between the nova ejecta and the dense circumstellar medium, which is enriched by mass loss from the giant secondary. However, more novae has been detected with Fermilab, and we know that these systems have a main sequence companions, and therefore they don't have a rich circumstellar medium. So in this case, where the shocks are happening? Currently, the hypothesis or the suggestion is that the shocks are internal to the ejecta. More precisely, between an initial slow dense torus, which is shaped in the equatorial direction by the binary motion, followed by faster, less dense wind or outflow, which slams through the torus, and at the interface of these two ejecta, the shocks are happening. This didn't come from nothing. It actually came from radio imaging of the gamma ray nova V959 MON, which initially showed unresolved thermal emission. And we expect that at this stage, we have the ejection of, or the emission is dominated by the slow dense torus. Here, the equatorial direction is in the vertical direction. Sorry, you have to look at the plot like this, but this is how the projection of V599 is in the sky. And we have some synchrotron emission, which is a tracer of shocks. But later on, we start seeing thermal emission being dominated by an outflow in the bipolar direction. And we think that this is the wind that is coming later. Once the less dense wind dissipates, we can still have emission from the slow dense torus in the equatorial direction. Now you can look back again and see it in the direction that we prefer. We have the dense equatorial torus followed by this fast wind. And as I said, the shocks are happening at the interface of these two components. So based on the hypothesis or the theory, sorry for the colors, they look much nicer on my laptop. We expect that the shocks, which are traveling in a very dense medium, are radiative than adiabatic because their cooling time scale is faster than their expansion time scale. And we expect that the temperature of the shocks to be between 10 to the power 6 to 10 to the power 7 Kelvin, which means they should peak in the X-rays. But we don't see much X-rays. Actually, we see only gamma ray and optical. So what's happening in the X-ray? We expect that the dense medium ahead of the shocks is absorbing the X-rays, reprocessing them into lower wavelengths when they are re-emitted or escaping in the optical and ultraviolet. If we compare what is the gamma ray luminosity to the optical luminosity in the gamma ray novae, we found that most of them show a ratio of around 1%. So the gamma ray luminosity is only 1% of the optical or bolometric luminosity. And although this seems minimal, but it's actually very important. Because based on standard gamma ray emission mechanism, we expect that only 5% of the shock power is used to accelerate particle to relativistic speeds. And only 20% of these 5% are emitted in the Fermilab passbands. So expect that only 1% of the shock luminosity is observed in gamma ray. And if we compare these two relations, we can naively conclude that a large fraction of the bolometric luminosity is coming from the shocks, which means we have shock-powered emission rather than emission powered by the thermal emission powered by the white dwarf, which places some question marks on the standard paradigm of novae. But for this to be true, we should see some kind of a correlation between the optical and gamma ray light curves of a nova. The first evidence came in 2016 with Nova Assassin 16MA, where we see the gamma ray and the optical light curves of both novae showing a similar trend and dipping together. But the strong evidence came last year with Nova Assassin 18FV, which have erupted in the constellation of Carinae in 2018 and was discovered by Assassin. This is a real photograph of the nova. It is really bright. And here we have a giant star next to it. And by mere chance and coincidence, one of the nanosatellites of the Breedt nanosatellites constellation was monitoring the giant star next to the nova. And it captured the eruption of the nova in real time. And this is what we got. We got a 1 in a 2 million chance light curve, actually, not in a 1 in a million, 1 in a 2 million chance light curve, following the nova eruption from its start, throughout its different stages, and showing some short time scale flares lasting for a couple of days with an amplitude of less than 0.8 magnitude from the base of the nova. And this is really beautiful, because if I show you what a typical one-day cadence ground-based observations of the nova look like, we can barely resolve these flares. We have some variability, but we cannot see the separate 8 flares in the light curve. Unfortunately, when the nova went off, Fermilab had technical problems due to its solar panel, and it was not observing. But when Fermilab came back online around 23 days after the eruption, this is what we got. Because of the brightness of the nova, this is the brightest gamma ray nova ever, we got a very well resolved gamma ray light curve showing flares correlated in time with the flares in the optical. And I think this is really cool. And this is very beautiful and somehow confirm what I was just saying. But can I just now conclude that, okay, the optical emission or large fraction of the optical emission from novae is coming from shocks, and that these flares in the optical are also coming from shocks? Well, not that fast, because we can suggest a different scenario than the one I was suggesting to form these correlations between the optical and gamma ray flares. In this case, we're going to have a change in the luminosity of the white dwarf, which leads to a radiation-driven wind. Accelerate the wind, which collide with slower ejecta ahead of it, and emit gamma rays, but in this case, the shocks are adiabatic and not radiative, so we only get some gamma ray, not much of optical, and the whole of optical would be coming from the white dwarf. So can we tell, or can we rule out one of these scenarios? Well, one way is to check if there's any lag between the gamma ray and the optical emission. Because in this case, we would expect that the gamma ray would lead the optical, which is going to take time to be reprocessed and then re-emitted the X-ray would be reprocessed and re-emitted in the optical, so we'd expect a lag from the optical compared to the gamma ray. However, in this case, it's not very easy to say what will happen. But it might be that the diffusion time of the emission from the white dwarf, which emerges in the optical, takes less time compared to accelerating a wind and then creating shock, and then we have gamma ray emission. What did we get from the light curves? Well, it wasn't possible to say anything for the nova assassin 16MA because the resolution of both light curves was not great. However, for Nova Carinae, for the first time we managed to measure a lag, a 2 sigma lag between the gamma ray and the optical light curve of around 5 hours. I'm not going to say that this would rule out this scenario, but definitely would favor the other scenario, that it is possible that a large fraction of the optical luminosity from the nova is coming from shock interactions. Also, we got new star observations around 35 days after the eruption, simultaneously with the optical and gamma ray activity. And we've observed hard X-ray, absorbed as X-ray, that should be coming from deeply embedded shocks. And this also is another point that favors that we have shock interaction that is powering the emission in the nova. You're going to hear all about it from Kiril Sokolovsky on Wednesday or Thursday, so I'm not going to detail into the X-ray observations. But if you want to also know more about X-ray observations during gamma ray emission from novae, please check my student's poster, Alexey Bobrick, who's done a really great job about this. So what we're suggesting here, that the optical luminosity of the nova is powered by shock rather than emission from the white dwarf, or at least part of it. Actually, it's not very crazy. This has been theorized for other transients, such as type 1a supernova shock breakout, stellar merger, TDEs. I'm not expert on this object, but this is usually based on features in their light curves or their spectra. But this is the first time we have direct evidence from unprecedented space observations that it is possible to power an optical transient due to shock interactions. But this is one object. So we hope we get more of this. And now we're living in the era of space surveys. We have Breedt, we have TESS, hopefully more satellites in the future. And actually in 2019, we have one nova erupted in the field of TESS, and we are studying it now. And hopefully more of this chance occurrence will happen so we can really tell if this theory is correct or the other one. So I've just told you about the expectations from these light curves, that we expect that a large fraction of the optical luminosity is powered from the shocks. But did we manage to explain the flares? Because in order to have changes in the gamma ray or optical luminosity, we need to be changing the shock luminosity. And the only ways to change the shock luminosity is either by changing the density of the medium or the velocity of the ejecta. If we looked at the optical spectroscopy, this is how good this nova been monitored by amateur astronomers and by other facilities such as VLT and SALT. And we got really nice coverage of the different stages of the evolution. I'm showing here H alpha. And you can see that we have high resolution spectroscopy from amateur astronomers. And initially, we see low velocities dominating the spectrum. And after maximum, we see higher velocities. But we don't see new velocities with every flare, which is something we should expect and we have seen and observed in other flaring novae. So if the velocity is not changing, it's only changing once after 25 days where it suddenly the emission line broadened a lot. But what is happening here? If not the velocity is changing, what is changing? Well, we naively suggest that the slow torus around the system, which is initially ejected, is not smooth. It is bumpy. It is probably made of multiple shells or spirals. And this is dominating the emission at the beginning in the P-Cygni profile we see. And this is highlight the first part of the light curve. You cannot see it here, unfortunately. And then later on, we have a fast outflow or wind kicks in. And this will start propagating, and at some point, will start going through the slow outflow and creating the shocks, and is responsible for the flares we see in this part of the light curve. And at some point, it will emerge in the spectra as high velocity emission. This will expand. We see it's accelerating by a little bit, couple of 100 kilometers per second in 10 days. But then the light curve show a conversion in the trend. So it's starting to show a change in its trend. And we think that another outflow has kicked in with even higher velocities and has also started shocking the slow outflow and created the other flares. How do you know that? Because we see in the optical spectroscopy that in one day, the emission lines broadened by several hundred kilometers per second. So there must be new ejection at higher velocities. After day 30, the emission is completely dominated by the slow outflow, which I guess will reach the escape velocities and dominate all the emission while the fast wind dissipates. So this was merely based on speculations from the observations we have, but also our collaborators in Columbia University, Brian Metzger and Elad Steinberg, had did some modeling and managed to roughly reproduce the light curves that we see. I'm not going to talk about the models here. And also, based on these observations, we are suggesting that the flares we see in the optical light curve in some novae are indeed coming from shocks. So Jackie is not that confused anymore because now we have at least some answers for some of the features we see in the optical light curves. Do all the flares that we see in the optical light curves of novae come from shocks? You can ask me this question during the discussion. I have an answer for it. Now, throughout my talk, I've been considering that Novae eruptions are an ejection of at least two outflow, a slow dense torus followed by a fast wind. And this was merely based on the radio imaging of the Nova V9591. Is this true? What about this single ballistic ejection? Can we consider that the two outflow ejection is universal? Because a lot of people till today, and I'm one of them, we still believe that it is possible to have single ballistic ejection from especially fast novae. And also from imaging of nova shells, we can see that there is some kind of spherical symmetry, and we don't see evidence for these multiple ejections. And some novae, and some are not. Yeah, so can we consider this universal or not? Well, I always thought that in order to answer if we have both of them happening in different novae, or one of them is universal compared to the other, the answer would come from high-resolution spectroscopy, particularly if we manage to get on the nova before it reached its maximum, so during the rise. In order to do that, we combined effort from different facilities, two agile large telescopes, SALT and SOAR, which are equipped with high and medium resolution spectrographs, and also alerts from Assassin, which has been helping us to find novae very fast. You're going to hear a talk by Adam Kawash later today about the challenges of finding novae. And of course, the priceless work by the community of amateur astronomers. We work a lot with amateur astronomers, particularly AVSO observers, which provide us with very useful and dedicated photometry, which allow us to locate or constrain the maximum of the light curve. And also now we are in days where amateur astronomers are providing us with high-resolution optical spectroscopy. Stella has highlighted the work that has been done by amateur astronomers yesterday, and it's really very useful. And actually, this combination has been a game changer, because for the novae that we managed to get on them before maximum, we found a trend. Here I'm showing spectral profile of Balmer, either H alpha or H beta for different novae. And what we see before maximum is that the spectra are dominated by P Cygni profiles characterized by relatively low velocities. I'm talking about velocity ranging between 200 to up to 1,000 kilometers per second, depending on how fast is the nova. And then after the optical maximum, we see a broader and faster emission emerging. But what is really intriguing is that we can still see the slow velocity P Cygni profile superimposed on top of the broad emission. And this is very important, because we are here getting emission from two physically distinct ejecta components. And this is hard to be explained by a single ballistic ejection. My interpretation is that initially we are getting emission from a dense, optically thick, slow component, which is manifesting as P Cygni profile, and later after maximum, the fast, optically thin wind will emerge and will manifest as broad emission. And we can still see emission from both components. So I would say we can, well, I want to be a little bit conservative, but we can consider that this scenario is maybe more universal than the first one. And I can leave you with my summary. Thank you very much.
Thank you. Questions, please. Let's start here, please.
Thank you. So basically, I agree with you, your conclusions. I have a short comment to explain my question. So similar processes we observe in solar flares. when we have, and we know that these flares occur in a region with a complicated and strong magnetic field, which accelerate particles up to 50% of energy transferred to particles. Some guys say even higher. Then you have a coronal mass ejection and shocks, on which we can distinguish two components at least, so the electrons accelerated inside the flaring region and protons accelerated on a shock in a coronal mass ejection. Some particles comes back to solar atmosphere, heating it and produce additional shock. Okay. So that my question is, it might be the key. So to distinguish, is it similar processes or different, might be polarization. Could you comment on it?
Can you repeat the last sentence, please?
That's just comment about polarization.
Okay. I guess it was a long question. Okay, so so when you're talking about the particle acceleration and the solar corona, this might be a different regime than we have here in Novae. The particle acceleration efficiency assumptions were taken from supernovae, I guess, in this case. What would we learn from polarization? We do spectropolarimetry, but mainly to study dust, and also we might be able to model them and get an idea about the geometry of the ejecta. But how can we use polarimetry to understand the particle acceleration? I have no answer for that.
I mean that we can get some information about, do we have strong magnetic field or not?
So based on the diffusive shock acceleration mechanism, yeah, we have magnetic field that will lead to the acceleration of the particles. That's the assumption.
Then I would expect polarization.
Probably we'll have to do polarimetry then. Yeah, but we cannot also. I'm not sure if we can resolve the shock emitting region with polarimetry.
I might have missed. You already covered. Shock also, in principle, could be possible in the accretion disk also, and as because these sources are giving outflow, often people argue outflows are being triggered by the shock in accretion disk. But your shock is not in the disk, some kind of interface. So my question is that, is it, how are you ruling out there is no shock in accretion disk and outflow is perhaps might be triggered from shock only?
So you're asking if the shocks are maybe happening between the ejecta and the accretion disk of the system.
Right. And
I guess
might have.
Yeah, I guess
which generally people talk about in case of say black hole disk. So
yeah, I don't think so, because the densities and velocities are not that high to create the gamma ray emission we have. So we need higher enough velocities and higher density. I don't think the accretion disk is that high to get gamma ray emission. So we have initial outflow from the actual eruption that is shaped by the binary motion in form of a torus, and then we have shocks later when we have a faster wind catching up with it. But it's not a shock between the ejecta and the accretion disk.
Yeah, but unlike black hole case.
Unlike black hole case, yeah.
So on the flares that you see, Bob Williams had a couple of papers where he detected absorption lines in nova spectra, which he interpreted as evidence for kind of several episodes of mass outflow before the nova eruption. Could that be where your shock runs into?
Exactly. Thank you very much for asking me this question, because I have the chance now to show my other paper that we submitted last year or this year. And here we have another nova in the LMC in 2017 showing multiple flares. But these flares last for 10 or 20 days, and they have amplitude of several magnitudes. And for this nova, what we found that with every flare, we have a new system of absorption features at higher velocities. So we think we have a new ejection of material at higher velocities. Fred Walter have also showed this for two other novae, V5688 Sagittarius and V1369 San. So that's why when I told you, do all flares in novae come from shock interaction? Maybe not. Maybe some of them are due to multiple ejections of material.
I apologize for interrupting you as a co-author and the person who's passionate about Novae, but I feel strongly that we need to recognize the work of people who are no longer with us. So people who did the imaging of Novae shells have suggested that at least some Novae do have this bipolar versus toroidal geometry, and that may not be the case for all Novae though from the imaging, but it's quite a small and interesting number, and so it was talked about already many years ago. So I've been in the field for long enough to remember that.
I totally agree.
Yeah, and the other thing, it's just a language matter, but last week, for instance, I and Koji were at this X-ray conference in Bologna. So the opening of the conference, Günther Hasinger talked about gamma ray novae, and he really means black holes. And lots of other people during the conference also were talking about gamma ray novae indicating black holes. So let's try not to confuse the language.
Gamma ray novae are gamma ray classical novae. They are not black holes. Yeah.
Okay, no more questions? Sorry, please.
Is there any relation between the currents of gamma ray emission in novae and the speed of the nova?
That's a good question. Actually not. I have plots where we try to see the T2, which is the time to decline by 2 magnitude from maximum, compared if the novae are gamma ray emitter or not. There's no correlation, but so far, I guess because it's easier to find them and they have maybe denser ejecta, we see somehow a shift toward slower novae, which lasts in maximum for longer, and therefore the ejection might be even longer. Yeah, but some fast novae also showed gamma ray emission.
Okay. Let's thank our speaker again. Okay, the next speaker, Irma Fuentes Morales, the orbital periods of novae. 25 minutes, please keep 20 to leave some time for questions.
Okay. Okay. Hi everyone. I'm Irma Fuentes Morales. I'm a PhD student in Universidad del Paraíso in Chile, and today I will talk about the orbital periods of Novae. I'm working with Klaus Tapper. He is my advisor in Universidad del Paraíso. Monica Sorotovich, Linda Smith-Bright from ISO, Alessandro Ederoclite from University of Sao Paulo, and Nikolaus Bock, who is present here in the conference. Well, as already we know, the cataclysmic variables are classified into two big groups, depending on the intensity of the magnetic field of the white dwarf. We found magnetic and non-magnetic. And what about the classical novae? Classical novae is a subtype of cataclysmic variables. The answer obviously is not, because classical novae is a cataclysmic variable that report a nova eruption. So, for example, we found the representative intermediate polar DQR is in fact the nova Hercules that erupted in 1934, and the RR Pictoris is a nova that erupted in 1925, and this nova present typical characteristics of the XW sextantis. And by the other hand, for example, Zcamp, the most common dwarf novae, present nova shell. So for that reason, novae are uneven in cataclysmic variables. Well, classical novae, This is the typical parameters, the amplitude, which is the difference between the maximum, which is the correspond to the moment of the eruption, and the minimum that correspond to the magnitude in the quiescent state. It's typical from 8 to 14 magnitudes, and the recurrence time of the eruption has been calculated greater than 10,000 years, and the typical range of orbital period is about 1 to 10 hours. This is a typical light curve, and my thesis is focused in this part of the classical nova. Well, what's happened after a nova eruption? After the nova eruption, the material is ejected into the interstellar medium, forming an extending shell around the CV. And several decades after the eruption, the properties of the host CV is hidden by this nova shell. And for that reason, the brightness decrease to very faint magnitude. And in this part, as I said before, this part is focus my thesis. And the study of the postnova is too difficult because in order to try to recover the postnova, we need a large amount of time in large telescope. So that is a problem for us. In order to understand why the classical novae is important, the most important parameter that delivers clues about the CV evolution is the mass transfer rate. And the orbital period is directly related with the orbital period. Here is, we see the orbital period distribution of cataclysmic variables, and three distinct features in the distribution we can see. We know that the system with periods around 2 or 3 are very scarce. This is the period gap. Most of the systems in CVs are below the period gap, and the number of systems with longer period decreases. But what happens with the orbital distribution of the nova population? This is a comparison between the orbital period distribution of novae with the all CVs. In 2009, my advisor began a project in order to try to obtain in order to try to enlarge the sample of the orbital period distribution, orbital period now in novae. So this is the distribution that he made in 2013, and we can see the most of the novae are in between 3-4 hours, and this part of the orbital period distribution indicate that the postnova has high mass transfer rate. So now I will show some new orbital period from our project. The first one is B2572 Sagittario. The nova eruption was in 1969. The maximum brightness was about 6, and the magnitude now is about 18. This system was recovered by Tapper in 2013, and we obtained 5 light curves, 1 in 2012, and 4 in 2015. And it's possible to distinguish, the light curve shows the orbital hum, and we can see different amplitude. For example, the amplitude in 2012 was about 0.3 magnitude, and 2 years later was almost twice. So we derived the orbital period equal 3.75 hours that indicate that this is a high mass transfer system. Other example is IL Nor. This is a very old nova. The eruption was in 1893. The maximum brightness was 7, and now is about 19 in B magnitude. And this object was observed by Gustav Warner in 2010. They obtained 2 light curves, 1 year apart, and we obtained 4 light curves in 2015 in Las Campanas Observatory with DuPont telescope, and we derived this period, 1.74 hours, which means below the period gap. And it's possible to see that this period fits the Guttav-Warner light curve. Other example is B360 Sagittarius. This nova erupted in 1927, and in a search of stunted output in Novae, Fogg observed this object in the SMART telescope during 2 years, between 2013 and 2015, and we could derive the orbital period that this period is in the period gap. And other interesting result from the same search of stunted output in Old Novae is the confirmation of the orbital period of the period of RS car. Good and Warner derived a period close to 2 hours, and they said that this modulation could be related to a superham instead of orbital period. And if we see the phase light curve, it's possible to see that this is the typical shape of the superham period. So in order to try to prove if this is the orbital of superham, is necessary to perform radial velocity. So with this new period plus the new orbital period since 2013, we made a new orbital period distribution, and the total sample now is 88, and here this is great. This is this gray distribution corresponds to the distribution made by Tapper in 2013, and the white one is the new. And for example, we found six novae below the period gap, which correspond to the 7% of the sample. Between the period gap, we found 12, which correspond to the 14% of the sample. Between 3 to 4 hours, we found the most orbital period, which correspond to 34, and period greater than 7, we found 18, which correspond to 20% of the total sample. And well, all these classical nova have a ball secondary. Also we compare the observed orbital period distribution with a simulated one, and we perform a simulation from binary star evolution code. We evolve the system until the post-common envelope phase, and then we perform the ECAR model described by Traver et al. In 2016, and this is the result. This is the observed, and this is the simulation. Here we see the probability, and we can see the simulation indicate that the most of the system are located above the period gap, between 3 to 6. However, the model doesn't reproduce the peak, the observed peak, to 3-4 hours. When we search the orbital period of in the Ritter catalog, in the Ritter Ecole catalog, we discard 25 orbital period because the orbital period are uncertain. Why? Because, for example, we observed the light curve, and the light curve are showing possible ellipsoidal modulation, or because the light curve was unpublished, or, for example, if the nova has uncertain position. For example, here in the table, double asterisk indicate that the orbital period corresponds to an object that was not identified spectroscopically. And with asterisk, one asterisk, the light curve shows possible ellipsoidal modulation. Here there are examples. For example, this is a possible ellipsoidal modulation, and B1174 present on certain position. Other example is DK lag. The light curves, the orbital period was derived from these two light curves, and the light curve presents a strong flickering. For that reason, it's difficult to say certainly if the orbital period is correct or not. And other example here, even the author said that the length of our longest light curve constrained the orbital period greater than 4.8 hours. So for that reason, we discard, we reject this nova from the distribution. Okay, so like conclusions, our project started by Tapper in 2009, called Life After Eruption, has notably contributed to increase the total number of orbital period, with an increment about 40% of the known orbital period. From our orbital period distribution, most nova are above the period gap, and the period gap virtually doesn't exist in nova. And simulated orbital period distribution is consistent with the observed one, except for the peak at 3-4 hours in the observed distribution. This seems to indicate that the prescription for magnetic breaking in CVs is not the best approximation. And if here there are nova observers, we encourage to to the community to observe these 25 systems. So, thank you.
Questions, please?
What I learned in primary school is that classical novae are novae that have only one eruption. If they have two, they become recurrent novae. Okay? But apparently I'm out of date because you put a time there that even if they haven't erupted again, there is a reason to still call them classical novae. But my question really is, have you included recurrent novae in your analysis?
No.
Or have you compared with recurrent novae what the distribution is?
Yeah.
I think this is very important.
You're right. But in our study, we discard the recurrent novae. But the sample is little small, I think, less 10 recurrent novae. We only focusing in the class with only one up to reported.
So for the last 70 years, the understanding has been that all novae are recurrent. Recurrent novae is just a terminology to address those novae we see observing again, exploding again during a lifetime. You showed our picture of the extended ionized medium in the region of Nova Cygni 72, V1974 Cygni. Of course, that's not the Nova shell. The Nova shell is a teeny tiny dot inside that region, and it was actually imaged with HST. You could have put that beautiful picture there for the Nova remnant. So what you showed has nothing to do with the Nova remnant.
Okay.
I'll talk about it during this talk.
Here?
Yeah, that's not a Nova remnant. Nova remnant is much smaller than the green picture.
Okay. Yeah, thank you.
So are there more novae that haven't been recovered that could be potentially added to that list? Like more old novae where just nobody has looked at it?
Hidden novae.
Well, there's a long list of classical novae, but how many have been actually followed up? Yeah, so like how many of all the...
Out of all stars?
No, of all Catalogue classical novae.
Okay.
What fraction has been ever looked at?
So you recover a novae by studying the quiescent phase, yes? So are there still many other such types of stars? Or do you have any approach how to recover more?
Do you have more candidates? Okay, yeah.
So what would you advise? For example, by, let's say, Gaia data, is it possible? Because they are a lot. Are they enough?
Well, our project is focusing, like, try to from the lowest catalog, try to obtain the certain position of the Nova, and then we try to obtain from the color diagram the possible candidates of the catalog, and then we try to compute from the spectroscopy. So our sample is from that catalog, but we are thinking about...
I'm sorry, can you please turn off the microphone?
Okay.
Thank you.
No? Now? Now. Oh, yeah. Yeah. It's possible more candidate from Gaia and Alessandro Eclipsing. We begin to work with this.
Okay, next question, please.
So, in your simulations, I assume you use a common envelope efficiency, no? Does it so the outcome of the simulations, does it depend on this alpha value? If you're using alpha value, and the second question is, how do you know that a synthetic system undergoes an eruption?
Was performed.
Last question.
Really nice work, your talk. I have a very quick question. You mentioned you obtained spectroscopy. Which telescope you use for your spectroscopy? You might have mentioned that, I just missed it. Which telescope you use for this spectroscopy?
Well, we obtain a spectroscopy in order to try to confirm the nova, and if, for example, if the orbital period derived from the photometry is not reliable, we try to with the spectroscopic variable velocity. So, for example, now we are thinking to apply it to try to obtain the orbital period from time resolved spectroscopy for this object. But in our project, the spectroscopy is important in the phase in order to try to confirm the nova.
Okay, thank you very much. The next speaker is Marina Orio, timing supersoft X-ray sources with NASA.
So, do I need the password if it stops, or shall I just go ahead? This one is without password. It's not burning. We think it's a hydrogen burning white dwarf because the phenomenology is very, very typical. It has a temperature around 500,000 degrees, which is very similar to Novae right after the outburst, when the white dwarf shrinks back to pre-outburst dimensions, and hydrogen burning is still lasting for a while. So it is not always X-ray bright. It has some off states. The period and the cadence and the timing of these off states is not completely clear yet. These off states are probably, they seem to be brief, lasting only a few days, but they're repeated every few months. It has a very high luminosity. It depends on how you fit the spectrum, I guess, but it's a few times 10 to the 37 erg per second, so very close to Eddington luminosity. And we know the distance, at least approximately, because it's in the LMC. And all photons, when you observe it in X-rays, are below 0.8 keV. The binary period is just a little over a day, and it has a very luminous accretion disk that seems to prove that it's accreting at a very high rate. And that high mass accretion rate would be necessary to avoid outbursts, because all the energy can be radiated. Although this is a little bit of a conventional theory that was refined later on, and it seems that in any case you need to have some off states and on states, or you have to have some oscillations that you would never have very steady burning, completely steady. So it's an interesting source with a little bit extreme in that it must have a very high mass accretion rate, and it's the only one, not the only one of only 3 or 4 that have been observed without significant changes, maybe 5, for 40 years, basically, since Einstein. So there is another period in addition to what I'm talking about that is also detected in X-rays, but it has been detected only in some observations of about 38 minutes. Proposed binary models. So if you want to assume that it's really steady burning, you need 10 to the minus 7 solar masses per year, which is very, very high mass accretion rate. And if you assume that the typical way to obtain an estimate of the mass is to look at the helium-2 line at 4686 angstrom in the optical spectrum, because it's supposed to be very close in the inner disk, very close to the primary. And the radial velocity would indicate a black hole with a mass of 6 solar masses. But it has been argued already a long time ago that because this line is not eclipsed even partially when the disk is eclipsed, it must be emitted in a wind, that it's not representative of the motion close to the compact object. So Van den Heuvel et al. In 1992 had a famous model that was proposed also as a model for type 1a supernovae progenitor because of the high mass accretion rate involved and the high mass of the white dwarf that was necessary to fit this model. And they can fit the data with the nuclear burning massive white dwarfs, definitely above 1 solar mass, possibly about 1.2, with a secondary of larger mass. So they have secularly unstable mass transfer on a thermal time scale of the secondary that has limit cycles. And for 1,000 years, 10,000 years, depending on the system, you can have more or less constant mass accretion rate, and then it would stop. And then it would start again after a very, very long time. So the mass of the white dwarf would increase, and it would go towards the Chandrasekhar mass. There is another way to interpret this, and it's called the accretion wind evolution model, Hachisu and Kato, which actually fits well another supersoft source that has been observed extensively in the Magellanic Cloud. So the evolution is self-regulated by a periodic high wind from the disk, and the common envelope phase is completely avoided. The disk periodically becomes flared and hides the burning white dwarf, and that would explain the off states when you don't observe it in X-rays anymore. The problem is that we don't have good timing of optical and X-ray observations, and we're not completely sure that they're exactly anti-correlated. It would become very optically more luminous when the X-rays are suppressed. We're not completely sure yet that this is the case because of the difficulty in synchronizing the observations properly. So, and there is a decline in optical luminosity for 200 days, repeated every 450 days, which is independent, however, from the cadence. It doesn't seem to be the same cadence and duration at all as the X-ray off states. So there is still work to do, maybe with Swift, and if closer monitoring can be done. This is the extended nebula I was talking about. It shows at least that this nebula, that this white dwarf has been very, very hot to ionize the interstellar medium at such large distances. So it has been very hot for a very long time. The thing I'm going to talk about is this 67 seconds oscillation. It was discovered by Alida Odendahl et al. In 2014. So they discovered it in the XMM Newton light curves of Cal 83. Many of these short period oscillations in Novae and supersoft X-ray sources were discovered thanks to the long observations needed to obtain grating spectra. So Chandra and XMM pointed at them for a very long time, and it was easier to discover the oscillations, although some of them are so clear that even with 1,000 seconds with Swift, you can recover them easily. And I showed that there are other cases like this. But the funny thing is that Alida Odendal and colleagues measured a 3 seconds drift in this period, which is not very easy to explain. So the period didn't seem to be constant all the time. It seemed to have a varying amplitude, but even and it was not always measurable. So sometimes the amplitude was so low that it wasn't recovered for a while, for a few hours. So what they did, they attributed the period to rotation, and I will get back to it and explain how they explained the drift. The important thing is that there are pulsations of tens of seconds in other supersoft X-ray sources. And it seems to be a common phenomenon. Usually it happens in post-novae, in the supersoft X-ray source we see after a nova, where we're pretty sure that we're observing nuclear burning on the surface of the white dwarf. So there is a list of papers. Notice that there are 35 seconds, two 35 seconds period, one of 33 seconds. Then we have another supersoft source in M31 with a 212 and 13 seconds period, and other novae with slightly longer than a minute periods. So right now we have just, the Swift colleagues, and I also collaborated, but they did most of the work. They discovered a period of only 83 seconds in V38-39 Sagittari. So this seems to be a common phenomenon, and what is telling us, that's an interesting question. So it is known that post-AGB stars and newly born white dwarfs that still have some hydrogen burning seem to have pulsations. Usually, so a few are known, but also theoretically you can show that you must have some kind of pulsations. So those that have been measured are the order of 300, one is 300 seconds, I think. And a reasonable explanation has always seemed the non-radial G-mode oscillations occurring because of the so-called epsilon mechanism. You know that there are some of these, in very hot white dwarfs, we think there are G-mode non-radial pulsations because of the opacity. That's called the K mechanism. But it can also happen with much shorter time scales because of the burning itself. If you have steady burning for long enough, it can create internal gravity waves, and you will measure these pulsations. So there were studies before they were discovered in Novae even, Corsico, Kawalar, and only recently, so last year, my colleague at Wisconsin, Rich Townsend, worked with Bill Worf. You know him as a great expert of Nova modeling. He did his PhD in that, and they worked also with Lars Bilsten. And they found out that the periods, it's very easy to predict. I don't think it's very easy, but I mean, it's quite straight, quite sure, quite certain that you can predict the periods, depending on the physics of the systems and how the burning is happening and the mass of the white dwarf and the temperature of the surface. And they predict that these periods should not exceed 10 seconds. Now, could it be rotation? That's the other question. So let's see, I was just looking, you can correct me if I don't have all the facts straight, but if you have an isolated white dwarf, usually the period you measure is only, the shortest are just slightly below an hour. And theoretically, you have two possibilities: the extreme possibility that you conserve all angular momentum, and then you can go down to, I think, 300 seconds or something like that. And if instead, if you assume that it rotates like a solid body, stellar evolution considerations show that it has to have a period of at least, that is not shorter than 2 days. But in the binary, we can go below this few hundred seconds period, and the rotation velocity from at most 600 kilometers per second can go up to 2,000 kilometers per second, which would actually allow the white dwarf to be more massive than the Chandrasekhar mass by 5%. And if that happens, you're still, even with 10 seconds, you wouldn't be above breakup velocity. The breakup velocity is only of the order of 1 second. So Alida Odendahl and collaborators suggested that we are detecting the rotation period, but the decreted envelope is not synchronized with the white dwarf, and so it's not quite co-rotating, which is a little bit of a strange explanation. I'm not sure that the stellar evolution experts would agree with that, but you know more. And so we decided to observe it with NICER on the space station. So NICER is just a big bucket that collecting X-rays. It's not an imaging instrument. It has these 56 X-ray concentrators in a field of about 15 by 15 arc minutes. And you have to have a relatively non-crowded field with X-ray sources, or at least no other supersoft sources around 3 minutes or so. It was studied basically mostly for neutron stars. Neutron stars, for instance, thermally emitting neutron stars can have also very soft spectrum, so it's sensitive in the soft part of the spectrum. And you can do really good timing with it, but you cannot observe continuously for a long time. So there are stretches of at most 1,000 seconds or so. Here, this is an image in which they show when they always have these, during the night of the instrument, they say, when they cannot observe, they move the instrument. And so they have these tracks of X-rays that they have recorded, and these are the luminous sources, and so it's their flagship image, because it's cute, it's strange and interesting. So I'm not going ahead. Oh, how was I moving ahead? With this, okay. So we've been studying recently a very similar case of Novae LMC 2009 that has this 33-second period, and Joannes and collaborators discovered. Very close, of course, to the 35 seconds periods of the other two Novae. One of them is the famous RS Oph. So also for this Novae, LMC 2009, in the XMM data, we try to investigate whether the period varies or other periods where different periods were simultaneously present. It's also possible that the period was constant, but the amplitude varies, and so you have a sort of false beat. So we came to the conclusion that there is a real drift in the period by about 0.4 seconds for this nova. Is it the same for Kali 83? So the problem is that implications of the drifting period. So I don't know if I showed, I don't know if I have a slide here. Oh, let me go back. I was talking about another possibility for the interpretation. So I'm going. And another interesting possibility that had been put forward for RS Oph was that of a precessing jet and blobs in this jet that reflect the super soft polar cap. So it was invoked by Labovitz et al. In 2016, and RS Oph really had a slow jet. So this would explain the varying periods, and in fact, in RS Oph, when we think that mass accretion stopped, but the nova remained a supersoft source and was cooling for a while, the period seemed to stabilize, and it wasn't varying anymore. So we tried to see with NICER whether the period was varying. These are exposures were done summing up different times during one day, and these are the periods that we recovered. But then we found out that, for instance, this different low significance period was included a period of high background that should have been excluded, and so we're working at that, and I'll explain maybe if there is time why it's not so simple. From those 6 exposure of vary length, these are the power, the Lomskargel, if you're familiar with timing, so they show the frequencies that we can measure with this method, Lomskargel method. And then we went into the shorter exposures. Some of these exposures during one of these days, they were done even 10 times. So we looked at these short intervals to see, considering that perhaps the period doesn't vary over a very, over, let's say, 800 seconds. But we weren't able to measure the period with sufficient precision to determine with certainty whether it really changes or not. And this is really critical to understand whether it's rotation. So one thing that has to be said is that Cal-83 probably doesn't have any significant mass outflow, so it's not a nova. So how can you explain it like we try to explain RS Oph? So what we're doing now, we're doing technical stuff. We're trying to work with the nicer team to improve the background. The super soft background can be high at certain times. And we want to determine when it's really varying. In one nova that had V4743 Sagittarius, in X-ray, you can actually measure the rotation period, much longer than this, over 20 minutes. It was detected with XM Newton and Chandra, and we thought that there was a drift, but it turned out that there wasn't. So there is a paper by Andrei Dobrotka, who is an expert of timing, and we want to see if the same is true. So a period of varying amplitude sort of mimics the same result as a period of varying duration. So Andrei has done some simulations with the results we have up to now, and he has actually done 1 million simulations, so with varying period or just a constant period with varying amplitude, and he compares them with the data, and here in the bottom are the chi-square, the residuals, and you can see that the hypothesis of constant period produces better results, matches the observed periods with nicer better. Although we still have to correct some of these periods. So I'm done. I already talked about LMC 2000, and I'm going back here. And going back, I wanted to go forward. Things to do. So we're working at technical stuff like improving the period. There are these sort of flares in the background due to South Atlantic anomaly or the polar horn region. And this was also an experiment because this source is so luminous and it's not excessively soft. And in the future, we want to work on other of these super soft sources, also some for which these periods have not been measured yet. And so that's what we would like to try to do, to try to understand whether we can get to the root cause of this strange modulation, whether it's really rotation, and is it really varying, and is this because of mass outflows, or what is the reason? And so it's still work in progress, but I thought it was interesting enough to show it even at this stage. So I'm done.
Thank you. Questions? There is one here.
Thanks. Marina, have you thought of doing simultaneous optical observations during these nicer things to see if there's any correlation between optical and
yes,
X-ray?
that would be the next stage. It's not so easy to, they observe when they can.
It's very easy with salt. We've been doing it.
With nicer?
Yeah.
Okay, let's do that. Okay, let's talk about it. Definitely.
More questions?
Because they really observe when they can, and also Cal-83 has off state. So we had to cancel the nicer observation after an attempt with Swift, and then they had also a trial exposure. So there are a few problems, but yeah, we can talk. We should talk about that, definitely.
No, we can think about it.
Yeah. Right. Okay. Definitely.
No more questions? Okay. Thank you.
Thank you. Thank you, Gagik, for the computer.
Hello, my name is Kiril Stoyanov. I'm from Bulgaria. And I would like to thank the organizers for the opportunity to present to you our latest results based on optical observations, both photometry and spectroscopy, of the symbiotic recurrent nova RS Oph. An inspiration for me to prepare this presentation was the fact that RS Oph should experience new nova outbursts within the next couple of years, and I hope that I will raise the attention to this object. Okay, I know that there is an expert on symbiotic stars here, and I will start with a short introduction. What are symbiotic stars? It's a binary system. Long period binary system that consists of a red giant or Myriad type variable, and generally a white dwarf, but in some rare cases it can be a neutron star, main sequence star, or a subdwarf. Because of the accretion, the accrete material reached the surface of the white dwarf, and the system experienced nova outburst, and in some systems are detected more than one outburst, so we call these systems recurrent novae. It is believed that the most of the novae are recurrent novae, but with a very long period between the outbursts. The most up-to-date catalog of symbiotic stars lists, it is published this year, it was published this year, lists 257 symbiotics in our galaxy and 66 extragalactic symbiotics, but this is in conflict with the theory because the theoretical models predict a number of, let's say, 100,000 symbiotics in our galaxies. There is a different models, but the predicted number is of that order. And some, as I said, some of the symbiotics are recurrent novae, some of the symbiotics novae are recurrent novae. There is a 4 symbiotic recurrent novae in our galaxy, and as far as I know, 1 extragalactic. The galactic recurrent novae are S-type, which means that the donor star is a red giant. As far as I know, the extragalactic symbiotic recurrent nova is a D-type, maybe Christian can confirm, which means that the donor star is a Myra-type variable. The explanation of this fact is the higher number of S-type symbiotics that are recurrent novae is that in the S-type symbiotics, the orbit is not so, it's, let's say, the distance between the components is of order of 1 astronomical unit. The orbital periods are between 1 or 2 years. And because D-type symbiotics harbor a Myra-type variable, the orbits are much wider and the accretion rate is lower than the S-type symbiotics. So we will continue with RS Oph. It's a symbiotic that consists very massive carbon-oxygen white dwarf orbiting around M2 red giant in a circular orbit. The orbital period is more than 453 days. And this system experienced 8 nova outbursts till now. The last one occurred in 2006. And after the nova eruption, the optical flickering from the system disappeared because the nova blast from the nova outburst destroyed the accretion disk. The accretion disk is the source of the flickering, the optical flickering. And the optical flickering appeared again more than 200 days after the outburst when the system creates a new accretion disk. The next outburst, according to Bradley Schaffer, should occur within the next years. Okay, I'm sure that Simone will reveal the mysteries of the flickering in his talk later this week. And because I don't want to spoil, I will mention only a couple of words for the optical flickering. It's a stochastic photometric variation of a timescales of a few minutes. The source of the optical flickering is either the bright spot or the boundary layer of the accretion disk or the disk itself. Among the symbiotics, there is 11 symbiotics that are flickering active. Okay, some authors prefer not to include Z Andromedae in this list because it is believed that the fast variability is caused by the rotation of the white dwarf, but I am following the work of Jennifer Sokolowski and her remarkable paper from 2001, and I am including this object among the sources with the fast variability. So RS Oph is among the symbiotics that are flickering active, and we decide to observe in optical bands this object and to try to calculate or estimate the physical parameters of the flickering source. Here you can see some examples of flickering. This is RS Oph, another symbiotic CH Cygni. Interesting thing that CH Cygni lost the flickering activity in 2010, and the flickering appeared again 4 or 5 years later. But these are observations before this episode from Liverpool telescope, I believe. And here you can see a flickering, example of flickering from a cataclysmic variable, and V Lyrae. These are just examples. We use 5 telescopes to obtain the observations, 4 in Bulgaria and 1 in Spain. We use mainly BMV bands, optical bands. Here on the left panel you can see the light curves in UBV are I bands, and you can see that flickering is present in all bands. And on the right panel are only B, V, and the color B minus V. We use only B and V in our case. Here you can see the color magnitude diagram. Here is the color B minus V, and this is the magnitude B magnitude. And as you can see on this left panel, the system becomes bluer when it becomes brighter. But when we subtract the red giant and leave only the hot component, the white dwarf, you can see that when the hot component becomes redder, it becomes brighter. Okay, according to Albert Brook, we can separate the light from the flickering active stars on 2 parts: a constant and a variable. This is the flickering. And in order to calculate the flux of the flickering, he proposed a method that he used the average flux and the constant light. Later, Thomas Nelson and his collaborators proposed it's not an upgrade, maybe an addition to this method, a new method. They proposed using the maximum flux in order to calculate the flux of the flickering source. We use both methods in our case, and there is no difference in the flux of the flickering source. As you can see here you can see that there is no difference. This is the calculation using the Brooks method. This is the calculation using the Nelson's method. There is no difference in the colors. So we use these colors to calculate the temperature of the flickering source, and later to calculate the radius and the luminosity of the flickering source, assuming that the source is spherically symmetrical. For the temperature, we have 2 quantities, so calculated by Brooks and Nelson's method, and we have the radius of the flickering source and the luminosity. It is interesting to compare our temperature with the temperatures of the bright spot of some cataclysmic variables, and as you can see that they are comparable. So we think that the flickering source in the case of RS Oph is the bright spot. Another interesting thing is when we try to compare RS Oph with its sister system, Tychorone Borealis. It's very similar, another symbiotic recurrent nova that should experience nova outbursts within the next years as well. As I showed you, the flickering is detectable in all photometric bands in RS Oph, but in case of the Tychorone Borealis, it's only visible and detectable in UB and V bands. Here, you can see examples for the amplitude of the flickering in the red bands R and I. The amplitude of the flickering in RS Oph is greater than 0.2 magnitudes, and in the case of Tychorone Borealis, it's really low, almost undetectable. Okay, T Coronae Borealis is X-ray source, and the X-ray emission is delta type according to UNA classification, which means that the X-ray emission comes from the boundary layer of the system. RS Oph is a faint X-ray source, and according to Professor Mukhopadhyay's paper, it points for a missing boundary layer. So probably in the case of RS Oph, the boundary layer is optically thick, completely optically thick. And in this case, the radius of the source of the flickering in the optical bands could represent the radius in which the X-rays are generated from the boundary layer and proceed in the inner parts of the disk itself. So this probably points again for a bright spot as a source of the flickering, optical flickering. Here I will stop with the photometry with the short conclusions. We calculate the core and the cores and the physical parameters of the source of the flickering. The temperature is comparable with the temperature of the bright spot with some cataclysmic variables, and probably the flickering is coming from a bright spot, and as you can see previously, the temperature is more or less constant. So the size, the radius of the bright spot should increase when the system is getting brighter. Now I will continue with the optical spectroscopy, high resolution optical spectroscopy. These are preliminary results. We start to observe RS Oph and T Coronae Borealis a couple of years ago with our new shell spectrograph at Trojan Observatory called Espero. Our idea is to collect data before the outburst and to compare and to follow the evolution of the emission lines before and after the outburst. In addition, we have some spectra from Ferro spectrograph from the 2.2 meter ISO telescope at La Silla. And we compare this spectra obtained before the last outburst with our new data. As I said, this is not a published data, it's preliminary. We have only 5 high resolution spectra till now from 2017. And I will go quickly on some interesting lines or regions to show you what happened and to show you the comparison between the spectra before the outburst and after the outburst. This is the H alpha line. Interesting thing that the H alpha line is have double peak structure, and the H alpha has 2 components. Unfortunately, here you can see only the narrow central component here. But if I scale, unfortunately I didn't do this. If I scale properly, you can see a broad component with high velocity up to more than 1,000 kilometers per second. The broad component is very variable. In fact, in the narrow component, the absorption part here, or the dip, is very variable as well. Here you can see that the equivalent width of the narrow component varies from -55 to -75 angstroms. The upper spectra are O2 from Ferros, and the down spectra are O2, and the upper are the new obtained spectra. We will continue with another Balmer line, H beta. Very similar structure, double peak structure. H gamma have double peak structure as well, but the absorption part is going deeper under the continuum in H gamma. This is the region of the oxygen wine line at 8446 angstrom. You can see some calcium-2 lines. The profile of the oxygen 1 line is double peaked again as well. Here you cannot see, you should trust me. but it has a Dao peak structure, very similar to H alpha. This is the oxygen 1 triplet, and it looks very different from the previous oxygen 1 line, which means probably that different mechanisms are acting for this emission lines of the oxygen. Maybe in one of the cases this is the Lyman beta fluorescence. I'm not sure. This is the helium-1 line, and the helium-1 line is not with a Dao peak structure. It's a single peak structure, which means that it is formed on a different part of the nebula of the system. And this line is very variable. I try to search for evidences for helium-2 line, but there is no hints, probably because the line is formed in the accretion disk, and because of the inclination we cannot see directly the accretion disk. And something like a conclusion from the spectroscopy, as I showed, the Balmer lines, all Balmer lines in our spectra have a double peak structure. Probably the oxygen 1 line at 8446 angstroms is excited by the Lyman beta fluorescence. There is evidence for forbidden oxygen lines, forbidden in oxygen 1, but no the famous oxygen 3 forbidden lines. Speaking about the helium lines, they have a single peak structure. There is no detection of helium-2, and also there is no detection of Raman scattered lines. And for me, the most important conclusion from the spectroscopy is that the spectra looks really like the spectra from 2004, 2 years before the last outburst. And thank you, and I hope this is thank you in Armenian. I'm not sure I used Google Translator.
Most of the lines that you are showing are typical of an accretion disk. Are you sure these are nebular or come from the accretion disk? Also, you show a lot of flickering, which is also a normal feature of accretion disks. Huh?
There is accretion disk in this. There is an accretion disk, but these emission lamps are formed from the stellar wind and the nebula of the system.
Okay, so
because of the inclination of the system, we cannot see in the spectrum the accretion disk.
So strictly speaking, this is not a symbiotic star. It's a recurrent typical nova.
Symbiotic recurrent nova.
Okay.
I wouldn't be too sure to say from the colours that it was definitely the bright spot that was flickering rather than the accretion disk. I'm not saying it's not the bright spot, but accretion disk can be quite hot too, and so I think it would be difficult to judge just on colours alone.
Yeah, you're right. Thank you.
You are right about the 018446. This is fluorescence line, so this should be a Lyman beta fluorescence. But I guess also from the ratio between the 8446 and 7773, we might have an idea about the density of the ejecta. I'm not sure, but we can chat about this later. We said we want to chat about your results, so we can do a...
Okay, thanks, we can, yeah.
Okay. And the last talk of this session.
Yeah, I changed up the topic of my talk a little bit. I will talk about dwarf novae versus novae, but I generalized my talk a bit to talk about the current state of the galactic nova rate and how all-sky surveys like ASSASSIN are helping us estimate it. So, okay. Let's start with why is understanding the galactic nova rate important? Well, first of all, classical novae are thought to contribute significantly to the chemical evolution of the galaxy, producing isotopes like lithium-7, sodium-22, aluminum-26, and nitrogen-15. Novae are also thought to be the progenitors of type 1a supernovae, as other people have mentioned. Understanding novae is important for understanding the star formation rate of the galaxy and understanding close binary evolution. And we really don't understand the mass of our own galaxy all that well, and to first order, the nova rate should trace the mass of the galaxy. So before I talk about how we find novae, I want to talk about how many novae we expect to find. So people have been estimating the rate since the 50s, and you can see the estimates are very diverse, as low as 11 and as high as 260. And there's really two methods we use to estimate the galactic nova rate, the galactic method and the extragalactic method. So I want to talk about and explain those two methods. So the first, the extragalactic method, is just simply looking at a nearby galaxy, estimating the rate there, and then converting it to our own. And then the galactic method, which you assume some complete sample of local novae, and then use that to extrapolate to the entire galaxy. So there's recent work, a paper in 2017 by Shafter et al., where they use both of these methods to estimate the galactic nova rate, so I want to summarize that very quickly. So recently published rates of M31, the nova rate in M31, range from 65 to as high as 106 per year. The low end was before we knew about this sample of faint and fast novae, which are exactly what they sound like. They're fainter than other novae and they evolve much more quickly, so they're probably easier to miss. So if you include those, other studies have found the nova rate in M31 to be as high as 100 per year. So we don't know the mass ratio of the galaxy to M31 all that well, but we do know the K-band luminosity ratio, which should trace the mass difference. So Shafter estimates that the mass ratio to the galaxy to M30, or the K-band luminosity ratio, is about 3/4. So putting all this together, we'd expect the galactic nova rate to be about 50 to 70 per year. So the other method that we use to estimate the galactic nova rate is the galactic estimate. So this is where you take some complete sample of local novae and then extrapolate to the whole galaxy. So the first question is, how do you know when you're complete? So to figure this out, here's a plot of a cumulative rate distribution as a function of the peak apparent magnitude. And what they did is they compared this distribution to what you would expect from a uniform distribution of novae, which would follow this line. But we wouldn't expect novae to follow a uniform distribution. Novae like to go off in the disk. We would expect it to more follow a disk distribution, which is this line. And you can see it follows this line to about second magnitude. So this is where Shafter estimates that we are complete. He also considers scenarios where we would miss a significant fraction of second magnitude novae. So second magnitude is very bright, but if it went off, if a second magnitude nova went off behind the sun, you could possibly miss it. Or just because light pollution is becoming more of a problem, naked eye astronomy is kind of dead and you could possibly miss it. But he considers that we're complete at second magnitude all the way down to about 40% complete. And so what he basically does is he runs Monte Carlo simulations of novae in the galaxy, distributes them as with a bulge and disk component. He considers galactic extinction. And he says the most likely estimate of the global nova rate is when the complete sample of the brightest novae, his simulated number matches the observed, which there have been 7 novae that have reached second magnitude since 1901, and there hasn't been any since the 70s. So that is sort of evidence that maybe we are missing the brightest novae now, since there hasn't been one since the 70s. But here are his results. So this is the complete distribution as a function of the peak apparent magnitude. And you can see that it does match down to second magnitude. This is the observed rate. And he says from his most plausible model, we would expect anywhere from 30 to about 80 novae per year. So both of these estimates are consistent with one another. We'd expect maybe 30 to 80 novae per year from the galactic estimate and the extragalactic estimate. But how many novae do we find per year? So here's a histogram of the number of novae discovered per year since the 1900s. And you see during the 20th century, we only found a few novae per year. And it seems like maybe we got a bit better in the 21st century. But even on our best year, 2012, I stop at 2015 for reasons I'll make more obvious in a second, we only find 14 novae. And on average, we find 7 or 8. So the obvious question is, where are all of these novae that the models predict? So let's look at where novae go off in the sky. So here's an all-sky map. And you can see novae really go off anywhere in the sky, but they really like to go off in this region, and there's some structure here. And if you put this in galactic coordinates, it makes a lot more sense that novae like to go off towards the galactic center and in the plane. So I want to reiterate what Stella talked about yesterday, is that we really rely on citizen scientists and amateur astronomers to find novae for us. Until recently, they've really found almost all of the novae. And they do a really good job of finding novae and finding them quickly, but with this method of finding novae, it's impossible to know our selection effects and where we're biased. So we really need a more systematic way to find novae to figure out why and how many novae we're missing. For example, OGLE, which observes the galactic center, will recover novae that the amateurs have missed. So we know we are missing novae. So what do we need to try to find a large fraction of novae? So we really need an all-sky survey that especially observes the galactic plane and towards the galactic center. We don't need a big telescope. We don't need it to be very deep. Novae should be very bright in the galaxy, but we need relatively high cadence. So you can see that the distribution of Schafter's models really falls off at about 14th, 15th magnitude and flattens out. And there is this population of faint fast novae that have T2 of about 10 days. So if you don't have nightly observations of the sky, you might miss this type of nova. So there have been surveys like exactly what we need. For one example is Assassin, the all-sky automated survey for supernovae, which is we at Michigan State are members of. So they observe the entire visible sky down to 18th magnitude nightly. They have 4 facilities in Hawaii, Chile, Texas, and South Africa. The field of view is 4.5 square degrees, and their pixel scale is 8 arcseconds. So here's a sky map of their fields in the past year, and you probably can't read the numbers, but the pink fields were only observed about 300 times a year, and the yellow fields were observed 600, and their most observed fields are observed over 1,000 times. So if it's not cloudy at any of these facilities, they really are going to observe the whole sky every night. So the primary science goal of Assassin is in their name, is to discover supernovae. And for this reason, before 2016, they avoided observing the plane. And they were very successful. They've discovered over half of the bright supernovae since 2014. But since 2016, they have observed the entire sky, which is exactly what we need to find novae. So since here's an example of an alert that we get from CV candidates that Assassin sends out. So Assassin is an image subtraction survey. So here is a reference image of a field, and then each one of these is an observation of the same field on a given date. So this dates back to August. And then you can see there's nothing in the field until Sunday night, I think, September 14th. There is some source here in the center that wasn't there in the reference image or any of the days before. So this was a nova that went off Sunday night that we got alerted about with Assassin. So it is doing its job. And actually, the amateurs beat Assassin to this source, but we still did get alerted about it. So how many novae would we expect to find with a survey like Assassin? So Assassin is magnitude limited down to about 18th, but we don't necessarily check all of the sources that deep because there's a lot of artifacts. So I get alerted about everything down to 15th magnitude, and maybe the people at Assassin check down to 16th, 17th. But if I want to be conservative, I'm saying we're checking everything down to 16th magnitude. And from Schafter's models, we predict that we would find about 90% of the novae in the galaxy. This is including extinction. So this is about 40 or 50 novae per year. So how have we done since 2016 now that Assassin has observed the whole sky? Probably most of you in the room already know this, but since 2016, in 2016 there were 11 novae discovered, in 2017 there were 7 novae discovered, 2018 there were 15 novae discovered, a record but still not what we were expecting, and in 2019 so far there are 4 novae discovered. At least there were when I wrote this talk, but since there was one discovered Sunday night, we're now up to 5. And it's not like Assassin has put amateurs out of their jobs or anything. The discoveries are by a mix of Assassin and other all-sky surveys and amateurs. So for example, these are the novae discovered this year. Only 1 has been discovered by Assassin, 3 by amateurs, and I'm including the recurrent nova that went off last month. And then there is this Gaia 19 DUM, or what they're calling Dumbledore, this faint, highly redded nova that Assassin and the amateurs missed. This nova was in the Assassin data, but because it was so faint, they didn't check the candidate. So this is really telling us that amateurs and Assassins still aren't enough to recover most of the galactic nova. We might have to use a survey like ZTF to go even deeper. So what's going on here? Schafter would predict that we'd discover 40 or 50 novae per year with a survey like Assassin. Why are we still missing a large fraction of galactic nova? So one possibility we considered is that they're detected by Assassin, but they're either mischaracterized or not followed up. Another possibility is that interstellar dust is playing a bigger role here than we expect. And then the last possibility we thought of is that they're just not detected by Assassin for any reason. And we still can't rule out that our expectations are way too high, that the galactic nova rate could be closer to 10 per year. So I'll elaborate on a couple of these. So this is a really busy plot, but it's the cumulative discovery rate of novae still as a function of peak magnitude. So the red line is what Schafter predicts from his models, and here are the discovered novae from 2018 to 2017. And one thing I will note is that at every magnitude, even at the brightest end, the discovery rate is still lower. But we can also add the Assassin contribution to this plot. So this is novae plus other CVs, mostly dwarf novae. And you'll notice at the lower end, we really start to get a ton of Assassin discovered CVs. So when I'm talking about things that are maybe mischaracterized or not followed up, there's just too many sources down here to get spectra of all of them to try to classify them. We can probably assume most of these are dwarf novae, or we just have an outburst on the accretion disk and not a thermonuclear runaway on the white dwarf. But we need to figure out a way to decipher between all of these dwarf novae and novae. So this is what we're working on right now. So Assassin has over photometry of over 4,000 CV candidates in their database. So we can combine these light curves with photometry from pan-stars and Gaia, and this is going to allow us to study things like their outburst amplitude, the decline time, the quiescent colors, and the distances to the CV, especially from Gaia. So we're looking for some parameter space that is going to separate the dwarf novae from the classical novae. In most cases they should, but CVs are really a heterogeneous sample, and we're looking for a parameter space that is going to separate these in most cases. So the other possibility I talked about is that interstellar dust is obscuring novae more than we expect. So Schafter included dust and extinction in his models, but he did it simplistically where just the extinction would fall off exponentially as you get away from the plane. So here is the Baystar 3D dust map, which uses photometry from pan-stars and 2-mass and uses distances to stars from Gaia. So they have this 3D dust map where we're bobbing up and down in the galactic plane here, and you can see that the dust isn't simple in the galaxy. It's very clumpy, and depending on where a nova would go off, it could get obscured way more than you expect, and we could possibly miss it. So this is going to allow us to model the expected nova rate better. It's hard to see on this, but this is just another visualization of this. As the distance goes up, how much reddening and dust are you running into? So this is from 0.1 all the way to 10 kiloparsecs. So this is going to allow us to do a 3D modeling of distributing novae in the galaxy and seeing how much they're obscured by the dust. So since 2016, Assassin has observed the whole sky, and from models we'd expect to find between 30 and 110 novae, depending on how complete you think we are for the brightest sample. But since 2016, we've discovered maybe 10 per year. So what's going on here? Are we still missing the novae for any reason, or are our expectations too high? And this is the question I'm going to try to answer for my thesis at Michigan State, working with Laura Chomiak. But thank you for listening.
You know that many amateur astronomers, mainly from the East continent, the Asia, I don't want to name the country, they have a trend to look for SU Ursa Majoris stars, for looking for super humps. So would it be possible that this is creating a bias, because they're looking for very fast variations?
Yeah.
So is there any way that you can convince them to make a more broad follow-up?
From what I understand, if there's evidence of super humps, that means it's a dwarf nova and not a classical nova. So I think that is good evidence, and we wouldn't have to get a spectrum of it to classify that object. So I think that is a good way to classify if it's a dwarf nova, just for the evidence of super humps.
Hi, two comments. The first one is, at some point about the Gaia nova, you said that the amateurs missed it.
Yeah.
Now, remember that these are people that dedicate their free time.
Yeah, I don't want to...
We missed it.
I saw that too. Right. Assassin also missed it. No, I don't want to insult it. I mean, it's really faint.
So
my point was that it's really faint, and we maybe need bigger telescopes than just amateurs or Assassin to recover most of the novae.
And the other small comment is this thing about using the 3D dust map. That's totally the way to go.
Yeah.
You were aware of, there is a 3D dust map of the galactic plane already, which was done by Stuart Sale.
No, I'm not aware.
IFAS data.
Okay.
So yeah, you should.
Okay, yeah, I'll look into that. Thank you.
If the cause for the discrepancy between the observed and the estimated number of nova is the extinction, do you expect the fraction of systems that you find to be dependent on the distance?
Yes.
It's something that can you check that?
The problem with, it's hard to get the distances to novae. So dwarf novae should definitely be all local, but novae, their in quiescence are hard to detect, and we don't know about them. So, sorry, what was your question again?
So the fraction, if you go deeper into extinction,
yeah.
you should be seeing less novae. So my question is, if you come closer to, I mean, if you do all the fraction or the number of systems that you find as a function of distance, if there is a decrease as soon as you go further away.
So you're saying in the known sample of novae, do we see a decrease?
If you see this.
I'm not sure how many distances to novae that we know of. I would guess that'd be the case, but I'm sorry, I don't know how the distribution looks as a function of distance.
So maybe something worth looking at.
Yeah, definitely.
Hi. In a previous paper, it was referring to crowding as being an issue with Assassin.
Yeah.
which is when I think you might see a brighter object in the same pixel, and therefore you would miss the nova. To what extent do you think we're losing a nova because of crowding?
That keeps me up at night. Yeah, I am worried about this. Assassin has 8 arcsecond pixels, which is a massive problem. And for their apertures, it's two pixels, so it's 16 arcseconds. So yeah, I am worried about just novae like to go off in the plane and towards the galactic center in crowded fields. Is it so crowded that we would just miss it? And I'm not sure how to test this. We would have to somehow go into the Assassin and try to simulate this. But yeah, that is something we're thinking about and we want to look at.
No questions?
It might be a silly comment, but related to this question, wouldn't difference image, like even if it's crowded, wouldn't difference imaging still recover these things because they're so bright?
It should, but the subtraction doesn't do as good of a job in a crowded field. It's hard to subtract all of the stars away.
So I have another question. You were considering the reasons why we miss some novae, right?
Yeah.
So, given the absolute magnitude and having the distribution function in the galaxy, more or less we are able to recover the visible magnitude, right? So, and then 18 magnitude limit would be, we can see if most of the stars are fainter this limit, so that's why we miss most of them or some of them at least. So can you have any comment about it? If you have the limiting magnitude, why Assassin misses, so it is 18, yes?
Yeah, so novae, the median absolute magnitude is about -7.5. So
Okay.
and if we assume the galaxy is 20, 30 kiloparsecs, you still need a lot of dust to make a novae as faint as
Even
18.
independent of dust, just by having the distance, so you have the visible magnitude and most of them can be missed just out of the limit.
If a novae's in the galaxy and there's no dust, it's going to be really bright, like brighter than 12th magnitude. The galaxy is just not that big. I mean, we can see them in other galaxies. So to make a novae really faint, you have to have a lot of dust.
Okay. So, no more questions. Thanks again. And is there any announcement by the organizer? No? Okay.